Hello everyone, I hope you're doing good and staying safe. Welcome to Simplicode's YouTube channel, and today's video is based on Python training program. I hope my audio is fine and the screen is clearly visible. If you guys are facing any issue, do let us know in the comment section below and we will try to fix it as soon as possible. Alright, I see only a few folks have joined the session, so let us just wait for another 2 minutes so that rest of the people will also join as soon as possible. In the meantime, guys, I would like to update that we have regular updates on multiple technologies and programming languages on our channel. So if you're a tech geek and in the pursuit of learning something new, consider getting subscribed to our channel Simplicode to stay updated with all the latest tech content. And hit that bell icon to never miss an update from us. Alright, I see most of you have joined the session, so let's get started. Now, previously we had 2 sessions on Python training tutorial for beginners, wherein we have covered almost all the Python fundamentals that are needed to get started. So we have got a great response from that 2 tutorials, guys. So we are back with another part 3 on Python tutorial training for beginners. Now, in today's session, we'll be discussing some more intermediate to advanced Python topics. So stay tuned for that. So firstly, let us discuss the agenda for today's session, guys. We'll start the tutorial by understanding what is PyCharm and how it is useful and how beginners should start before going on to the advanced level concepts. Now, after that, we'll be discussing some top 5 Python libraries for data science. After that, we'll be discussing some major Python packages and libraries like NumPy, Matplotlib, Python Scikit, and Python Bokeh. Followed by that, we'll perform a thorough exploratory data analysis using certain data sets from Kaggle, wherein we'll perform Python analysis on different concepts like Spotify data analysis, World Happiness Report, Olympic and IPL data analysis. After that, we'll be discussing about Python script mode and web scraping. And then we'll look at through the Python developer roadmap and skills that are needed for a beginner to get started. And after that, we'll understand some reasons to learn Python in 2022. And finally, we'll wrap up the session by discussing some Python interview questions and automation project ideas. I hope I've made myself clear with the agenda and you guys have understood also. So without any further ado, let's get started. Over to our training expert.
Today we're going to be working with PyCharm, the Python IDE or user interface for professional developers in the Python scripting language. For myself, I like PyCharm because it separates your different environments, and if you're working in, say, Python 3.6 and you need to do code in 3.5, you can easily create those different environments in the PyCharm setup. It also has a number of wonderful tools to help you do your different projects and to help you with your coding. We'll start from their website, www.jetbrains.com/PyCharm. JetBrains is the company behind the PyCharm development, even though PyCharm is open source. On this page, you'll see if you come to their main page, and you can just do a search. If you search PyCharm, you'll find this as the top result. You'll see download now, and it says full-fledged professional or free community version. So if we go on the download now button, you'll see where you have the 2 choices. Unless you're doing a lot of sharing and web development where you're interfacing up into the web, you really don't need to pay for the professional version. If it's your first time in, start with the community version, and then as a company, if you need the professional version, you can upgrade. So we'll go down here where it says community, we'll go ahead and click on the download, and then open and run that just like you do any other install onto your computer. And once you've installed it, you'll see this icon on your desktop, the PC for PyCharm icon. I have it in my quick start. I'll go ahead and click on that there and let it open up, and you'll see the PyCharm opening up in the community version 2018.3. Now it'll load up whatever the last project you worked on automatically, and then you can see here where it comes up and has tips, so you can go through some of the tips and see some of the cool tricks you can do. You should also notice on yours that the fonts and everything are a little bit smaller. I intentionally enlarged mine for doing the demos and tutorials, and you can easily position your workspace, which I'm working here in scratch3.py file. That just happens to be the last one I was doing. By default, name them Scratch whenever you start a new file, and you can of course rename them. And you will see on this page there's 3 major well, there's a number of major areas. They have on the left, you have tabs that you can go between, turns on and off things here. Here's our project we're working on, so I can make it disappear if I don't want to have this page open. You'll see on the top, we have our standard file edit view, navigate, and your different toolbar pull downs. Your major icons, in this case, if you hover over it, of course, it'll tell you that it has open, save. You can synchronize this with, if you're working on larger projects and you have the professional version. Generally, you won't use this unless you're in the professional version. You also have like your back or undo. You'll see here where I have scratch. That's the one I'm working on. This tells it what it's running. So if I have multiple files I'm flipping between, I can easily run the different ones, or I can edit the configuration from here also. And then we just have our simple run button. You'll see if I hover over it, it also is Shift F10. We have a debug. It looks like a little bug, which is kind of cool. And we have our settings. And we usually start with the settings. We can get to settings here through the wrench. You can also go under File, and you'll see down here also Settings. And when we go under Settings, we have Appearance. This is all your setup you'll want to get into. This is where I change the font so it's nice and large. You can see I'm using size 24 font. Normally you only need it at 12 for most of your work. And there's a lot of other settings in here you can change as far as the look and feel of your project you're working on in your interface, how you want it to look. You can also adjust the appearance of your editor down here with your different fonts, colors, styles, setup, what menus you want to show up. There's a lot here under the appearance and behavior that you can do, and also along with the editor. We'll come back to settings when we get into our own project, but for right now we're just going to look at the appearance and the editor, and you can change your fonts and everything in there. And we'll close out of that. Other things to note, courses are open. If you're opening up a Python or folder, you can also save. If you go under File, there's the new Scratch file. That's how I come up with the new Scratch file in our project. Your save over, you open recent. There's a lot of different things you can do in here. You can also export and import settings on whatever you're working on. We're going to start off by creating a new project. So the very top selection under File is New Project. And when I click on there, you'll go ahead and give it a name. It has Untitled. We'll call this PyCharm Tutorial. And we'll go ahead and create that. And it asks me, do I want this window, a new window, attach, or cancel? I'll go ahead and keep it in the same window. I could open up a whole new window and project in here, but I don't need to. I don't have anything in the other project that I'm working on, so I can just let this take over. And you'll see it takes about half a minute for it to go through the creating the virtual environment and flashing through all the different files as copying into our new project. And that's important because whatever I do in this project is separate from my other projects. That way, if I have certain imports or certain modules I've added in, I can track what's being used with this project, and then if we're going to deploy it, I'll be able to let the our admin on the server side or whatever is going be able to bundle those and deploy those. Now at this point we want to get jumping on our programming and get started in writing our script for Python, and you can either go up here to our project folder and right click on that, and if you go up to the top you'll see new, and you get a lot of different options. New Scratch file, new file, directory, Python file. You can also get to this by going under File and you'll see New, or you can use the Alt Insert. Any one of those will take you to the same window. And again, we want to select the Python file since we're writing a Python script, and we'll go ahead and do a PyCharm. We'll just call this PyCharm in the Python file, and I'll click OK on there. So now I have an active window up in the middle. You'll see my PyCharm on the left underneath the project PyCharm tutorial. And I didn't mention it yet, but there's also Python console, terminal, and to do on the bottom. Let's go ahead and write some basic code. Let's go ahead and import math. So we'll do a little bit of math here. And from import math, we'll do x equals minus 0.75. And you'll see that as we're doing this, stuff highlights and appears. And so I can do print, and it lets me know what the actual code is. And let's say I'm doing absolute value. I want the absolute value of x. You'll see it appear there on the top, and I can either hit the enter key or I can click on it. And if I click on it, it does absolute value, and we'll type in x. And it even shows me that x is on my list, so there's x. And now that we have all that, let's go ahead and run the code. And the first thing you notice is our run button is not highlighted, and this thing says add configuration. Now I can click on here and add configuration, and I can tell it what I want to run, but I'm very lazy, so we'll just go up to the run button across the top. On the pull down, you'll see run, which is also Alt Shift F10. And if I click on this run, it'll ask me what I want to run, and I want to run my PyCharm. That's the name name of the .py file. And so I'll click on that, and then it'll pop up and we'll hit run on there. You should notice that my configuration has now changed to PyCharm up here on the top, and now I have my run button, so if I ever need to run it again, I can just push this button and it'll know that that's the last one I'm working with and that's what I should run. And this will reset each time you create a new project because you're now in a new environment. That way you can do additional configuration in there. And then we're going to bring it down here, and I want you to notice on the bottom, it's automatically, let me just put a big arrow on here. Here it is, PyCharm. It's opened up a PyCharm and it's opened up a run tab down here. I can now easily get to the output on this, and you can see that the output of the absolute value of minus 0.7 is 0.7, and it says process finished and with exit code. So it's hit the end of the file and is done. And if you're looking at these tabs down here, and I said I was going to come back to them, you can see there's the terminal. So if I want to put terminal commands in here, I can actually, just like as if you're in the terminal user interface, I can print hello, enter. And this is actually the terminal for, this would be if you're doing something like pip install, that kind of thing underneath the terminal. And you can see there's the Python console, and the Python console is just like this. You can type in your straight Python commands. So if you want to do something like that and hit enter, you'll see that print hello, and it prints hello. But we're under the run. And so we've had it up here. This runs this script. And let's say we've had long code and we've decided that after X, and then we had X1 and X5 and new X and old X, we decide we don't want to call this X. We want to call this something different. Well, we can highlight the X or whatever variable it is. We can right click. And this is an important thing to note. You can very easily refactor. Now, refactor is a little different than just changing or renaming it. Refactor goes through your whole code and changes X to whatever you want it to be. And so we'll, instead of call this X, we just want to call this Y, and we'll refactor the Y, and you'll see it changes Y throughout our code. So now we've been working on our code for a while, and we imported math, but what if we wanted to import NumPy as NP, our NumPy array? And we've got our code here. We'll say that we have new array equals np.array 1, 2, 3, 4. And if you've done this before, you know that if you're on your computer and you've never run the NumPy array before, this is an external module, NumPy is. So if I go up here and I run this now, it's going to come up and say import NumPy as NP, module not found, error. No module named NumPy. So when we're looking at this, we can either go underneath the wrench for settings or under file and settings. And we talked about the appearance in here and your editor and how you can adjust all that for different looks. There's also the project and version control. So we go under version control and you can see there's a lot of different options here. But we went under the project, and under the project, there's the project interpreter. So if I wanted to work in something other than, in this case, Python 3.6, I can easily switch this. Right now, I just have 3.6 installed on this setup, on this particular machine. But at some point, I had 2.7 for older projects, and 3.7 is a new Python that just came out, which doesn't work with the number of modules. So you can easily switch what Python you're working on to see if it works with the different modules. And you'll see down here where it has the package also, and it has pip and setup tools. And on the right-hand side, it has the plus, so we can add additional modules in here. And in this case, we want NumPy, so we'll type in NumPy at the top, and it'll come down and you'll see there's NumPy, and then there's a lot of different other versions of NumPy for doing special things. There's NumPy Turtle, NumPy Display, and so on. We want just the basic NumPy. And so when we click on the NumPy, we can now install the package, and this will copy NumPy onto this environment. So this NumPy is now only in this project. That way, if you have another project and you don't want to have to reload all your different Python tools, you just want the ones for that specific project, you don't have to worry about that. And you can see where it pops up down here and says package NumPy installed successfully. So I'll go ahead and close out of this window, and now you can see I have NumPy in my packages. One of the downsides of having such a robust package like PyCharm, which has all kinds of settings, as you can see there's build settings, there's languages and frameworks, there's tools, is the most basic things you need to know where they're at. And so your project setup and project interpreter are one of the most important things to be able to find right away. And of course your appearance, so it appears correctly. So what's the use of having a nice IDE if you can't adjust it so it fits your needs? And we'll go ahead and click OK out of here, and then we'll come back in here to our PyCharm, and we'll go back up here and hit the run, and you'll see now process finished and we don't have an error. Now if I'm done, I can always go up here to File, I can close the project, and then we can go back up here and we can go to open project, or I can just exit out and go back into the software. And then we can always go under and open a file. We can either click on the icon or file and open, and then browse for a file. Let's say I'm an overachiever, so I want to open up another project I'm working on or just did, and I have the option of opening this up in a new window. So I can replace my PyCharm tutorial with my OOP, object-oriented programming, or I can open it up in a new window. And this is nice because now I have the two windows, and if I'm working on, in this case, you'll see classes, I can now flip between the two screens and I have two separate interfaces that I'm going through. And we'll go ahead and close this one out. And then we already talked a little bit about the configuration. I can edit these configurations. We can save the config, but let's go ahead and edit the configurations. And you can see in here it opens up our PyCharm setup. And we also looked at how to get through this through settings. This is just a quick way to get to it. It's just on here with your configuration setup. And you can see here it's running the PyCharm.py. That's the script we've chosen. That's the name of this particular folder or this particular file, PyCharm.py. And you'll also see you can change your Python interpreter here. It's same as we did on these settings. And we have the 3.7, there's my 3.6 environment, 3.6 RE. So I have a lot of different options as far as which environment to choose from. And we already talked about a number of ways to run it. You can go under run and run it from up here. There's our run. You can click on the run key. If you hold your key over there, you'll see that you can also run it using Shift F10. That will run it. And another option is you can right click on this space and also go down here to run. It's always good to have your code actually do something. So we'll come down here and do print new array. And we can run it this way. And you'll see down here it prints our 1, 2, 3, 4. And let's also do a print goodbye, print hello. And one of the nice things you can do with PyCharm is we can then, on this left spot here, click and it'll add a red dot, which is a breakpoint. And this time, instead of running it, we can go through either under the run, you'll see debug charm. You'll see this little bug here. We can right click it and find our picture of the bug down here and debug. If you hold your mouse over it, you'll see Shift F9. So when we run this, it'll come through and it will go ahead and it just stops here at our breakpoint. And then we end up with our variables showing what they are, the modules in PyCharm, and you get a lot of information. And so it's loaded the new array. We now have the new array in here. And if I push F8, that will continue to run. You can also, if you hover your mouse over here, you'll see the debugger. You can also stop PyCharm where it's at. So if we hit the debugger again, it'll continue. Stop and rerun, cancel. If we go under run, you'll see debug also here set up the stop PyCharm. But the key is F8. And when I do F8, it goes down to the next one. So it's going to print hello. And then I hit F8 again and hit F8 again to get to the end of the program. And let's go ahead and write a short script up here. We're going to create like a small matrix. It's a simple list of lists. And we'll do an input so we can get some values into it. We'll say, let's do enter X and Y. And then if we're going to have an enter, we should have X and Y. And this will be an array. We'll do integer X or X in string split comma. So what this does is we're going to generate an X and Y variable here. So if I run this, it'll prompt me down here in our input, and it's looking for like 3, 4. Now if I run this with something that's not an integer, because we have an integer, we're going to convert each of those to an integer. So if I put in A, B, it'll give me a value error because it doesn't know what to do with A, B. And then let's go ahead and create a list, and we'll have our list equals, call it list, and then we'll have, let's see, 0 for column in range Y. Now if you remember from range, that's 0 up to but not including the Y value. So if you enter in 3, that's 0, 1, 2. We're going to assign a 0 for each one of those, but we also want to do that for row in range X. And so what we can do here is we'll do, so right now if we run this and we just print list, which you can do, we'll run that, enter X and Y, we'll go ahead and do 3, 3, and you'll see it creates a list of 0, 0, 0, 0, 0, 0, 0, 0, 0. So we want to go ahead and change that. We'll do for row in range X, and there's so many ways to do this. We could have just as easily done for value in, but we'll do it this way, for a column in range of Y, and we're going to set our list of row and column equal to some other value. And we'll just do row times column. So we should end up with a row, we'll have like a 0 times 0, 0 times 1, 0 times 2, 1 times 1, 1 times 2. And we can do a print like we did before. That's one option. So we can just print list, and we'll go ahead and run that. Let me resize this window so you can see a little better what's going on down below. And we'll stick to our 3, 3, and you'll see that we end up with 0, 0, 0, 0, 1, 2, 0, 2, 4, just multiplying them. That can be really hard to read, and so a lot of times in my own code, I'll do something like this. I'll put when I'm troubleshooting things, I might reformat it, do the same kind of row and column thing for column in range of y, and then we'll just simply print, in this case, list of row of column. And if you run this, this will come out. Let me just go ahead and run this. There we go. We'll enter in, let's do 3, 3, and you'll see that it puts out each value coming down, 0, 0, 0, and so on. These could be very complicated values. It might not just be a number. Another trick we can do, this I find myself doing regularly also, is instead of doing each individual, maybe I need to look at the row to figure out what's going on with my rows. And you can see here, if I type in 3, 3, I'll end up with each row coming across. And this is just simple manipulation of a basic list with sublists. That's all that is. Now, one of the, especially in the data science realm, one of the most important things to start doing is to plot what you're looking at. I don't know how many times this has saved me. I'll be working on a project and something just won't look quite right on my data and my predictions. And then I plot it and I go, oh wow, that is just too perfect of a fit. And I look back at my data and I say, well, it's because I'm fitting the answer to the answer. That sounds very odd, but it does happen. You would be amazed when you get into some of the deep coding what you can do with your predictions in your scikit. So in this case, we're just going to do a simple plot, and the simple plot is in the format of x, or x comma y. So these are all our x values, and we'll do 1, 2, 3, 4, and these are our y values, 1, 2, 3, 4. What's important to note here is, one, we're importing the Matplotlib library, .pyplot as PLT. PLT, once we put it in here, this creates a basically a canvas that you're painting on. So you can plot all kinds of stuff on here, and you won't see anything until you do plt.show. And so when you do plt.show, then we'll display that graph. And let me go ahead and run that and take a look and see what that does. And of course, we have a module error because this is a new environment or a new project. And you'll see it even highlighted it in red up here. And if you remember from that, we can go under settings. Once we're under settings and our project interpreter, we see NumPy up there. Add the plus. And then we need to import Matplotlib. There's our Matplotlib. We'll go ahead and install this package, which takes it just a moment. And once it's done, it appears on the bottom and says package properly installed. Or what it actually says is installed successfully. Once you have that, we can close out of here. We can close out of our settings. You can either click OK on the bottom or you exit out. Either one is fine. And now if we go ahead and run this, and we'll start it over again since I had an error, PyCharm, it'll pop up with a nice figure, and you can see our plot there. 1, 1, 2, 2, 3, 3, 4, 4. And when you are working with the PyPlot library, remember that you're sending, this works really good with NumPy because you can reshape it, because a lot of times you'll end up with your data 1, 1, 2, 3, and you have to reformat it to 1, 2, 3, 4, your X and your Y plots. And if we're going to do NumPy and Matplotlib, the next one is to import pandas as PD, so you have a nice data frame in PyCharm. Again, it's highlighted in red, so we need to go up here underneath our setup, our project interpreter, and up to the plus sign on the right, and let's go ahead and install pandas. And here's our pandas right at the top, so we'll go ahead and install that package, and then you have to wait just a moment for the package successfully installed. And once we see that successfully installed, then go ahead and close out and either OK or exit out. And we're back into our pandas. And then pandas is such a wonderful data frame setup. One of the nice things about it, besides being an excellent displaying of information and data and lots of manipulation you can do, it also makes it really easy to import and export information. I actually have like a file called cars here. I'm going to go ahead and copy the address to it. So here's our address. And if you remember, the backward slash, we either have to do double slash or change it to a forward slash. So we'll just do that really quick. This is for this video we're working on, so it's in my simplilearn videos PyCharm forward slash. In this case it's cars.csv, and we're going to change this into a string so we can pull our data from here. Let's do it this way. Now in some editors you can highlight and just do brackets. I'm actually going to do a Control X, type in our denoter for a string, and then just paste it right in because I'm very lazy. I try to do as few clicks as I can. I'll set path equal to this, ends in the cars.csv because that's the file. And once we have that, we can go ahead and df.pd.read underscore CSV. We have our full path, and then we'll just print, we'll do a full print of our data frame. You can do df.head.tail, there's all kinds of different tools to sort and process your data frame. And let's go ahead and run this, and you can see here it has 261 rows and 8 columns that print out. And since I like to see what it looks like on the top, we'll do head, which does the first 5 rows. And you can see right here we have our MPG cylinders, cubic inches, horsepower, weights per pounds, etc. All the different data pulls in on this. And it puts it in a nice readable rows and column setup. So we covered the basics of PyCharm today. We went from the website where we downloaded it. Up here you can see from JetBrains underneath the community version, which is complete open source and free to use. We went in and learned about our settings, where you can set up your different modules, different ways to get into it, the different ways to run code, where to go ahead and install the modules like Pandas and NumPy that don't come as a default. Remember, PyPlot and Math do come as a default. No, PyPlot doesn't. Just Math comes as a default. So we learned where to install all these different modules from. We've run our basic code. We've shown you how to do the debugger, how to add a flag at the beginning, how to rename your variables and refactor them, so if you want to rename it all the way through, and we walked through the basic running of the programs in the debug run.
As you know, Python is the most popular programming language when it comes to solving data science problems. Due to its flexibility and applications, Python has made its name in data science, artificial intelligence, and machine learning applications. So today, we'll learn the top 5 libraries for data science.
So let's talk about this amazing library, TensorFlow, which is also one of my favorites. So TensorFlow is a library for high performance numerical computations with around 35,000 GitHub commits and a vibrant community of around 1,500 contributors. And it's used across various scientific domains. It's basically a framework where we can define and run computations which involves tensors. And tensors, we can say, are partially defined computational objects again, where they will eventually produce a value. That was about TensorFlow. Let's talk about the features of TensorFlow. So TensorFlow is majorly used in deep learning models and neural networks, where we have other libraries like Torch and Theano also. But TensorFlow has hands down better computational graphical visualizations when compared to them. Also, TensorFlow reduces the error largely by 50 to 60% in neural machine translations. It's highly parallel in a way where it can train multiple neural networks and multiple GPUs for highly efficient and scalable models. This parallel computing feature of TensorFlow is also called pipelining. Also, TensorFlow has the advantage of seamless performance. As it's backed by Google, it has quicker updates, frequent new releases with the latest of features. Now, let's look at some applications. TensorFlow is extensively used in speech and image recognition, text-based applications, time series analysis and forecasting, and various other applications involving video detection. So, favorite thing about TensorFlow that it's already popular among the machine learning community, and most are open to trying it, and some of us are already using it. Now, let's look at an example of a TensorFlow model. In this example, we will not dive deep into the explanation of the model as it is beyond the scope of this video. So here we're using Amnes dataset, which consists of images of handwritten digits. Handwritten digits can be easily recognized by building a simple TensorFlow model. Let's see how. When we visualize our data using Matplotlib library, the inputs will look something like this. Then we create our TensorFlow model. To create a basic TensorFlow model, we need to initialize the variables and start a session. Then after training the model, we can validate the data and then predict the accuracy. This model has predicted 92% accuracy. Let's see, which is pretty well for this model. So that's all for TensorFlow. If you need to understand this tutorial in detail, then you can go ahead and watch our deep learning tutorial from simplilearn as shown in the right corner. Interesting, right? Let's move on to the next library. Now let's talk about a common yet a very powerful Python library called NumPy. NumPy is a fundamental package for numerical computation in Python. It stands for Numerical Python as the name suggests. It has around 18,000 commits on GitHub with an active community of 700 contributors. It's a general purpose array processing package in a way that it provides high performance multi-dimensional objects called arrays and tools for working with them. Also, NumPy addresses the slowness problem partly by providing these multi-dimensional arrays that we talked about, and then functions and operators that operate efficiently on these arrays. Interesting, right? Now let's talk about the features of NumPy. It's very easy to work with large arrays and matrices using NumPy. NumPy fully supports object-oriented approach. For example, coming back to NdArray once again, it's a class possessing numerous methods and attributes. NdArray provides for larger and repeated computations. NumPy offers vectorization. It's more faster and compact than traditional methods. I always wanted to get rid of loops, and vectorization of NumPy clearly helps me with that. Now let's talk about the applications of NumPy. NumPy, along with Pandas, is extensively used in data analysis, which forms the basis of data science. It helps in creating the powerful n-dimensional array. Whenever we talk about NumPy, the mention of the array, we cannot do it without the mention of the powerful n-dimensional array. Also, NumPy is extensively used in machine learning when we are creating machine learning models, as in where it forms the base of other libraries like SciPy, scikit-learn, etc. When you start creating the machine learning models in data science, you will realize that all the models will have their base as NumPy or Pandas. Also, when NumPy is used with SciPy and Matplotlib, it can be used as a replacement of MATLAB. Now let's look at a simple example of an array in NumPy. As you can see here, there are multiple array manipulation routines. Like there are basic examples where we can copy the values from one array to another. We can give a new shape to an array from maybe one-dimensional to we can make it as a two-dimensional array. We can return a copy of the array collapsed into one dimension. Now let's look at an example where this is a Jupyter notebook, and we will just create a basic array, and for detailed explanation you can watch our other videos which targets on these explanations of each libraries. So first of all, whenever we are using any library in Python, we have to import it. So now this np is the alias which we will be using. Let's create a simple array. Let's look what is the type of this array. So this is an NdArray type of array. Also, let's look what's the shape of this array. So this is a shape of the array. Now here we saw that we can expand the shape of the array. So this is where you can change the shape of the array using all those functions. Now let's create an array using arrange functions. If I give arrange 12, it will give me a 1D array of 12 numbers like this. Now we can reshape this array to 3, 4, or we can write it here itself. So this is how arrange function and the reshape function works for NumPy. Now let's discuss the next library, which is SciPy. So this is another free and open source Python library extensively used in data science for high-level computations. So this library, as the name suggests, stands for Scientific Python, and it has around 19,000 commits on GitHub with an active community of 600 contributors. It is extensively used for scientific and technical computations. Also, as it extends NumPy, it provides many user-friendly and efficient routines for scientific calculations. Now, let's discuss about some features of SciPy. So SciPy has this collection of algorithms and functions which is built on the NumPy extension of Python. Secondly, it has various high-level commands for data manipulation and visualization. Also, the ndimage function of SciPy is very useful in multi-dimensional image processing, and it includes built-in functions for solving differential equations, linear algebra, and many more. So that was about the features of SciPy. Now let's discuss its applications. So SciPy is used in multi-dimensional image operations. It has functions to read images from disk into NumPy arrays, to write arrays to disk as images, resize images, etc., solving differential equations, Fourier transforms, then optimization algorithms, linear algebra, etc. Let's look at a simple example to learn what kind of functions are there in SciPy. here I'm importing the constants package of SciPy library. So in this package, it has all the constants. So here I'm just mentioning C or H or NA, and this library already knows what it has to fetch, like speed of light, Planck's constant, etc. So this can be used in further calculations. Data analysis is an integral part of data science. Data scientists spend most of the day in data munging and then cleaning the data also. Hence, mention of Pandas is a must in data science lifecycle. Yes, Pandas is the most popular and widely used Python library for data science, along with NumPy and Matplotlib. The name itself stands for Python data analysis, with around 17,000 commits on GitHub and an active community of 1,200 contributors. It is heavily used for data analysis and cleaning as it provides fast, flexible data structures like data frames, series, which are designed to work with structured data very easily and intuitively. Now let's talk about some features of Pandas. So Pandas offers this eloquent syntax and rich functionalities. Like there are various methods in Pandas like drop NA, fill NA, which gives you the freedom to deal with missing data. Also, Pandas provides a powerful apply function, which lets you create your own function and run it across a series of data. Now forget about writing those for loops while using Pandas. Also, this library's high-level abstraction over low-level NumPy, which is written in pure C. Then it also contains these high-level data structures and manipulation tools, which makes it very easy to work with Pandas, like their data structures and series. Now let's discuss the applications of Pandas. So Pandas is extensively used in general data wrangling and data cleaning. Then Pandas also finds its usage in ETL jobs for data transformation and data storage, as it has excellent support for loading CSV files into its data frame format. Then Pandas is used in a variety of academic and commercial domains, including statistics, finance, neuroscience, economics, web analytics, etc. Then Pandas is also very useful in time series specific functionality like date range generation, moving window linear regression, date shifting, etc. Now let's look at a very simple example of how to create a data frame. So data frame is a very useful data structure in Pandas and it has very powerful functionalities. So here I'm only enlisting important libraries in data science. You can explore more of our videos to learn about these libraries in detail. So let's just go ahead and create a data frame. I'm using Jupyter Notebook again, and in this, before using Pandas, here I'm importing the Pandas library. Let me go and run this. So in data frame, we can import a file, a CSV file, Excel files. There are many functions doing these things, and we can also create our own data and put it into data frame. So here I am taking random data and putting in a data frame. Also I'm creating an index and then also giving the column names. So PD is the alias we've given for Pandas, random data of 6x4, index which is taking a range of 6 numbers, and column name I'm giving as ABCD. Now let's go ahead and look at it. So here it has created a data frame with my column names at ABCD, my list as 6 numbers 0 to 5, and a random data of 6x4. So data frame is just another table with rows and columns where you can do various functions over it. Also, I can go ahead and describe this data frame to see. So it's giving me all these functionalities where count and mean and standard deviation, etc. Okay, so that was about Pandas. Now let's talk about next library and the last one. So Matplotlib for me is the most fun library out of all of them. Why? Because it has such powerful yet beautiful visualizations. We'll see in the coming slides. Plot and Matplotlib suggests that it's a plotting library for Python. It has around 26,000 commits on GitHub and a very vibrant community of 700 contributors. And because of such graphs and plots that it produces, it's majorly used for data visualization. And also because it provides an object-oriented API which can be used to embed those plots into our applications. Let's talk about the features of Matplotlib. The PyPlot module of Matplotlib provides MATLAB-like interface. So Matplotlib is designed to be as usable as MATLAB with an advantage of being free and open source. Also, it supports dozens of backends and output types, which means you can use it regardless of which operating system you're using or which output format you wish. Pandas itself can be used as wrappers around Matplotlib's API so as to drive Matplotlib via cleaner and more modern APIs. Also, when you start using this library, you will realize that it has a very little memory consumption and a very good runtime behavior. Now let's talk about the applications of Matplotlib. It's important to discover the unknown relationship between the variables in your dataset. So this library helps to visualize the correlation analysis of variables. Also in machine learning, we can visualize 95% confidence interval of the model just to communicate how well our model fits the data. Then Matplotlib finds its application in outlier detection using scatterplot, etc. and to visualize the distribution of data to gain instant insights. Now let's make a very simple plot to get a basic idea. I've already imported the libraries here. So this function matplotlib inline will help you show the plots in the Jupyter notebook. This is also called a magic function. I won't be able to display my plots in the Jupyter notebook if I don't use this function. I'm using this function in NumPy to fix random state for reproducibility. Now I'll take my n as 30 and will assign random values to my variables. So this function is generating 30 random numbers. Here I'm trying to create a scatter plot. So I want to decide the area. Let's put this. So it's just multiplying 30 with random numbers to the power 2 so that we get the area of the plot, which we will see in just a minute. So using the scatter function and the alias of matplotlib as plt, I've created this. If I don't use this, then I have very small circles as my scatter plot. It's colorful, it's nice. So that's one very easy plot. I suggest that you explore more of Matplotlib and I'm sure you will enjoy it. Let's create a histogram. So I'm using the style as ggplot and assigning some values to these variables, any random values. Now we are assigning bars and colors and alignment to the plot. And here we get the graph. So we can create different type of visualizations and plots and then work upon them using Matplotlib, and it's just that simple. So that was about the leading Python libraries in the field of data science. But along with these libraries, data scientists are also leveraging the power of some other useful libraries. For example, like TensorFlow, Keras is another popular library which is extensively used for deep learning and neural network modules. Keras wraps both TensorFlow and Theano backends, so it is a good option if you don't want to dive into details of TensorFlow. Then scikit-learn is a machine learning library. It provides almost all the machine learning algorithms that you need, and it is designed to interpolate with NumPy and SciPy. Then we have Seaborn, which is another library for data visualization. We can say that Seaborn is an enhancement of Matplotlib as it introduces additional plot types.
NumPy is one of the most powerful libraries in Python and is used in data science applications. So today, we'll cover all you need to know about NumPy and its concepts and how to use it in the Python. So let's begin.
Now we're going to go over what is NumPy, installing and importing NumPy array versus Python list, basics of NumPy, finding size and shape of any array, range and arrange functions, NumPy string functions. And then in part 2, I'll move on to cover axes, array manipulation, and much more. So let's start with what is NumPy. NumPy is the core library for scientific and numerical computing in Python. It provides high-performance, multi-dimensional array object and tools for working with arrays. And I'll go a step further and say there are so many other modules in Python built on NumPy. So the fundamentals of NumPy are so important to latch onto for the Python so that you can understand the other modules and what they're doing. NumPy's main object is a multi-dimensional array. It is a table of elements, usually numbers, all of the same type, indexed by a tuple of position integers. In NumPy, dimensions are called axes. Take a one-dimensional array, or we have, and remember dimensions are also called axes, so you can say this is the first axis, 0, 1, 2, 3, 4, 5. And you can see down here it has a shape of 6. Why? Because there's 6 different elements in it in the one-dimension array. And they usually denote that as 6 comma with an empty node on there. And then we have a two-dimensional array where you can see 0, 1, 2, 3, 4, 5, 6, 7. And in here we have 2 axes or 2 dimensions, and the shape is 2, 4. So if you were looking at this as a matrix or in other mathematical functions, you can see there's all kinds of importance on shape. We're not going to cover shape today, but we will cover that in part 2. Did you know that NumPy's array class is called NDArray for NumPy Data Array? Now we're going to take a detour here because we're working in Python, and 2 of my favorite tools in Python is the Jupyter Notebook, and then I like to use that sitting on top of Anaconda. And if you flip over to jupyter.org, that's jupyter.org, You can go in here. You can install it off of here if you don't want to use the Anaconda notebook. But this is the Jupyter setup, the documentation on the Jupyter. Jupyter opens up in your web browser. That's what makes it so nice, is it's portable. The files are saved on your computer. They do run in IPython or IronPython, and you can create all kinds of different environments in there, which I'll show you in just a minute. I myself like to use Anaconda. That's www.anaconda.com. If you install Anaconda, it will install the Jupyter Notebook with the Anaconda separate. And you can install Jupyter Notebook and it'll run completely separate from Anaconda's Jupyter Notebook. And you can see here I've now opened up my Anaconda Navigator. What I like about the Navigator, and this is a fresh install on a new computer, which is always nice. I can launch my Jupyter Notebook from in here. I can bring other tools, so the Anaconda does a lot more. And under environments, I only have the one environment, and I can open up the terminal specific to this environment. This one happens to have Python 3.7 in it, the most current version as of this tutorial. And then you open a terminal if you're going to do your pip installs and stuff like that for different modules. You can also create different environments in here. So maybe you need a Python 3.6, Python 3.5. You can see we're having a nice framework like Anaconda really helps. So you don't have to track that on your own in the Jupyter Notebook and your different Jupyter Notebook setups. We'll go ahead and launch this Jupyter Notebook. And then I've set my browser window for a default of Chrome. So it's going to open up in Chrome. And you can see here, this opens up a folder on my computer. We have a couple different options on here. Remember, I set the environment up as Python 3.7. You would install any additional modules that aren't already installed in your Python on this. And it keeps them separate. So you do have to, for each environment, install the separate modules so they match the environment on there. And in here we have a couple things where you can look up what's running. You have your different clusters. Again, I just installed this on a new machine, so I just have a couple things in here that were run on here recently. And where we go on here is we then have on the upper right, New, and from the pull down menu you'll see Python 3, and this will open up a new window. And now we're in Jupyter Python, so this is a Python window, and we'll just do a print. And this, of course, let's go hello world. And we'll run that and it prints out hello world in the command line. There's a couple special things you have to know what we're not going to do today, which is on graphics. If you've never seen this, one of the things you can do is you can also do A equals hello world. And if you just put the A in there, now if you do a bunch of these where you have A equals hello world, B equals goodbye world, and you put A, B, A, then return B, it'll only run the last one. But you can see here, if you put the variable down here, it will show you what's in that variable. And that has to do with the Jupyter Notebook inline coding. So that's not basic Python, that's just Jupyter Notebook shorthand, which you'll see in a little bit. So back to our NumPy array versus Python list. Python list being the basic list in your Python. Why should we use NumPy array when we have Python list? Well, first, it's fast. The NumPy array has been optimized over years and years by multiple programmers, and it's usually very quick compared to the basic Python list setup. It's convenient, so it has a lot of functionality in there that's not in the basic Python list. And it also uses less memory, so it's optimized both for speed and memory use. And let's go ahead and jump into our Jupyter Notebook. Since we're coding, the best way to learn coding is to code. Just like the best way to learn how to write is write, and the best way to learn how to cook is cook. So let's do some coding here today. And just like any modules, we have to import NumPy. We almost always import it as NP. That is such a standard. So you'll see that very commonly. We can just run that. And now we have access to our NumPy module inside our Python. And then the most common thing, of course, is to go ahead and create a NumPy array. And in here, we can send it a regular list. And so we'll go ahead and send this a regular array. Let's go 1, 2, 3 to make it simple. And then I'm just going to type in A, and we'll run this. And so you can see down here, the output is an array of 1, 2, 3. And we could also do print, just a reminder that this is an inline command, so that wouldn't work if you're using a different editor. You can see that it's an array 1, 2, 3. But we'll go ahead and leave it as A. Kind of a nice feature so you can see what you're doing really quick in the Jupyter Notebook. And just like all your other standard arrays, I can go A of 0, which is going to be a value of 1. Of course, we do A of 1. You go all the way through this. A of 1 has a value of 2 in it. So whether you're using the NumPy array or the basic Python list, that's going to be the same. That should all look pretty familiar and be pretty straightforward. Remember, the first value is always 0. when we set on there. So let's take a look why we're using NumPy, because we went over the slide a little bit, but let's just take a look and see what that actually looks like. And what we want to look at is the fact that it's fast, convenient, and uses less memory. So let's take a glance at that in code and see what that actually looks like when we're writing it in Python and what the differences are. And to do this, I'm going to go ahead and import a couple other modules. We're going to import the time module so we can time it. And we're going to import the system module so that we can take a look at how much memory it uses. And we'll go ahead and just run those so those are imported. And so we'll do b equals range of 1,000 is fine. And so that's going to create a list of 1,000, 0 to 999. Remember, it starts at 0 and it stops right at the 1,000 without actually going to the 1,000. And let's go ahead and print. And we want system.getSize of. And we'll pick any integer because we have 0 to 1,000. We'll just throw one in there, 5. It doesn't matter because it's going to whatever integer we put in there is going to generate the same value because we're looking at the size of how much memory it stores an integer in. And then we want to have the length of the b. That's how many integers are in there. And if we go ahead and execute this and run this at a line, we'll see, oops, I did that wrong, comma. If we multiply them together, we'll see it generates 28,000. So that's the size we're looking at is 28,000. I believe that's bytes. That sounds about right. So let's go ahead and create this in NumPy, and we'll go with c equals np, and this is a range. So that's the NumPy command to do the same thing that we were just doing in a list. And we'll also use the same value on there, the 1,000. And then once we've created the value of c for np.arange, let's go ahead and print. And we can do that by doing c.size times c.item size. And that's very similar to what we did before. We did get the size of, so the c size is the size of the array, and each item size, just reversed. So it's the size of an integer 5, item size is going to be the integers, and c size. And let's just take a look and see what that generates. And wow, okay, we got 4,000 versus 28,000. That's a significant difference in memory, how much memory we're using with the array. And then let's go ahead and take a look at speed. Let's do size. We tried this with lower values, and it would happen so fast that the NP array kept coming up with 0 because it just rounded it off. So size, and let's create an L1 equals range of size, and we'll do an L2. We'll just set up to the same thing. It's also range of size on there. There we go. And then we can do on A1 equals np dot arange size. And then let's do on A2 equals np dot arange. We'll keep it the same size. And what we're going to do is we're going to take these two different arrays and we're going to perform some basic functions on them. But let's go ahead, actually let's just load these up now. We'll go ahead and run this so those are all set in memory. Except for the typo here. Quickly fix that. There we go. So these are now all loaded in here. And let's do a start equals time.time. So it's just going to look at my clock time and see what time it is. And then we'll do result equals, and let's do, let's say we got an array, and we're going to say, let's do some addition here. X plus Y for X comma Y. And we'll zip it up here. Two different arrays. So here's our two different arrays. We're going to multiply each of the individual things on here. L1, L2. There we go. So that should add up each value. So L1 plus L2, each value in each array. And then we want to go ahead and print. And let's say Python list took. And then we'll do time dot time. We'll just subtract the start out of there. So time, whoops, I messed up on some of the quotation marks on there. Okay, there we go. Time minus the start. And we'll convert that to seconds, so we'll go, because that's in milliseconds, so times 1000. And let's hit the run on there. And this is kind of fun because you also get a view while we're doing this of some ways to manipulate the script. And as you can see, also my bad typing. There we go. Okay, so we'll go ahead and run this. And we can see here that the Python list took 34. Actually, I have to go back and look at the conversion on there. But you can see it takes roughly 0.34 of a second. And we can go ahead and print the result in here too. Let's do that. And we'll run that just so you can see what kind of data we're looking at. And we have the 0, 2, 4, 6, 8. So it's just adding them together. It looks pretty straightforward on there. And if we scroll down to the bottom of the answer, again, we see Python list took 46. A little different time on there depending on what core, because this is on an 8-core computer, so it just depends on what core it's running on, what else is pulling on the computer at the time. And let's go back up here and do our start time. Paste that into here. And this time we're going to do a result equals, and this is really cool. Notice how elegant this is. It's so straightforward. This is a lot of reason people started using NumPy is because I can add the two arrays together by simply going A1 plus A2. It makes a lot of sense, both looking at it, and it's just very convenient. Remember that slide we're looking at? Fast, convenient, and less memory. So look how convenient that is. Real easy to read, real easy to see. And I don't know if we don't need to print the result again, so let's just go ahead and print the time on here. And we'll borrow this from the top part because I really am a lazy typer. And this isn't the Python list, this is the NumPy list, or NumPy array. And let's go ahead and see how that comes out. And we get 2.99. So let's take a look at these two numbers, 46 versus 2.99. So we'll just round this up to 3. That's a huge difference. That's like more than 10 times faster. That's like 15 times roughly at a quick glance. I'd have to go do the math to look at it. And it's going to vary a little bit depending on what's running in the background on the computer, obviously. So we've looked at this, and if we go back here, we found out it's much faster. Yes, there's going to be different speeds depending on what you're doing with the array. Very convenient, easy to read, and it uses less memory. So that's the core of the NumPy. That's why a lot of people base so many other modules on NumPy and why it's so widely used. So we did glance at a couple operations while we were looking at speed and size. Let's dive into a little bit more into the basic operations. And these are always nice to see. I mean, certainly you want to go get a cheat sheet if you're using it for the first time. Look things up. Google is your friend. We did this for the most basic numpy.array or np.array. And we'll go ahead and create an array. Let's do pairs, 1, 2. And then let's do 3, 4. And if we're going to do that, let's do 5, 6. There we go. And if we go ahead and take this and run this, I can go ahead and do our A down here so it's in line and it'll print that out. You can see it makes a nice array for us. So we have A, and if you look at that, we have 3 different objects, each with 2 values in them. And hopefully you're starting to think, well, how many dimensions or indexes is that? And you'll see 3 by 2. So let's go ahead and take a look, and let's go, how about A.nDimensions? Speaking of which, we'll run that, and we have 2 dimensions for each object. And then we can do the item size, so A dot. We saw this earlier, where we looked up how many items. It was up here, where we wanted to multiply item size times the actual size of the object. So the memory is being used versus the item size. And we should see 4 there. Memory is compressed down. That's always a good thing. And then the shape. The shape is so important when you're working with data science and you're moving it from one format to another. So we have our shape. We just talked about that. We have 3 by 2. 3 rows by 2 objects in each one. Generally, I don't look too much at the size, but the dimensions I'm always looking up. And this is nice, you can automate it. So you might be converting something, you might need to know how many dimensions are going into the next machine learning package so that you can automatically just have it send that information over. So we looked at A shape. Let's go ahead and create a slightly different array, np.array. Let's go ahead and just do as our original setup here. And one of the features we can do, which is really important, is we can do dtype equals. In this case, let's do NP float 64. And so what we've done is we're converting all of these into a float, and we type in A. And now instead of having 1, 2, 3, 4, 5, 6, you see they're all float values. 1.0, there's no actual 0 in there, just there's a 1 dot, or the 1 period, 2, 3 period, 4 period, 5 period, 6 period. And this, again, data science, I don't know how many times I've had to convert something from an integer to a float so that's going to work correctly in the model I'm using. So very common features to be aware of and to be able to get around and use. And we'll also do, let's just curiosity, item size. We'll go ahead and run that. And we see that it doubled in size. So it's not a huge increase. Well, doubling is always a big increase in computers. But it's not a huge increase compared to what it would be if you're running this in the Python list format. And then we did the shape earlier without having it set to the float 64. Let's go ahead and do a shape with it set to 64. And it should be the same 3, 2. So it all matches. So we've gone through, and remember, if this is all brand new to you, according to the Cambridge study at the Cambridge University, if you're learning a brand new word in a foreign language, the average person has to repeat it 163 times before it's memorized. So a lot of this, you build off of it, so hopefully you don't have to repeat it 163 times. But we did manage to repeat it at least twice here, if not a little bit more. And let's go ahead and take this. We're going to go look at one more setup on here. And let me just take this last statement here on the converting our properties of our data. And instead of float 64, let's do complex. Let's just see what that looks like. And let's go ahead and print that out and run it. And so we now have a complex data set up, and you'll see it's denoted by the 1 dot plus 0 dot j. And if we flip over here and do a basic search for NumPy data types, better to go to the original web page, but pull up a bunch of these. You can see there's a whole list of different NumPy data types. Shorthand, complex, we have complex, complex 64, complex 128. Complex number represented by 2 64-bit floats, real and imaginary components. One option on there, float 16, float 32. Float, shorthand for float 64, most commonly used. And of course all the different ones that you can possibly put into your NumPy array. So we covered a basic addition up there when we were comparing how fast it runs. But some very basic components, how to set up a NumPy array, how many dimensions it has, item size, data type, again we went to item size, and there's also the shape. Probably one of the more used. I use a shape all the time, very commonly used. And then down here you can see where we actually created a NumPy complex data type. So let's look at some other features in NumPy. One of them is you could do NumPy dot zeros, and we're going to do 3, 4. There we go. And we'll go ahead and run this, and you can see if I do np.zeros, I create a NumPy array of zeros. This is really important. I was building my own neural network, and I needed to create an array where I initialized the weights, and I wanted them all to be the same weight. In this case, I wanted them to start off as 0 for the particular project I was working on. And there's other options, like you can do NumPy1s, and we'll do the same thing, 3, 4, we'll run that. And you can see I've created an array of NumPy1s. In this case, it comes out as a float array. And then this is an interesting to note, because we have, let's go back to our Python and do lrange5, and we'll print the L, so that's our list. And if I run that, it doesn't create the range until after the fact, until you actually execute it. That's an upgrade in Python. Python 2.7 actually created the array, 0, 1, 2, 3, 4. This one actually creates the script, and then once it's used, it then actually generates the array. And if we do that in NumPy arange, remember that from before, and if we do NumPy arange 5, and let's do L equals, or we can just leave it as NumPy, that's fine. There we go, and just run that. You can see there we actually get an array, 0, 1, 2, 3, 4 for the value of the NumPy arange 5. It generates the actual array. And for part 1, we're going to do just one more section on basic setup. And we're going to concatenation Do a concatenation out example. There we go. We're going to do strings. Let's take a look at strings and what's going on with there. And let's do, let's see, print. Let's do an NP character, something new here. And we're going to add, and then here's our brackets for what we're going to add. Oh, and let's say, let's do hello, comma, hi. And in the brackets on there, let's create another one. And this one's going to be ABC, and we'll do XYZ. So we're just creating some, randomly making some up on here. And then we'll go ahead and just print this. If we run that, you can come down here, and of course make sure all your brackets are open and closed correctly. And then you can see in here when we concatenate the example in NumPy, it takes the two different arrays that we set up in there and it combines the hello with the ABC and the hi with XYZ. And if we can also do something like print, let's do np character dot multiply. So there's a lot of different functions in here. Again, you can look these up. It's probably good to look them all up and see what they are, but it's good to also just see them in action. And let's do hello space, comma, 3. And we'll run this one and run that without the error. And you'll see it does hello, hello, hello. So we multiplied it by 3. And we can also, and let's just take this whole thing here instead of retyping it. And we can do character center. So instead of multiply, let's do center. And over here, keep our hello going. Take the space out of there. And let's do center at 20 and fill character equals, we'll fill it with dashes. So if we run this, you can see it prints out the hello with dashes on each side. And we keep going with that. We can also, in addition to doing the fill function, we can play with capitalize, we can title, we can do lowercase, we can do uppercase, we can split, split line, strip, join. These are all the most common ones. And let's go ahead and just look at those and see what those look like, each one of them. Here we're going to do the hello world, all-time favorite of mine. I always like to say hello universe. And you can see here we did a capital H with the world, but so we want to capitalize. So capitalize is the first one in the array. So we get hello world on there. And we can also take this and instead of capitalizing, another feature in here is title. And let's just change this to how are we doing? How are you doing? Instead of we, we'll do you. And let's run that. And you can see here, because we created it as a title, it capitalizes the first letter in each word. And in this one, we're going to do character lower. Two different examples here. We have an array. We have hello world all capitalized, and we have just hello. And you can see that one is an array and one is just a string. If we run that, you get an array with hello world lowercase and hello lowercase. And if we're going to do it that way, we can also do it the opposite way. There's also upper. And let's paste those in there. And you can see here we have character.upper opposite there, python.data, and we'll do Python is easy. Hopefully you're starting to get the picture that most of the Python and the scripting is very simple. It's when you put the bigger picture together and starts building these puzzles and somebody asks you, hey, I need the first letter capitalized, unless it's the title, and then you start realizing that this can get really complicated. So NumPy just makes it simple, and we like that. And so in this case we did Python data, it's all uppercase, Python is easy, like shouting in your messenger, Python is easy. And then if you're ever processing text and tokenizing it, a lot of times the first thing you do is we just split the text, and we're just going to run this np.character.split, are you coming to the party? If we do that, it returns an array of each of the individual words. Are you coming to the party, splitting it by the spaces? And then if you're going to split it by spaces, we also need to know how to split it by lines. And just like we have the basic split command, we also have split lines. Hello, and you'll see here the scoop in for our new line. And when we run that, if you're following the split part with the words, you should see hello, how are you doing? The two different lines are now split apart. And let's just review 3 more before we wrap this up. commonly used string variable manipulations. We have strip, and in this case we have Nina, admin, Anita, and we're going to strip A off of there. And let's see what that looks like. And then you end up with nin, demin, nate. It basically takes up all leading and trailing letters. In this case we're looking for A. More common would be a space in there, but it might also be punctuation or anything like that that you need to remove from your letters and words. And if we're going to strip and clean data, we also need to be able to reformat it or join it together. So you see here we have a character join. We'll go ahead and run this. And it has on the first one, it splits each of the letters up by the colon and the second one by the dash. And you can see how this is really useful if you're processing, in this case, a date. We have day, month, year, year, month, date. Very common things to have to always switch around and manipulate depending on what they're going into and what you're working with. And finally, let's look at one last character string. We're going to do replace. If you're doing misinformation, this is good, pulling news articles and replacing is and what. In this case, we're just doing he is a good dancer. We're going to replace is with was. And you can see here, he was a good dancer. Hopefully that's not because he had a bad fall. He just was from 1920s and has gotten old. So there we go. We've covered a lot of the basics in NumPy as far as creating an array. Very important stuff here when you're feeding it in. How do we know the shape of it, the size of it? What happens when we convert it from a regular integer into a float value as far as how much space it takes? We saw that that doubled it. Item size, you have your in dimensions, and probably the most used is shape. And we'll cover more on shape in part 2. So make sure you join us on part 2 because there's a lot of important things on shape in there and setting them up. We also saw that you can create a zeros-based array. You can create one with ones. If we do a range, you can see how it is a lot easier to use to create its own range, or a range as it is in NumPy. And you saw how easy it was to add 2 arrays. We saw that earlier, just plus sign. Then we got into doing strings and working with strings and how to concatenate. So if you have 2 different arrays of strings, you can bring them together. We also saw how you can fill, so you can add a nice headline, dash, dash, dash. We saw about capitalize the first letter. We saw about turning it into a title, so all the first letters are capitalized. Doing lowercase on all the letters, upper for all the letters, just lower and upper, nice abbreviation. We also covered how to split the character set, how to strip it. So if you want to strip all the A's out from leading A's and ending A's or spaces, you can do that very easily. Also how to join the data sets. So here's a character join option for your strings. And finally we did the character replace. We covered a lot in part 1.
We will cover some more concepts and operations in NumPy. Please watch the first part before proceeding with the second part.
We covered part 1, where we went over the difference between the Python array and the NumPy array, and why it's both easier to use, uses less memory and resources, and is also faster than the Python list. We also went over a number of the basic features in there, like looking up the min, the max, the median, how you can go ahead and create some very basic arrays, fill them all with zeros, fill them all with ones, look up the size, the shape. So we covered a lot. We covered a range, which is equivalent of Python, well, sort of the equivalent of Python list range. And then we looked a lot into characters and working with the NP character and how to capitalize, center it, change it to a title, lowercase, uppercase, splitting, stripping, joining, and replacing characters. So what's in it for you? Today we're going to go over array manipulation. We're going to go over NumPy, arithmetic operations, slicing arrays, iterating over arrays, array concatenation, splitting arrays, NumPy histogram using Matplotlib library, and a few other useful functions in the NumPy. And then we'll do a practice examples at the end. And hopefully you already got your Jupyter notebook. I like to use it through Anaconda, but certainly you can just use a direct Jupyter notebook. Now let's go ahead and dive in there since we're going right into part 2, which is getting some coding going under our belt. And here in our Jupyter notebook, we can go under New and create a new folder, Python 3. I think I forgot to do this last time, but we could just do the Control++, which in any browser enlarges a page, makes it a lot easier to see. Always a nice feature. Another beautiful benefit of using Jupyter Notebook. And let me go ahead and show you a neat thing we can do in Jupyter. This is nice if you're working with people and you're doing this as a demo on a large screen. I'm going to do the hashtag or pound symbol array manipulation, kind of a title of what we're working on. And then I'm going to call this cell type markdown as opposed to code. And you'll see it highlights it here, and then if I run it, it just turns it into array manipulation. And then we're specifically going to be working on array manipulation, changing shape to start with. And we'll go ahead and mark this cell also a markdown, so it has a nice little look there. And then it comes up, and you can see it, just like I said, it just highlights it and makes it in bold print, just making it easier to read. Not a Python thing, but a Jupyter thing that's good to know about, especially if you're working with the shareholders, since they're investing money in you. Of course, the first thing we want to do is import. We're going to import NumPy as in P, and that should be standard by now. By now, you start a Python program, you're doing some data science. NumPy is just something you bring in there. And let's go ahead and create our array, and we're going to do that as the np.arange. Remember, that's 0. Well, we're going to do 0 to 9, and then we'll go print. Put a little title on the original array. We'll just print that array A. Remember from the first lesson. So we have our array, which is 0, 1, 2, 3, 4, 5, 6, 7, 8. And let's add a print space in between. Let's create a second array, B, but we want this to reshape array A. And what does that mean? And the command is simply reshape. And then we have 9 items in here, and this is so important right now. So be very aware, if I did some weird numbers in here, it's not going to work. And we want multiples of 9. We know that 3 times 3 is 9. So we're going to reshape our A array by 3 by 3. And then we're going to print, well, let's give it a title. Oops, I had too many brackets in there. Modified array, and then let's go ahead and print our B. And let's see what that looks like. And as we come down here, you can see we've taken this and it's gone from 0, 1, 2, 3, 4, 5, 6, 7, 8 to an array of arrays. And we have 0, 1, 2, 3, 4, 5, 6, 7, 8. And so we split this into 3 by 3. And you can guess that if I tried to reshape this, let's just do a 5 by 3, which is 15, that's going to give me an error. So it's not going to work. You're not going to be able to reshape something unless the shape, all the data in there matches correctly. So we can take this flat 9, and they call it a flat because it's just a single array. And we can reshape it into a 3 by 3 array. And first you might think matrices, which this is used for that, definitely. I use it a lot in graphing, because it'll come in that I have an array that's xy, comma, xy1, y1, comma, x2, y2. And so the shape of it might be 2 by the length of the number of points. And I need to separate that into x flat array and a y flat array. And you can see this can be very easy to reshape the array doing that. And we can, of course, go back. We can do b, do a print, and we'll do b.flatten. Remember I said it's called a flatten array? And if we run that, you'll see it just goes back to the original one. It takes this 0, 1, 2, 3, 4, 5, 6, 7, 8 and flattens it back to a single array. And then one other feature to be aware of is if we flatten it, one of the commands we can put in there is order. Let me just go ahead and do that. Order equals F. Strangely enough, F stands for Fortran. The whole Fortran days. I remember actually studying Fortran programming language. In this case, you'll see that it uses the first, like 036 is the order. So instead of flattening it like we had before, 0, 1, 2, 3, 4, 5, 6, 7, 8, it now does 0, 3, 6, 1, 4, 7, 2, 5, 8. And if you go to the NumPy array page, you can see here that they have the flatten. I just open up the NumPy ND array flatten setup to look it up. And they have 3 different options. They have C, F, and A. And it's whether to flatten in C, which was based on how the C code works for flattening, or originally worked, which is row major. Fortran, which is column major, or preserve the column Fortran ordering from A. So whatever it was in, the default is the C version. So the default that you saw, you could put order equals C and it'd have the same effect as we saw there before. You could even do order equals A. That would also have the same effect because that's the default. So really the only other thing you usually change on here is to change it to C if you need it. And you can see right here, or F, I mean not C. The only thing you really want to change it to is to your F for the Fortran order, which then does it by column versus by row. And let's look at, here we go, reshape. So let's create a range of 12, and let's reshape it. And we'll do 4, 3 for this one. And remember this is NumPy. I forgot the NP there. NP.arrange. and we can type in just A for print, or you can do full print A. And of course, in Jupyter Notebook, you even have a little extra print at the beginning. When we run this, we'll see we create a nice array of 0, 1, 2. It's reshaped it. So we have 4 rows and 3 columns, or you could call that 3 columns and 4 rows. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But this one is so important. We'll do NP transpose A. Let's go ahead and run that. And it helps if I get all the S's in there and don't leave an S out. And you'll see here we've taken our array. If you remember correctly, we had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we've swapped it. So we've gone from a 3x4 or a 4x3 to a 3x4. And this really helps if you're looking at like a huge number of rows and the data all comes in. Like let's say this is your features in row 1, your features in row 2, and this is X, Y, Z. Well, when you go to plot it, you send it all of X in one array, all of Y in one array, and all of Z in another array. And so it's really important that we can transpose this rather quickly. This is kind of a fun thing. I can highlight it and do brackets around it. And if you remember correctly, because we're in Jupyter, it doesn't matter where we do the print or not. It'll automatically print it for us. And you see if I hit the run button, it comes up with the same exact thing. And let's play with the reshape. And you know what, let's zoom this up a little bit here. Make that even bigger so you can really see what's going on. And let's play with the reshape just a little bit more. We'll do B equals np.arange. Let's do 8. And reshape, we'll do 2, 4. Let's go ahead and print B and then run that. And you'll see we have now the 2 rows. This is a bit more like, so we have 4, maybe 2 rows of 4 things. So this might be all of our X components and our Y components. So we can switch it back and forth real easy. Important to note here, whether we do 2, 4, or in the case of 4, 3, this has 12 elements. And so however you split it up, it's got to equal 12. So 4 times 3 equals 12. That's pretty straightforward. Same thing down here. 2 times 4 equals 8. If I change this, and let's say I do 2, 3, let's just run that in, and you'll find we get an error because you can't split 8 up into 2 rows by 3. You have to pick something that it can split up and arrange it in. So let's go ahead and run that. And just for fun, let's go reshape our B again, if I can type. Reshape our B again. And what else goes into 8? Well, we could do 2 by 2 by 2. So we can take this out to 3 different dimensions. And then if we, because this is going to come out, as a variable, we can just go ahead and run it, and it'll print it. We could also do a print statement on there, just like we did before. And you'll see we have 2 different groups of 2 variables of 2 different dimensions. So 2 by 2 by 2. And let's go ahead and assign this to a variable. C equals B reshape. And let's do something a little different. Let's roll the axes. Roll axes. And we'll take our C and do 2, 1. And if we go ahead and run this, it's going to print that out. Whoops. Hit a wrong button there. Let's do that one again. And you roll the axis and you can see that we now have, instead of 0, 1, 2, 3, 4, 5, 6, 7, we now have the 0, 2, 1, 3, 4, 6, 5, 7. So what's going on here? We're taking and we're rolling the numbers around, and let's just simplify this. We'll just do it with C, 1 and run that. And so if we roll a single axis, you got 0, 1, and then it rolled the 4, 5 up, and then we have 2, 3, 6, 7. And if we do 2, let me see what happens there. And this is one of those things you really have to play with and start feeling what it's doing. We've now taken 0, 2, 4, 6, 1, 3, 5, 7. So you can see we've now rolled by 2 digits instead of rolling the 1 setup. We now rolled 2 digits up there. And so if we go back and we do the 1, so we've rolled it up, 0, 1, 4, 5. And then we're going to take the 2 in there. And we've rolled the 0, 1, 2, 3, 4, 5, and 6, 7. So we start rolling these things around on here. There's a lot of different things you can do on this. But it's another way to manipulate the numbers on your NumPy. And finally, let's go ahead and swap axes. We'll do C. And let's just go ahead and run that. It's going to give me an error on there. That's because it requires multiple arguments, left out the arguments. So now we can swap them, we get the 0, 2, 1, 3, 4, 6, 5, 7. So you can see everything's been swapped around. So next thing we want to go over is we want to go over NumPy arithmetic operations. How can we take these and use these? Let me just go ahead and put this cell as a markdown. There we go. We'll run that so it has a nice thing. Alright, nice title on there. That's always helpful. And let's start by creating two arrays. We'll do A is an NP range, A range 9. And let's reshape this 3 by 3. So by now you should be seeing this reshape stuff and this should all look pretty familiar. We have our 0, 1, 2, 3, 4, 5, 6, 7, 8 on there. And let's create a second one, B. And this time instead of doing A range, let's do NP array. We'll just create a straight up array. And we'll do an array of 3 objects. So it's going to be 3 by 1. And if we go ahead and print B out, let me run that. This is actually pretty common to have something like this where you have a 3 by whatever it is and a 3 by 3 array. When you're doing your math, you kind of have that kind of setup on there. And what we can do is we can go np.add AB. Don't forget we can always put a print statement on there. So if we add it, you'll see that it just comes in there and it goes, okay, we're adding 10 to everything. And we could actually do something more, make it more interesting. 10, 11, 12. So let's change B's now 10, 11, 12, and let's run that. And you can see that we have 10, and then you had 1 plus 11 is 12, 2 plus 12 is 14, 13, so 10 plus 3 is 13, 11 plus 4 is 15, and 12 plus 5 is 17, and so on. We'll put this back since that's how the original setup was. Let's do 10 by 10 by 10, and run that, and get the original answer. And if you're going to add them together, we need to go ahead and subtract AB. And we run that. We get minus 10, minus 9, minus 8, just like you would expect. So we have our subtraction. 0 minus 10 is minus 10, and so on. And if you're going to add and subtract, you can guess what the next one is. We're going to multiply. And we'll multiply AB. And this should be pretty straightforward. You should expect this. If we multiply 10 times 0, we got 0. 10 times 10 is 10, and so on. And finally, if you're going to multiply, what's the last one we got is divide. What happens when we do divide A by B? And we run this, and we're going to get 0. And this is 0 divided by 10 is 0. 1 divided by 10 is 0.1. 2 divided by 10 is 0.2, and so on and so on. So the math is pretty straightforward. It just makes it very easy to do the whole setup. And again, if we went this, and let's say, let's change this up here. Instead of 10, we do 100. And make this 1,000. There we go. And if we run that, and then we do the add, you can see we got 10 plus 100 plus 1,000. Same thing with the subtract. Same thing with the multiply. And then you can also see the same thing here with the divide. So a lot of control there with your array and your math. Again, let's set this back to 10. Oops, it's right up here, wrong section. There we go, 10. And we'll just go ahead and run these and get back to where we were. And this brings us to our next section, which is slicing. And let's put in our, we'll just make this a cell type markdown. And then we run that. Of course, it gives us a nice looking slicing there. And slicing means we're just going to take sections of the array. So let's create an array NP A range. Let's just do 20. And if you remember, if we do A, we have a 0 to 19. And then we can do A, and remember we can always print these. This can always be put in a print, but because I'm in Jupyter, if you're doing a demo in Jupyter, it's just so great that you have all these controls on here. So we can slice 4 on, and this should look familiar because this is the same as a Python and a lot of other different scripting languages. If we do 4, it goes 0, 1, 2, 3, that's the first 4 in the thing, and it skips some and starts with this one. The first 4 are skipped, and then from there on. You can also do the opposite and go till the 4th one. If we run that, we get 0, 1, 2, 3. Quite the opposite on there. We can do a single item, so we can pick object number 5 on the list, run that, And 5 happens to be 5 because that's the order they're in. And then this one's interesting because I can do s equals slice. And let's create a slice here. And let's do 2, 9, let's leave a 2 on there. So we'll create an s slice on here. And then if we take our array and we do array of s, we're taking our slice in there, and let's go ahead and run that. And let's take a look and see what it generated here. First off, we started with 2, so we have 2 at the beginning. We're going to end at 9, which happens to be 8, so it stops before the 9. Remember when we're doing arrays in Python. And then we step 2, so 2, 4, 6, 8. We could do this as 3. Let me run that, and you can see how that changes, 2, 5, 8. And we could do this as, let's leave this at 3, and if we change this to 10, oops, let's make it 12, there we go. And we run that, we have 2, 5, 8, 11. So that's pretty straightforward, but it's a very nice feature to have on here where you can slice it and take different parts of the series right out of the middle. So now that we've accessed the different pieces of our array, let's get into iteration. And this is interesting because my sister, who runs a college data science division, the first question she asks is, how do you go through data? And she's asking, do you know how to iterate through data? Do you know how to do a basic for loop? Do you know how to go through each piece of the data? And in NumPy, they have some cool controls for that. So put this in as a markdown. There we go, and run it. And it's called the ND-iter. I'm not sure what the ND stands for, but ND-iter for iterator. So before we do that, though, let's create an array or something we can actually iterate through. We'll call it a equals np a range. Let's do something a little funny here, or funky. And we'll do 0, 45, 5. I'm not sure why the guys in the back picked this particular one, but it's kind of a fun one. And if I run that, we do this, you can see we get 0, 5, 10, 15, 20, 25, 30, 35, 40. That's what this array looks like. And that's just from our slice. This is just a slice. That's all that is we created a slice of 0 to 45, step 5. And so we can do with this, we can also do a equals reshape. Let's go ahead and take and reshape this. And since there's 9 variables in there, we'll do a reshape at 3 by 3. So if we run that, whoops, missed something there. That is the A. That really helps. So if we do the A reshape, and we'll go ahead and print that out. We get 0, 5, 10, 15, 20, 25, 30, 35, 40. And then we simply do 4xn, our NumPy ND-iter of A, colon, and we'll just go ahead and print x. And let's see what happens here when we run through this and we print each one of those. It goes all the way through the whole array, so it's the same thing we just saw before. We got 0, 5, 10, 15, 20, 25, 30, 35, 40. So it prints out each object in the array, so you can go through and view each one of these. And certainly if you remember, you could also flatten the array and just do for A and that also and get the same result. There's a lot of ways to do this, but this is the proper way with the ND iterator because it'll minimize the amount of resources needed to go through each of the different objects in the NumPy array. And hopefully you asked this question when I just did that. And the question is, how can I change this instead of doing each object? So first of all, let's go ahead and take my cell type, and we're going to mark that down and run it. And so we're going to work on iteration order C style and F style. Remember C because it came from the C programming, and F because it came from the old Fortran programming. So let's give us a reminder. We'll do a print A, and we'll do 4xn np iterate A. But we also want to do this in a specific order. And you know what? I'm a really lazy typer, so let's go back up here. This is the ND iterator. I knew I was missing the ND part of A. And let's do order equals C. We'll print X on there. And let's do that again. And this time order equals F. There we go, order equals F. And let's go ahead and run this and see what happens here. And the first thing you're going to notice, our original array, 0, 5, 10, 15, 20, 25, 30, 35, 40. When we do order C, that's the default. 0, 5, 10, 15, 20, and so on. And then when you come down here, you'll see F, order F, is 0, 15, 30. So it takes the first digit of each of the subarrays, or the second dimension, and then it goes into the second one, 5, 20, 35, 10, 25, 40. So slightly different order for iterating through it if you need to do that. So we've covered reshaping, we've covered math, we've covered iteration, we've covered a number of things. The next section we want to go ahead and go over is going to be joining arrays. So we need to bring them together. Let me go ahead and take the cell and make it a markdown. Cell type markdown. There we go. And run that. So let's work on joining arrays so we can bring them together and what different options we have. And let's do, we'll do an NP array 1, 2, 3, 4. We'll go ahead and print. Let's do, oops, first. These arrays aren't that big, so let's just go ahead and keep it all on one line, A. So if we run this, first array 1, 2, 3, 4. Whoops, I forgot that it automatically wraps it when you do it this way. So we'll go ahead and keep it separate and print A. There we go. And let's go ahead and do a B. And we'll do 5, 6, 7, 8. And notice I'm keeping the same shape on these two arrays. Depending on what you're doing, those shapes have to match. And let's go ahead and print second array. Do a print B. We'll go ahead and run that. Oops. Messed something up there. Let me fix that real quick. When I was reformatting it to go on separate lines, I messed that up. There we go, run. All right, so we have first array 1, 2, 3, 4, second array 5, 6, 7, 8. And we'll put a carried return on there. And the key word we use is concatenate. And if you're familiar with Linux, that usually means you're adding it to the end on there. And we're going to do what they call along axis 0. So we have concatenate AB along axis 0. Let's go ahead and run that and see what that looks like. And so we have 1, 2, 3, 4, 5, 6, 7, 8. So now we have an array that is 4 by 2. Has a nice shape of 4 by 2 on here. And if we're going to do it along the axis 0, you should guess what the next one is. We're going to do it along the 1 axis. And let's see how those differ from each other. Let's just go ahead and run that. And again, all we're doing is adding in the axis equals 1. So we have our concatenate, we have AB, and then axis 1. Remember a couple things. One, these are the same shape. So we have a 2 by 2, same dimensions going in there. You're going to get an error if you're concatenating and they're not. If you have something that instead of 1, 2 is 1, 2, 3, 4, 5, 6 with a 5, 6, 7, 8. They'll give you an error on there. In fact, let's take a look and see what happens when we do that. Let me just take this. 1, 2, 3, 3, 4, 5. And let's run that. And if we come down here, oh, we got there. It says all the input array dimensions except for the concatenation axes M must match exactly. So it'll let you know if you mess up. That's always a good thing. Let's go ahead and take this back here, and let's go ahead and run that. And so we have our 0 axes, which is 1, 2, 3, 4, 5, 6, 7, 8. We bring them together. And you'll see a very different setup here when we do it along the axis 1. We end up with, instead of 4 by 2, we end up with a 2 by 4. 1, 2, 5, 6, 3, 4, 7, 8. And that's just changing which axes we're going to go ahead and concatenate on. What I find is when you're talking about the concatenate or the joining arrays, you really got to play with these for a while to make sure you understand what you mean by the axes. It looks very intuitive when you're looking at it. Axis 0, 1, 2, 3, 4, 5, 6, 7, 8. Axis 1 is then splitting it a different way, 1, 2, 5, 6, 3, 4, 7, 8. When you're actually using real data, you start to really get a feel for what this means and what this does. So if we're going to do that, let's go ahead and look at splitting the array. And do that under Markdown and run it. There we go. So you have a nice little title there. And we'll go ahead and create an array of 9. Let's do NP split. We'll do A, and we're going to split it by 3. Let's just see what that looks like. So if we split it, we get an array 0, 1, 2, 3, 4, 5. We get 3 separate arrays on here. Now remember, we're looking at, let me just print A up here. So we're looking at 0, 1, 2, 3, 4, 5, 6, 7, 8, and then we can split it into 3 separate arrays. And let's take this, we're going to do this right down here, I'm just going to move the A split down here. Instead of the 3, let's do 4, 5, and put that in brackets. And so when we do it this way, we have 0, 1, 2, 3, 4, 5, 6, 7, 8. And that's kind of interesting. I wasn't sure what to expect on that, but we get, when you split an A by 4, 5, you get a totally different setup on here as far as the way it split the array. And to understand how this works, I'm going to change the 5 to a 7. And this will visually make this a little bit more clear. So we had 4 and 5, it went 0, 1, 2, 3, 4, 5, 6, 7, 8. And you see the markers 4 and 5. When we do 4 and 7, I get 0, 1, 2, 3, 4, 5, 6, 7, 8. And so what you're looking at here is the first markers, this is going to go to 4. So there's our first split at the 4, the marker at 4, and then the second split is going to be at position 7. And this is the same thing here, 4, position 5. That's why we're splitting it in those two sections. We could also do it 7, just to see what that looks like. Run. And you can see I now have 0, 1, 2, 3, 4, 5, 6, 7, 8. So we can split it in all kinds of different arrays and create a different set of multiple arrays on here and split it all kinds of different ways. And before we get into the graphs and other miscellaneous stuff, let's go ahead and look at resizing the array. We'll go ahead and take this cell and set the cell as a markdown and run it. Give us a nice title there. And we'll do an array, an NP array of 1, 2, 3, and 4, 5, 6 here. And let's go ahead and just print. Let's go print a dot shape. And we'll go ahead and run that. Whoops, hit a wrong button there. Hit the comma instead of the dot. So we have a shape of 2, 3 here. And this is important to note because when we start resizing it, it's going to mess with different aspects of the shape. And so we'll go ahead and do a print. Scoop in for a blank line. There we go. And let's do b equals np dot resize. We're going to resize A, and let's resize it with 3 by 2. And then we'll just go ahead and print B and print B period shape, not a comma. We'll run that. Oops, forgot the quotation marks around the end. We'll go ahead and run that, and let's just see what that looks like. So we have 1, 2, 3, 4, 5, 6, our original array, with a shape of 2, 3. And then we want to go ahead and resize it by 3, 2. And we end up with 1, 2, 3, 4, 5, 6, and we end up with a shape of 3, 2. That shouldn't be too much of a surprise. You know, we got 6 elements in there, we can resize it by 2, 3 was the original one, and then we're actually just reshaping it is how that kind of comes out as when you resize it like that. But what happens if we do something a little different? And let's go ahead and just take this whole thing and copy it down here so we can see what that looks like. And instead of doing 3, 2, remember last time I did the, to reshape it, I messed with the numbers and it gave me an error. Well, when you resize it, you don't have to match the numbers. They don't have to be the same dimensions. So we can, instead of going from a 2, 3 to a 3, 2, we can resize it to a 3, 3. So let's take a look and see how it handles that. And when we come down here to 3, 3, we end up with 1, 2, 3, 4, 5, 6, and it repeats 1, 2, 3. So it actually takes the data and just adds a whole other block in there based on the original data and repeating it. All right, now at this point, we've been looking at tons of numbers and moving stuff around. What we want to go ahead and do is get a little visual here because that certainly you can picture all the different numbers on there, but let's look at histogram. Let's put this into a histogram. Let me go ahead and run that. And to do that, we're going to use the Matplot library. So from Matplot library, we're going to import PyPlot as PLT. And that's usually the notation you see for PyPlot. So if you ever see PLT in a code, it's probably PyPlot in the Matplot library. And then the guys in the back did a nice job, and gals too, guys and gals back there. Our team over at simplilearn put together a nice array for me, 20, 87, 4, 40, 53, with a bunch of numbers. That way we had something to play with. And what we want to do is we want to plot the histogram. Now remember, a histogram says how many times different numbers come in. And then we're going to put them in bins. And we have bins 0 to 20 to 40 to 60 to 80 to 100. You might, in here with the Matplotlib library, they call them bins. You might hear the term buckets, or they put them in buckets. That's a really common term. And then we want to give it a title. So the way it works is you do your plt.hist for histogram, your plt title, and your plt show. And we're doing just a single array in here in the NumPy array of A. And let's go ahead and run this piece of code. Take it a moment to come out there. It says figure size, so it's generating the graph. And you can see we have, and let's just take a look at this. Let me go down a size. There we go. Okay, so now we can see what we're taking a look at here. So between 0 and 20, we have 3 values. So we have a 20 here, we have a 4, and a 11, and a 15. 0, 1, 2, 3. It's actually 4 values, but they start at 0. So remember, we always count from 0 up. And from 20 to 40, we got 20. So it's 1, 42, 3, 4, 5, 6. And so you can see in the histogram, it shows that the most common numbers coming up is going to be between the 40 and 60 range, least common between the 80 and 100. This looks like an age demographics, is what this looks like to me. And you can see where they would have put it in the buckets of different age groups, which would be a nice way of looking at this. Histograms are so important and so powerful when you're doing demos and explaining your data. So being able to quickly put a histogram up that shows what's common and how it's trending is really important. And using that with a NumPy is really easy. And you know what, let's take the same data, and I want to show you why we do bins, or why we have buckets of data. I'm used to calling it buckets. Why we have bins. Let's do it instead of by 20, let's do it by tens and see what happens. And what happens when you do it by tens is you miss out on you can see a nice curve here on the first one, and on the second one it looks like a ladder going up and a plummet, a ladder going up and a plummet, and a ladder going down. So the first would be more indicative of an age group, and the second one would be what you would get if you divided incorrectly. You wouldn't see the natural trend of, I don't know what this would be, maybe how much food they eat. Hopefully not, because I'm in 50, so I'm right in the middle there, which means I eat a ton of food compared to everybody else. But it's some kind of demographic. Maybe it's mental, maybe it's knowledge, because we hit a certain point and then we start losing, our marbles start leaking out or something. So you start off knowing something, and then as you get older you grow more. But you can see here we lose that. You lose that continuity in the thing if you split the histogram into too many bins or too many buckets. And if you actually plotted this by the individual numbers, it would just be a bunch of dots on the graph and wouldn't mean a whole lot. And we've looked at graphs. There turns out are a ton of useful functions in NumPy. I'm sure there's even new ones that aren't going to be in here. But let's just cover some important ones you really need to know about if you're using the NumPy framework. One of them is line space function. This is generating data. So you have a line space, we have 1, 3, 10, and when we do that, we end up with 10 numbers. So if you count them, there's 10 numbers. They're between 1 and 3, and they're evenly spaced. We get 1, 1.222. But these are all, there's a total of 10 here, and it's right between the 1 and 3 range. That can be, there's a lot of uses for that, but they're probably more obscure than a lot of the other common NumPy arrays set up. Then a real common one is to do summation. So we'll do summation where you do, in this case we create a NumPy array of two different arrays, 1, 2, 3, or 2 different dimensions, 1, 2, 3, 3, 4, 5. And we're going to sum them up under axes 0, which is your columns. And if you remember correctly, columns is the 1 plus 3, 2 plus 4, 3 plus 5, so we have 3 columns. And if we change this, we'll just flip this to 1. We get 2 numbers. So we get 1, 2, 3 all added together, which equals 6, and 3 plus 4 plus 5, which equals 12. We'll set this back to 0. There we go, since we're looking at axis 0. And these probably could have been, some of these could have been with our math section. Square root and standard deviation, two very important tools we use throughout the machine learning process and data science. And simply we take the NP array, we have again the 1, 2, 3, 4, 5, 6, 3, 4, 5. I don't know why I need to keep recreating it, probably could have just kept it. But we can take the square root of A. So it goes through and it takes the square root of all the different terms in A. And we can also take the standard deviation, how much they deviate in value on there. And there's a rabble function. We can run that. And NP array is x. We're going to do x equals, hey, we changed it from A to x. X equals rabble. And this sets it up as columns. So we have 1, 2, 3, 4, 5. This is all columns on here. Very similar to the flatten function. So they kind of look almost identical. But we also have the option of doing a rabble by column. And then another one is log. So you can do mathematical log on your array. In this case, we have 1, 2, 3. And we'll find the log base 10 for each of those three numbers. And there's a couple of them. You can't just do any number here after log, but there is also log base 2. Log base 10 is pretty commonly used on here. We'll go ahead and run that. There we go. Before we go, let's have a little fun. Let's do a little practice session here on some more challenging questions. So you start to think how this stuff fits together. Right now we just looked at all the basics and all the basic tools you have. So let's do some NumPy practice examples. And let's start by figuring out how do you plot, say, a sine wave in NumPy. What would that look like? And so in this project we wouldn't have to do this because I've already run these. But we'd want to go ahead and import our NumPy as NP and import our Matplot library PyPlot as PLT. So we get our tools going here. And then we'll break it into two sections because we need our x, y coordinates in here. So first off, let's create our x coordinates. And our x coordinates we're going to set to an A range. And we want this A range, since we're doing sine and cosine, it's going to be between 0 and 0.1. And then we use our NP, and we actually can look up NumPy stores pi. So you have the option of just pulling pi in there directly from NumPy. It has a few other variables that it stores in there that you can pull from there. But we have NumPy pi. And we generate a nice range here. And let's go ahead and run this. And just out of curiosity, let's see what x looks like. I always like to do that. So we have 0.1, 0.2, 0.3, 0.4. So we're going 0 to, in this case, 9.4, 3 times NumPy pi. Remember, pi is like 3 point something, something, something. So that makes sense. It should be about 9. And we're doing intervals of 0.1. So we create a nice range of data. And then we need to create our y variable. And so y is going to simply equal, and then once we have our x and y, and if we print, let's go ahead and just print y. See how that, we'll do this, let's do this so it looks print x, print y. So we basically have two arrays of data. So we have like our x-axis and our y-axis going on there. And this is simply a plt.plot. Because we're going to plot the points, and we'll do x comma y, and then we want to actually see the graph, so we'll do plot.show, and we'll go ahead and run that. And you see we get a nice sine wave, and here's our numbers 0 through 9, and here's our sine value, which oscillates between -1 and 1 like we'd expect it to. Then for the next challenge, let's create a 6x6 two-dimensional array and let 1 and 0 be placed alternatively across the diagonals. Oh, that's a little confusing. So let's think about that. We're going to create a 6x6 two-dimensional, so the shape is 6x6 two-dimensional array, and let 1 and 0 be placed alternatively across the diagonals. Now, if you remember from lesson 1, we can fill a whole NumPy array with zeros or ones or whatever. So we're going to do NP, create a NumPy zeros, and we're going to do a 6x6, and we'll go ahead and make sure it knows it's an integer, even though it's usually the default. And just real quick, let's take a look and see what that looks like. So if I run this, you can see I get 6x6 grid, so 6x6, 0, 0, 0, 0, 0. Now, if I understand this correctly, when they say 1s and 0 placed alternatively across the diagonals, they want the center diagonal, maybe that's going to stay 0 all the way down. And then the next diagonal will be 1s all the way across diagonally, and then the next one zeros, the next one ones, and the next one zeros, and so on. Hopefully you can see my mouse lit up there and highlighting it. So let's take a little piece of code here, and we'll do z1::2, ::2 equals 1. And wow, that's a mouthful right there. So let's go ahead and run this and see what that's doing. And so what we're doing is we're saying, hey, let's look at, in this case, row 1. There's 1. And then we're going to go every other row 2, so we're going to skip a row. So skip here, skip here, skip here. So we're going down this way, and we're going every other row going this way. It's hard to highlight columns. So you can see right here where we're not touching each row, like this row right here is not being touched. Okay, so we're going to start with row 1, and then we're going to skip a row and another one, and so we're going every 2 rows. And then in every 2 rows, we're looking at every 2, starting with the beginning. That's what this thing blank means. So we're going to start with the beginning, and we're going to look at all of them, but we're going to skip every 2. So starting with row 1, we look at all the rows, but we do it by 2 steps. So we go 1, skip 1, 1, skip 1, 1, skip 1, 1. If you left this out, it'd do every 1. This would just be 1s. In fact, let's see what this looks like. If I go like this and run it, you can see that I just get 1s. So this notation allows us to go down each row, row by row, and we're going to do every other row set up on there. And so if we're going to start with row 1, we also, Control Z, try that. There we go. We'll start with row 0. Again, we're going to go each row, step 2. So we'll start with row 0, and we'll go every other row. And this time we'll start with 1, column 1. And again, we go every other one going down. That's what that step 2 is. That's skipping every other one. We're going to set that equal to 1. So let's see what that looks like. And you can see here we get our answer. We get 0, 1, 0, 0. But it has the 1s going in diagonals on every other diagonal and 0 on every other one. A little bit of a brain teaser, that one, trying to get that one to work out. So you can see how you can arrange your rows, and here's your step and your different access on there. And then the next one is find the total number and locations of missing values in the array. The first challenge is to create some missing numbers. So let's create our array Z. We're going to do numpy.random.rand 10, 10. And before we do the second part, let me just take this second part out. And let's just see what that looks like. So let's run that. And there we go. So we have a 10 by 10 random array. It randomly is picking out numbers. And next, we want to go ahead and take our random integer size equals 5. And then we're going to do a random 10 size equals 5. So in the Z, we're going to select a number of random spaces here and set them equal to null value. And let's go ahead and run that so you can see what that looks like. And if we look at the array, we've created 1, 2, 3, 4. There should be a 5th one in here. My eyes may be failing me. So we've created a series of, because 0 to 5, 0, 1, 2, 3, 4. So we got 5, there are different null values on here. And this is kind of a neat notation to notice that we can generate random integers, size equals 5. So this generates 5 by 5 miniature grid inside of this to tell it where to put the nands at. So that's kind of a cool little thing you can do. And then we want to look up and see how many null values are in there. And this is simply just np is nan of z. Simple. So if it is nan, then we want to sum it up. So we're going to sum up all of the different null values on there. Now let's do one more feature in here, which is really cool. Let's go ahead and print the indexes. So np argware np is nan of z. So we're going to create our own another np array. And let's run this, and we'll see here that it comes up with the 4 indexes. So we did count 4 of them up there. It tells you where they are, 1, 9, 2, 0, 4, 6, 5, 4. And then let's go ahead and run this again. Run, there we go. This time I got 5. That's what we get for random numbers. Another fun one that I always like to do, it's very similar because we have np is nanz.sum, so we're summing the number of nans, and we can get the indexes and you can reshape the indexes, but you can also just do, we'll do an INDS where np is nan of z, and let's just print, that, print INDS. Let's see what that looks like. And it's very similar. We have 01306388693, but I've split it into two different arrays. So we have our x and our y kind of coordinates going there. And what I can now do is I can now do z INDS equals, and at this point you can also, instead of getting the sum, you can get the means or the all the numbers and that kind of thing, or the average as it is. So that'd be one thing you could do, and you can pick out the average. That's very common in data science, to get the average and just use that for a value. But we'll go ahead and just set it to 0, and then let's go ahead and print our z and run that. And you can see when we come down here, we have wherever there was a null value, it is now 0. And you can set this to whatever you want. This is another way to replace data or help clean data up, depending on what it is you're doing. So, wow, we covered a lot of stuff. So quick rehash going over everything. We went into there, we looked at array manipulation, changing the shape, how to switch that around. We even had the flatten down there, which remember we have another command lower that's similar. We could change the order by F. Remember, F stands for Fortran, very strange connotation, but there's C and F. C is the standard, and F switches it to a different order. To be honest, I usually have to look it up because I almost never use F, but when you need it, you're like, oh my gosh, what was the other order? Just do a quick Google. So we talked about reshape, making sure that the dimensions are the same. You don't want to have like something that has 12 objects in it and reshape it to 11 and 5 because it doesn't work. It doesn't divide into 12. We can transpose, so we can switch them. So we can go from a 4x3 to a 3x4. Oops, I did that the other way around. 3x4 to 4x3. We covered reshaping the array. We did the roll the axes. You can do some weird things with swapping and rolling axes and transposing the numbers. We dug a little bit into the arithmetic. So we talked about adding, we talked about subtracting, multiplying, dividing. And at this point it's so important we just look up the NumPy mathematics. And you can see here they have just about everything. Your trigonometry, your hyperbolic functions, rounding, sums, products, differences. There are so many, all your different miscellaneous mathematical connotations. So, Google it, go to the main NumPy page and look at the different setups you can do on there. So we covered that, and we did slicing, how to break it apart. We did iterating over the array. We covered joining arrays and how to concatenate. Remember, concatenate just means add on to it. So in this case, how are you adding B onto A is how you'd read that. From Linux, you should catch the concatenate because that's used regularly there. Splitting the array, we talked about how to split the array in different ways. So you can split it in array of arrays, all kinds of different ways to split the array up. How to resize it. And remember, resize does not have to have the same shape, but if you resize it, it will take the data and begin at the beginning and add new rows on if the size is bigger. If it's smaller, it truncates it. It just cuts the end off. We looked at how to do a histogram and how to plot that. We mentioned buckets or bins, as they call them in PyPlot. And then we covered a lot of other useful functions in NumPy. We talked about the line space setup for doing numbers in a series. How to sum the axes up. Again, that's part of the mathematical formulas there that we looked at. There's a sum, there's also means and median. All of those you can compute in NumPy. And you can also do the square root and standard deviation. The ravel function, very similar to the flatten. To be honest, I almost always just use the flatten, but the ravel has its own kind of functionality that it does. And then we went into some NumPy practice examples. We challenged you to create a sine wave in NumPy and how to do that. We're kind of looking for that A range. Remember how we do the A range, and you can have your beginning value, your end value, which they did as 3 times pi, NumPy pi, and we're going to do intervals of 0.1. and then y just equals the NumPy sine of x. There's our math from the math page we were just looking at. Remember that? It's right at the top. And finally we went down here. We had this kind of a little brain teaser, how to do diagonal zeros and ones, playing with the different connotations of the NumPy array. And then we did a random size, and we played a little bit with with the null values, playing with null values. If you're doing any data science, you know null values are like a headache. What do you do with them? Big sets of data, you get rid of them. Small sets of data, you have to factor something in there, like figure out the average or the median there, and then replace it with that.
We'll be discussing one of the most important and frequently employed libraries in data science, the Matplotlib. Matplotlib is a math and graphical extension to NumPy. Without any further ado, let's get started.
Today we're going to study the Matplotlib library and the Python code. So what's in it for you? What is Matplotlib library? Types of plots, plotting graphs and subgraphs, adding a graph inside a graph, graph parameters, title, label, legend, line graphs, line types, color and transparency, canvas, grid and axis range, 2D plots, scatter, step, bar, fill between, radar chart, histogram, contour image, 3D surface image, and then we'll hit a practice example, PyCharm. So let's start with what is Matplotlib library. Matplotlib library is an open source drawing library which supports rich drawing types. It is used to draw 2D and 3D graphics. And there are so many packages in the Matplotlib library, we're going to cover the basics. And there are so many packages that sit on top of the Matplotlib library that we can't even cover them all today. But we'll hit the main ones so that you have a good understanding of what the Matplotlib library is and what the basics can do. You can understand your data easily by visualizing it with the help of Matplotlib library. You can generate plots, histograms, bar charts, and many other charts with just a few lines of code. And here we have some basic types of plots that you can see here that we'll go into. We have the bar chart, the histogram. Boy, I use a lot of histograms in my stuff. A scatter plot, line chart, pie chart, and area graph. Let's start plotting them. And to do this, I'm going to be using Jupyter Notebook. You can use any of your Python interfaces for programming or scripting and running it. Of course, we here really like the Jupyter Notebook for doing a lot of basic stuff because it's so visual. And in our Jupyter Notebook, which opens up in this case, I'm using Google Chrome, you can go up here to New, and we'll create a new Python 3 and set that up. If you're not familiar with Jupyter Notebook, we do have a tutorial that covers some of the basics of that. And you'll look at any of our tutorials, I usually cover a number of them showing how to set up Jupyter and Anaconda. I myself use Jupyter through Anaconda. In fact, let's go ahead and open that up and just take a look at that, see what that looks like. You can see your Anaconda navigator. If you install it, it will automatically install the Jupyter Notebook. And that also installs a lot of other things. I know some people like the Qt console for doing Python or Spider. I've never used them. I actually use Notepad++ as one of my editors. And then I use the Jupyter Notebook a lot because it's so easy to have a visual while I'm programming. And even simple script in Python, I'll take it from the Jupyter Notebook and then do a save as. You can always go under File, and you can download as a Python program. So that'll download it as an actual Python versus the IPython that this saves it as. So let's go ahead and dive in and see what we got going here. And let's go ahead and put Matplotlib library tutorial. And I'm going to turn this cell into a markdown so it doesn't actually run it. You can see it has a nice little title there. That's all Jupyter Notebook. And then from Matplotlib library, let's import PyLab. Back one. And then let's go ahead and just print. We'll go PyLab and the version. Let's go ahead and run this. So we're going to import our PyLab module from the Matplotlib library. And we find out that we're in version 1.15.1. Always important to note the version you're in. Probably I was reading an article that said the number one thing that Python programmers struggle with is remembering what version they're working in and making sure that they're going from one platform to the other with the same version. And if we're going to graph things, I think we need some data to graph. So we're going to import NumPy as NP. Now, if you're not familiar with NumPy, definitely go back and check out our NumPy tutorial. There's so many different things you can do with it, dealing with reshaping the data and creating the data. We're just going to use it to create some data for us. And there is a lot of ways to create data, but we're going to use the np.linespace. So we're going to create a NumPy array, and the way you read this, is we're going to create numbers between 0 and 10, and we're going to create 25 of these numbers. So we're just going to divide that equally up between 0 and 10. And if we have x coordinates, we should probably have some y coordinates. And we'll do something simple like x times x plus 2. And let's just take a look. We're going to print x and print y. Let me go ahead and run this. And let's see what we got going on here. So we have our x coordinates, which is 0, 0.4, 0.83, etc. And you can look at this as an xy plot. So where we have 0, we have 2. Where we have 0.416, we have 2.17. And just as a quick reminder, we're going to do print np-array x, y dot reshape 25, 2. And the reason I want to do this is I want to show you something here. A lot of times a program returns x, y, and it's an array of x, y, x, y, x, y. And so when you're working with the pyplot, you have to separate it out and reshape it. So if I start off with pairs like this, I can reshape them. If I know there's 25 pairs in there, I can switch the 2 and the 25. And this is kind of goofy, but we'll do it anyways. Reshape. So I'm going to reshape my 25 by 2 back to 2 by 25. And if I run that, you'll see I end up with the same output as the xy, the two different arrays in here. And this is important that we want x and y separate. Again, that's all NumPy stuff, but it's important to understand that this is a format that Matplotlib works with. It works with an array of x's, and they should match your array of y's. So each one has 25 different entities in it. And then for our basic plotting of this data, it only takes one command to draw a graph of this data. And so we use our, from up here where we imported PyLab, we take our PyLab, and the key under there is plot for plotting a line. And then we want our x coordinates and our y coordinates. And we'll throw in R. And the R simply means red. So we're going to draw the line in red. Let me go ahead and run that. You can actually switch this around if you wanted to do different. There's B for blue. We have a lot of fun. Yellow. Hard to see yellow. There we go. But we'll go ahead and stick with red. Run. And when you're doing presentations with these, try to be consistent. You know, if the business and the shareholders send you a spreadsheet and they have losses in red, use red for losses in your graph. Try to be consistent. Use green for profit, for money. You don't have to necessarily use green, but it's whatever they're using, whatever the company's using. Try to mirror that. That way, people aren't going to be confused if you switch your data around and every time one graph has red for loss and one graph has blue for loss. It gets really confusing, so make sure you're consistent in your graphs and your coloring. And something to know, because we're going to cover this in a minute, this is your canvas size. So we have a canvas here, and what we're going to do next is we're going to look at subgraphs. Okay? So let's take our PyLab and create a subplot. And one of the things also to know when we're working with the Matplotlib library, I'm not setting, when I do this, this is my drawing canvas, the PyLab. So once I've imported the PyLab, I'm drawing my images on there. Very important to know. And with the subplot, we're going to give it some different values. And we're going to represent by rows, columns, and indexes. And let's do 1, 2, 1. So it's going to be the first row, second column, and the index is like you can stack your graphs and things like that. We don't worry too much about indexes, but rows and columns. We want to go ahead and use row 1 and column 2. And if we're going to have one object, we should probably have two, but before we do that, we have to plot data onto the subplot. So the order is very important, and we'll go ahead and stick with our x, y, and let's do this. We're going to add in a third parameter here. Remember we did red? We're going to add shorthand dash dash for dashed lines. So this plots the data into row 1, column 2. And if we're going to do that, let's do another one, pylab.subplot. And if we're going to do row 1, let's do column 2 and index 2. And this time we're going to add G for green, and this denotes a style. And if we're going to set up our PyLab subplot, there we go, PyLab, we got to go ahead and plot that. PyLab plot. And instead of XY, we want Y, X. Whoops, I messed up. This is in the wrong spot. There we go. We'll move that down here real quick because that goes in the plot part. So the subplot tells it the row, column, and index, and the pyplot tells it what data. In this case, we switch them. and the color, and then the style shorthand. Now let's go ahead and run that. And you'll see it takes this canvas, splits it in two, and now we have two different graphs. And we have the red one with dashed lines, and we have the green one, which has the little stars going up. And if we take this, and let's just for fun, let's change this and run that with an index of 1. It puts them both on the same index. It also gives me a warning because it's a strange way of doing two subplots. It's depreciated. There's another way to do it. But most people just ignore that warning because it's not going to go away anytime soon. Now that's using the same setup. What happens if we do, instead of this, let's change the column on here and find out what happens. And if we do the column, it didn't really like that on the setup. It just disappears. So let's keep our column as 2, and let's change the row on the second one to 2 and run that. And you'll see again it kind of squishes everything together. It can cause some issues. So let's take the index. So they each need a unique index. And you can see here where I've made some changes. I said row 2, and look what happens when I change to column 2. So I now have row 2, column 2, index 2. It squished it up here, so you could put another graph underneath is what that does. And there's all kinds of different things. You really have to just play with these numbers till you get a handle on them, because you have to repeat it 164 times according to Cambridge University if it's completely new to you. And you can see right here where, here we go, 3, run. There we go. But you can see it takes a little bit sometimes to play with these and get the numbers right. Oops, I hit the wrong one, that's why. Let's go 3 there, run. There we go. Now it's overlapping, so I have this doubled over here on the right. For now, we'll just go ahead and leave this with the where we have column and row 2 and the two different indexes so they appear nice and neatly side by side. And then, as we just saw, as we were flashing through them, we can put them on top of each other. And let me just highlight that and copy it down here. Paste it down there. And here we have 1, 2, 1. And then we'll do 1, 2, 1 also for this one. And that puts the two subplots directly on top of each other. It gives us that warning. And you can see we now have two different sets of data graphed on top of each other. And you can also see how it did the indexes. Since one of them is from 0 to 10, that's the green one on the x-axis, and the other one is from 0 to 10 on the y-axis. So it took the greatest value of either one and then used those as a shared value. So let's next look at operator description. And we'll go ahead and turn this cell into a markdown and run that so it looks nice. So Fig, and you remember I talked about the canvas earlier. I briefly mentioned it. We're going to look a little bit more at the canvas later on. But that's what the figure is. Fig, we're going to add axes. So we're going to initialize a subplot, add the subplot, in rows, in columns, and all kinds of different things with this that you can do. Let's look at that code and see exactly what's going on. And I want you to notice that there's Fig, which is the actual canvas in the Matplotlib library. And AX is commonly used to refer to the subplots. So when we're creating subplots, you'll see AX equals PLT subplot. Earlier, we did the PyLab. So let's go ahead and import PyPlot from Matplotlib library. And we're going to do it as PLT. You'll see that a lot. That's really the standard in the industry, is to call it PLT, just like Pandas is PD and NumPy array is NP. Certainly you can import it as whatever you want, but I would stick to the standards. And we're going to do the same graph as we did above with the PyLab, but with the PLT. So if it looks familiar, there's a reason we're doing this, because we want to show you how the figure part works and working with the canvas goes. But we're going to do the same plot as we did before. And we'll call it Fig, and we're going to set that equal to plot figure. So there's our figure or our canvas on there. And let's create a variable called axes, and we're going to set that equal to fig.add axes. And in this, we're going to control the left, right, the width, the height of the canvas from 0 to 1. And so we can go ahead and I'm just going to put some stuff in there. I got 0.5, 0.1, 0.8, 0.8. So when you're looking at this is a 0 to 1, or you could say 50%, 10%, 80, 80%. But it's a control. It's going to control your left and your right, along with the width and the height. So the width and the height, we're going to use 80%, and we're going to have like a little indent on the left and the right. And this should look familiar from above, axes.plot, x comma y, and then let's give it a color. How about red? Since we're recreating the same graph, let's keep it uniform. Oops, and it helps if I use AXIS instead of AXES. I don't know where that came from. But this looks identical to the one we had up above. So here's our axes plot, x comma y of red. Same graph, same setup, but this time we've added a variable equal to the figure.addAxes. So our plot figure is our canvas, our axes is what we're working in, and then our axes.plot x comma y. And again, we can draw subgraphs. We put that down here. Just like we did before. And a little different notation here. We're going to have fig comma axes equal plt.subplots. And in here it's going to be the number of rows. We're going to do one row and columns equals 2. So if you remember before, that's what we did. We had one row with 2 different graphs on it. We're going to do the same thing, but note how we did this. Here's our figure, or our canvas, and our axes. We're going to create actually 2 different axes. We're going to create row 1, column 2. And so axes is an array of information. So we can simply do let's do ax in axes. And this will now look familiar, x.plot. We're going to do x comma y. We'll go ahead and make it red. Keep everything looking the same. Remember, nice uniform graphs, everything looks the same. And if we go ahead and run this, you'll see we get 2 nice side-by-side graphs. So just as we had before, the same look, the same setup. And just for fun, let's change in columns to 3. We'll run that. And now you'll see we'll have 3 on there. And let's see if we make it a little bit more interesting. We'll do in rows equals to 2. And you can see down here we're going to get an attribute error because it's trying to scrunch everything together. So it does have a limit how much stuff it can put in one small space. That's important to know. You can fix that by changing the canvas size, which we'll look at in just a minute. And there's other ways to change it on here. But here we go. We can do in rows 2 and columns equals 1. You can see 2 nice images right above each other. We'll go back to the original. 1 row, 2 columns, side by side, left to right. And we can also draw a picture or graph inside another graph. And that's kind of a fun thing to do. It's important to note that we can layer our stuff on top of each other, which makes for a really nice presentation. So let's start by fig. We'll create another figure. So we're going to start over again with our canvas. We set that equal to plt.figure. So there's our new canvas. And let's do axes. We'll call it axes 1 and 2. Axes 1 equals fig.addAxes. Remember this from earlier? And this here, similar numbers we used before, saying how big this axis is, this figure in the axes is. So this is going to be the big axes. And let's do axes 2 equals another figure add axes, and then 0.2, 0.5, 0.4, 0.3. And if we're going to do this, they need data on them. So let's go ahead and plot some data on our axes. So axes1.plot. And we'll make this simply x comma y comma, make it red. And then let's go axes2.plot. And let's reverse them. Y comma x comma green. There we go. Doing what I told you not to do. You shouldn't be swapping axes around and plotting your data in 5 different directions because it's confusing. But let's go ahead and run this and see what this looks like. And then let's talk a little bit about this. We talked about the 0.2, 0.5, 0.4, 0.3. And let me just grab the annotation for that. That's left, right, width, and height. So we have in here that this is going to be left, right. So here's our left is 0.1 in, 0.5. And you know what? Let's just play with this a little bit. What happens when I change this to 0.1? Moves it way over to the left. So there's our 0.1. So we can make this 0.4. Run that. There we go. So you can see how you can move it around the branches on here. 0.2. 0.5 is the left, so that's our right. So let's see what happens when we do let's make this 0.1. And that actually is, they had it down as left, right. I thought this was wrong. It's actually how far from the bottom. Let me switch that on here. Bottom. There we go. So we had here on this. We can go ahead and put that back to 0.5 and run that. And this is 0.3. Let's make this 0.3 also. And that is the width. And then, of course, there's the height. We can make that really tiny. Actually, let's do 0.2. And let's run that. And you can see it changes the height on there. We can make it even smaller, 0.2 by 0.2. And as you can see, you can get stuck playing with this to make it look just right. It can sometimes take a little bit. Certainly, once you have the settings, if you're doing a presentation, you try to keep it uniform, unless it doesn't make sense for the graph you're working on. Try to keep the same colors, the same position, and the same look and feel. And I mentioned earlier we can adjust the canvas size. So this is from earlier. I just copied it down below. We're going to replot the same data we've been looking at. And what we can do is we can change the figure size to 16 by 9. And let me run that and show you what that looks like. So it fills the whole screen. And then if you are, normally when you're working on the screen, you don't worry too much about this. But we can set the DPI to 300. Run that. There it goes. This is your dots per inch. And if you are doing an output of this and you're printing a hard copy, you want the higher quality. I would suggest nothing under 300 if it's a professional print. You might get a little less than that, but whenever I'm doing professional graphics and printing them out on something, 300 dots per inch is kind of the minimal on there. You can go a lot higher too, but keep in mind the higher you get, the more memory it takes and the more lag time and the more resources you use. So usually 300 is a good solid number to use in your dots per inch. And you can see it draws a nice large canvas here, which is 16 by 9, and then the DPI is 300 on here, so it's a little higher quality. And just out of curiosity, I wonder how long it takes to draw something double that size, 600. And you can see here where at 600 DPI, it's going to take a while. There it goes, just because it's utilizing a lot more graphics on there. And let me just go back to the 300. Now let's do a 100. You're not going to see a difference on this because it is web-based graphics are pretty low. And up here you saw I did this with the plot figure. This works the same if I do figure axes subplot, figure size, and then we'll go ahead and do axes plot x comma y comma, we'll stick to red. Let's go ahead and run this. And you should get almost the same thing here. Here's our axes on the subplot on here with the fixed size and the DPI. Let me take this all out. Let me just remove all that real quick. Run it again. There we go. Now we're back to our original figure. And let's look at some of the other things you can do with this. One of the things we can do is we can set a title for the axes. So axes set title. You'll see right here, since I put this on the axes, it's the main title for the whole graph. And if you're going to have a title, you should also label. So we can label our X label, and we can set our Y label. In this case, we're just going to call it X and Y. Keep it nice and uniform, and if we run this, you'll see that we've added a nice X label and Y label. Whoops, where'd they go? And it turns out in this environment that you have to put it before the title. So let me go ahead and put it before the title. And there's our X, Y, and let me run that. And of course, we can also do up our size a little bit so you can see what's going on a little better. So here we have X label X. If you come down here, you'll see our X label and our Y label. We can, of course, change this to X label. You can change this to Y. It can be whatever you want on here, of course. And our title graph. There we go. Run. So here we have our title graph, our Y label, and our X label all set up on our nice little plot. And then before we move on to the next section, let's do one more thing on here. We have a thing called the legend. And we're going to set our AX legend, label 1, label 2 up here. That's the format for it, but let's go down here and actually use it. I'm going to do two different plots. We're going to have axes plot x by x times x squared and x cubed. And if I run this, you'll see it puts two nice graphs on the setup on there. But it's nice to have a legend telling you what's going on. So for the legend, we can actually do axes, since we have the two plots, legend. And on here, we've created an array, and we have y equals x squared, y equals x cubed. You can actually put this as whatever you want. Those are just strings. And then location 2. And let's go ahead and run this and see what that looks like. And you can see it puts a nice legend on the upper left-hand corner. Location 2. We can do location 3. And run it, and it drops it down to the bottom. Location 1, I can't remember where that's at. There we go, upper right. So each one of these is a number that refers to the different locations on the screen. 0, kind of have to play with them or look them up to remember where they're at, but they do work. It just kind of moves around depending on where you want your legend at on there. So on this section we cover the title of the graph, the Y labels, and legends. We're getting into starting to look really fancy here. So we now have something we can actually put out. You'll see the title of the graph looks a little fuzzy. So I might, in a web setup, put the DPI up a couple notches. Maybe put it at 200. 100 might work fine. Just so, that's something to notice on here when you're playing with these different things. We had our subplots DPI equals, let's do 200 and just see what that looks like. So you can see it now is a lot clearer. It's also larger. So it's a nice little feature you can throw in there with your DPI dots per inch. So the next section is let's look at some graph features. We're going to look at line color, transparency, size, and a few more things on here. And, oops, I forgot the main title. So we have our figure and our axes equals our plot and subplots. And I'm going to go ahead and do a DPI equals 150 so the graph comes out nice and large and easy for you to see. And let's go ahead and do 3 plots on here. We'll do x by x plus 1, so it's just going to be a straight line. Plot x plus 2 and axes dot plot x plus 3. This looks like we're doing nearest neighbor setup or showing how it located data and putting your lines on there between the nearest neighbors. There we go. So it draws a nice little graph with 3 lines on it. One of the things we can do is we can control the alpha on this. Oops, and you can actually see the when they did these lines, it automatically pulls in different colors for your setup. So there's some automatic things going on in there. And a lot of times we do that comma R, where we're going to do color equals red, another notation on here. Let's go ahead and run this. Now we have a bright red line down there. And with the Matplotlib library, you're not limited to red. You can also use one of the many different color references, as you see here, with the # 1155DD, which is just blue. And we can do the same thing with another color on here, which turns out to be green. And I can just as easily do this. Green, blue, oops, there we go, blue, and run that. And you'll see here we have red, blue, and green. And what I want to do is I want to make this, we're going to set what's called the alpha on this. And we're going to set this equal to 0.5. So this is halfway see-through when I run this. And it's almost going to look pink because you can see through it. And let's change this just a little bit, just to make this kind of fun. Let's square it. There we go, run it. So now we have this nice square that comes up. And you can see when it crosses it, because I plotted these 2 lines after it and they have no alpha, the red is behind those lines, or in this case pink, because we did the alpha halfway through. So let's go ahead and do this. Alpha equals 0.5. And, oh, you know what? Instead of squaring it, let's take it to the 0.5 power. That'll be kind of interesting to see what that does. We'll just go to keep it squared. There we go. And run that. And let's go back and look at this where it crosses over. And the first thing you'll see right here is on the blue, it's kind of light blue now. You can see how the 2 colors add together. You get almost a purple on there. So I can clearly see where the red crosses the blue line. And then the green just blanks it over because I didn't do any opaqueness, no alpha on there. So this is great if you have lots of data that crosses over and you need to be able to track those lines better. And we'll go ahead and do this 0.5 and we'll run that. Oops, I did equals 0.5. Let me go ahead and run that. And so you can see right here, now you can easily see the red line, how it crosses the green and the blue down here. And if we want to, we can do this as the default is 1, is solid. So we can change this all to 0.8. Let me just do that. Oops, 58, 8. There we go. Run. Oops, I must have hit a wrong button there. Let me try that again. I accidentally got rid of a bracket. And let's go ahead and run that. And we come down here and look at this. You can still see where it passes behind them, but the green dominates and the blue dominates because we're now at 80% instead of 50%. And you can do less. That's kind of fun, although at some point the lanes kind of fade. So 0.5 is usually the best setting on there. We have a nice pastel here at 0.3, and you can easily see where they cross over. And just like you can play with the colors, we can play with line width. And let's try DPI 100 and see what that looks like on my screen. Equals 100. And we'll go ahead and just take our AX plot. Let's do 4 of these lines just so you can see how they look next to each other. Real quick here. There we go. And if I run this, they should all appear the same. It automatically does different colors on there. So let's do color equals blue. Forgot my quotation marks. There we go. And we'll go ahead and just make these all blue, just for purposes of being nice and uniform. And then what I want to do is I want to do the line width. Line width equals 0.25. And let's just copy and paste that down here. Let's do equals 1. About 1.5. And let's do just make this equal to 2. Let's see what that looks like. And when we do that, you can see it goes from a very thin line, a 0.5, a 1, our 1.5, and 2, which is twice the width of the 1. And if we're going to do different sizes, we had different colors, we had our alpha scheme. Let's take this whole thing here. Let's paste it down here and do another one. But instead of line width, let's look at styles. And something to note here, you can actually abbreviate this with LW. So line width can also be let's just do everything 0.2. And let's set up a line style. We'll do the first one dashes, and let me just paste that down here so I'm not doing a lot of extra typing. There we go. Take this out. So we have our dashed. We can do a dash dot. Oops, let's do the dash dot here. And a colon here. There we go. And there's a lot of different options. We'll look at a few more as we go down for different ways of highlighting data. But when you look at this, we have everything as a line width of 2, and now we have a straight line, we have a dash line, or a dot dash, and a dot 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 line. And then another thing we can add on here is we're going to do, here's our ax plot, and we did x, let's do x plus 4, so it goes right on the top. I'm going to do color black, line width 1.5, so it's a smaller line. And we're going to take the line and we're going to set dashes. So look how I've changed some of the notation here for my line and my ax plot. So I can set my line comma equal to ax plot, and then I can change the line settings this way. And when I run this, run that on here, you'll see the 5, 10, 15, 10 creates a series of dashes that are varied in length. In this case, they alternate between a short dash and a long dash. And we can play with these numbers. Curiosity always has me what happens when you play with the numbers. Just to see what they look like, let's do this. Let's paste this down here. I'll do 2 of these just because they're kind of fun to play with. And let's change this from 10 to 3. And we're going to change this one from 15 to 4. And let's run that. And you can see the differences in the lines. Oops, a little bit confusing on there, because I forgot to change the lines are all on top of each other. So let me change that really quick here. And let's run that. And now you can see here's our original dash line alternating. When I change these numbers on the second one, the very end value to 3, you can see now we have dashes of 5. Let's see, I'm going to guess this is a dashes of 5, skip 10, dashes of 15, skip 3, and then it goes back to the beginning. Dashes, 5 dashes, skip 10, 15 dashes, skip 3. And of course the last one we just switched up a little bit. It looks a lot more uniform because I'm using 2 sets of 10. Or if I did something like this and changed it to 30, it really becomes pronounced as far as the distances between them. And instead of 4, let's let's put 30 here also. 30 by 30, there we go. Really pronounced on that one. And let's look at one more important group for plotting our data. And in this, here's our plot we started with the x plus 1, x plus 2, x plus 3, and did it in blue on this one, 3 or 4 different blue lines. And this property, we want to add the actual plots, so you can see where the plots are on the graph. And for that, we might have marker equals O. And if we run this, you'll see it puts a dot for each of these, and there's 25 dots because we have 25 x values. So we actually have 0, and each of the different values of x, y are then plotted here with the dots. And we don't want to just limit ourselves to dots. We can also do plus sign, that's another option. Dots is most common. I actually like the dots the best. If we do the plus sign, you can see it puts a nice crosshairs or plus sign on there. And we can do a marker. There's a number of different markers you can use. And I think this one was it. S is another one, which is a nice square. And that's actually a good one, S for square. O for period. Okay, that's just kind of weird. So you can see that probably on these markers, another one is number 1. So if we run that, you'll see we now have these little hatch marks. And let's just go with the O on this one. By the way, this works with square really nicely. Some of the stuff we're going to do here in just a second. Let's do marker size equals 2. And change that to 5 and run that. And you can see here it puts a nice little tiny dot versus this size dot here. And this is interesting because it said 2. I thought it would be bigger. But if you do 0.5, it gets even smaller. And let's just do 10 to see what that looks like. Run. That looks huge. So marker size, a lot of these are dependent on the DPI and the setups. There's things that switch around as far as the way the size shows up. You got to be a little careful when you change one setting, it can change all the other markers. And then let's take our square on here, and we had marker size, so we also have marker face. We'll set that equal to red. Of course, I may change so it's up 1 notch. We'll run that. Whoops, must have mistyped something on here. And I did, it's marker face color equals red. And so when I run that, you can now see I have the squares on there with the marker face color. Of course, we can mix and match these. come down here and we'll make this, instead of, let's make this +7, and we'll make this size 15, marker face color equals, and we'll do what, green, just because. There we go, run. Very hard to actually see what's going on there. Still 25 dots, they kind of overlap. As you can see, they print them over each other. And of course, if we really wanted to make it look horrible, we could just make that really huge. Generally though, you want something a little bit smaller and cuter. We'll just try doing it this way. There we go. That's too small to even see the face. So 4, you can start to see the face on there around 4, and maybe on 8. 8 might be a good number for this. There we go, 8. Again, that all just depends on what you're trying to show and display. So we've covered a lot of stuff here as far as our lines. We've covered opaque with our alpha setting on there. Give us some nice pastels. You can see how they overlap and how they cross over. We covered the line width, different size on there, different formats for the line itself, and these are all, you can combine all these. So you can have our line width equals 2, line style equals dash. You can bring this down here also to the markers. And then we added markers in, just standard circle, a plus sign, the square, a little tick which uses a 1. Then we add a marker size and a marker color face, and we combine those. You see we get a nice different series of representations. We also briefly mentioned color, where you didn't have to use, like in here we used color black. Someplace up here, I'd have to find it, we use the actual number for the color, as opposed to, I changed them to red and blue. So you can get very precise on the color if you have a very specific color set that you need to match your website or whatever you're working on. All of those are tools in the Matplot library. So we have one more piece to formatting the graph, so we want to show you, and then we have 2 big sections. We're going to go over the different graphs that they have along with a challenge problem. So let's go to the last section we're going to look at is limits. We're going to limit our data. So this first part I'm just going to paste in there. We're going to create our subplots 1, 2. So 1 row, 2 columns. We're going to do a figure size of 10, 5. This should all look familiar now since we've done a number of them. And we're going to go ahead and plot, and this is an interesting notation you should notice here. Our axes 0, so 1 we've used, instead of, you can just iterate through them, but they're just an array, so it's an array of 0 is still the axes of the first axes out of 2. And we're going to plot x squared, x cubed, line width 2. So we're going to go ahead and just plot 2 graphs right on top of each other without doing multiple plots on here. And we'll set the grid equal to true on here. Let's go ahead and run that. And you can see here are 2 plots with the x value going across. And I'm going to do something similar. And by the way, you can just, if you look at it, you can see the grid on there. That's all that is. Easier to spot the data going across. We're going to take the same data for axis 1. So we have our plot of x squared, x and x cubed, line width 2. And this time we're going to take our axis 1 and do y limit. It's actually set underscore y limit. This is the y-axis, so it's going to be an array of two values. And we'll do 0, 60. I'm just making these numbers up. The guys in the back actually made them up. I'm just using their numbers. And we're going to set the x limit, and we'll set the x limit as, don't forget our brackets there, 2, 5. So it's the same data going in, but we're setting a limit on it. And let's go ahead and run that. And let's see what it comes out of. And here we have the y limit 0 to 60. So we're looking at just the lower part of this curve here up to here. And we have the x limit 2 to 5. So that starts right here at 2, and you can see very different graphs. This is kind of nice because you could actually put one of these on top of the other if you wanted to draw focus to one part of a graph. Remember how we did that earlier, one inside the other? But just a quick note, you can easily limit your graph and kind of reshape the way it looks quite easily. And we can also add that grid down there if you want a grid. We'll run that and add the grid in there. Oops, I guess you have to do the grid beforehand. Switch that. There we go. Sometimes the order on this is really important, so you may double check your order when you're printing these things out. It also helps if I change it to 1. So in this case, it might not be the order. I wonder if we'll go back here as 1. There we go. So it doesn't matter the order on grid. But you can set the grid for easy viewing here. Nice setup on there. But you can see how we can limit the data. So let's start looking at some other 2D graphs and make this cell a markdown. So when we run it, it has a nice pretty title to it. And let's go ahead and create some data with an NP array. We'll do 0 to 5 on here. There we go. And let's look at 4 common graphs. We'll put them side by side. So we'll do a figure, our axes equals plot, subplots, 1, 4 columns, and then figure size. Hopefully it'll fit nicely on here. It seems to do pretty good on here. And I'll go ahead and just run that since we're in there. Run. You'll see I have 4 blank plots on here. And we'll start with axes of 0. Let's set title. And we want this to be a scatter plot. A scatter plot just means it has a bunch of dots on it. So here's our axes of 0 dot scatter. Easy to remember. Scatter a bunch of plots on there. We'll do our n, or we can do x or n. There we go. And let's go ahead and do axes set title scatter. Oh, I already did that. We're just going to do scatter. That's how you do it on there. That is how you create a scatter plot, simply with the scatter control. And we'll do, let's do the variable x plus, let's throw some randomness in here. Usually scatter plots have a lot of random numbers connected to them. That's why they do them on there. And so the bigger the x gets, the bigger the randomness, so 0.25 times the randomness. And what we should end up down here is with the scatter plot. And you can see as you go up, it just kind of has some random numbers and moves up and down the line. But plots just the points. So if you remember from back up here where we did marker, this is plotting basically just the marker. So it's a scatter plot. Probably less used is a step plot. So for axes 1, we'll go ahead and do a step plot so you can see what that looks like. And this time I'll use our n value instead of x. We generated that n value up here. And so for this we have n times 2, or n squared, n times 2, n squared. Line width equals 2, and if we run that, it creates a nice step up. Let's see, so we've got a scatter plot, we've got a steps plot. Let's do a bar plot. And we'll use the same formula, n squared, alignment centered, because you can have them to the left or right, width 0.5, and alpha, if you remember correctly, that's how opaque it is. Let's see what that looks like on there. So we have some nice, you can see here a nice bar plot. It should look very similar to the step plot, but colored in. And we can change the width. Let's see what happens if we do 0.9, run. And if we take width out completely, run that, you can see it starts coming together on there. And we can change the alpha. We can take the alpha out too and run that. So now you have the solid colors. And if we take out the center and run that, everything, you really can't see the shift on here because that's actually the default on this. But these are common settings for the bar graph. Let me just put them back in there. There we go. Alignment, center, and alpha. Now, I can't say I've used the step graph very much. There's certain, I guess, domains of expertise that require a step graph. But the scatter plot and the bar graph, very common, especially the bar graph. And we'll look at histograms here in just a minute. So I use histograms a lot, especially in data science. But this is nice if you have very concrete objects. How many people are wearing yellow hats? That kind of thing. But if we're going to do that, let's go ahead and do the last one, which I see a lot more in the sciences. I'm certainly using the data science, but more like for mapping. I saw a publication on solar flares, and they were discussing the energy, and so filling in the graph gives it a very different look. So we're going to do the fill between. And it's just like you think it'd be. It's fill between, but with a underscore between them. And we'll do x and x squared and x cubed. And we'll do color green and alpha again, in case you had other data you wanted to plot on there. You can see it forms a nice squared coming up here. And also, if you look at the bottom one is your squared value, the upper line is your cubed value, and then it fills in everything in between. If you remember from calculus, this would be if you had like a motor and efficiency, they would talk about the efficiency going up and the loss, and you're looking for the space or the area between the two lines. So it gives you a nice visual of that. And let's look at a few more basic two-dimensionals. So we're going to have our figure size on here. We're going to do a radar chart. To be honest, I've never used a radar chart in business or in data science. I have to find a reason to use one now. So the first line for doing a radar chart, we have to add axes and the figure. And with this actually creates our, let's run it so you can see what it creates. It creates a nice, looks like you're on a submarine and you're tracking the hunt for red October or something like that. And it needs all of these. The polar is the fact that we're doing polar coordinates. 0, 0, 0.6.6 has to do with the size. If you take out any of these things and run them, you get just a box. If you take out the other half, you pretty much get nothing in there. And if you change these numbers, change them a little bit, you can see it gets bigger. They had 0.6 on here. I'll go ahead and leave it as 1 because that's just kind of fun. That's all about the size on here, the height and the width. And then let's create some data. T equals NP line space. And this is 0 to 2 times NP times pi. So if you remember, that is the distance across, and we're going to generate 100 points. So this is just a thing of data we're putting together. Then we can simply do an ax.plot. And in this case, let's do t comma t, which would be a diagonal line on a regular chart. And we'll give it a nice color, equals blue. And line width equals 3. Let's see what that looks like. And we can see here a spiral coming out. And remember, this would be just a diagonal line on a regular chart. What happens if we take this and instead of t times 0.5, there we go. And you can see it slightly alters the way it spirals out. We could do t times 2. Spirals out a little quicker. So it's kind of just a fun. Like I said, I've never used a radar chart. It's a column. But you can always think of radar in a submarine. Kind of looks like one of those, or in an airplane. And none of this would be complete if we didn't discuss histograms. Oh my gosh, do I use a histogram so much. And we'll use our NumPy that we have set as NP to generate, it looks like we have 100,000 variables we're going to set equal to n. And of course we create our figure and our axes. Subplots 1, 2, figure size 12, 14. So we're going to look at 2 different variations of the histogram. And we'll set a title, default histogram, set our title there. And then this is simply hist for histogram, and we'll just go ahead and put in our n in there. And let me run this and see what that looks like. And let's talk about what is going on here. So we generated an array here of data, 1,000 random arrays. It looks like they're mostly between -4 and 4. And then it adds up each one. It says 0, you have 35,000 that are 0. So that's what's most common on here. And we have 20,000 that are somewhere in this range right here between the -2 and, well, it looks like 1 and -2. And somewhere between 0 and 1, there's 30,000 numbers. So all this is saying is this is how common these variables are. And this will point you in so many directions when you're looking at data science to go ahead and run your histogram. So you should always have your histogram, and you can always put limits and all the other different things on your array, just like you did on the other graphs on there. And then we're going to do a cumulative detailed histogram. And all it is a histogram. Let me just do that. And we set cumulative equal to true and bins equal 50. And I really want to highlight the cumulative equals true is important, but we can now choose how many bins we have. In the first one, it kind of selected them for us. In this case, let me go ahead and run this, and you'll see it prints the data out for us. And here's our, whoops, must have missed, oh, there we go. It doesn't help that I put it over the old one. There we go, okay. So now you have your default histogram, and then we have a cumulative histogram. And we should have 50 steps in there. And let's just find out if that's true, not so much by counting them. I'm not going to count them. If you want to, you can count them. Let's just change it to 10 and see what happens. And we see here we have now 10 counts of that. And we could set that for 5 and run that. And then we have our 5 on there. And we go ahead and take the cumulative equals true out, just so you can see what that looks like. And let me run that on here too. That looks just like it did before. I think there's 1, 2, 3, 4, 5, 6, 7, 8. They have 8 different bins on here. Is what the default came out of. Put that back in there. Run. And so now it should look almost identical, and it does. And then we can put the cumulative back in, see what that looks like with the cumulative. And run that. And we can see how that shifts everything over and has a slightly different look. Wait, it shifts it all to the right? No, it doesn't actually shift it to the right. It's cumulative, so it's the total of the different occurrences. And so what that means is, like, if you consider this like for the year of rainfall, we have like day 1, you had a little bit of rain. Day 2, we have more rain. And so if you look at the number, this is 100,000, 35,000. So it's a cumulative detailed histogram of the occurrence as it grows. And rainfall is a good one, because that would be a cumulative histogram of how much rain occurred throughout the year. And we're going to look at 2 more graphs. We've already looked at a bunch of them. We looked at our radar graph. We've looked at scatter, step, bar, fill in, basic plots. We've looked at different ways of showing the data. We can increase the size of the line, the look, the color, the alpha setting. So let's look at contour maps. Just put that in there. There we go. Draw a contour map. And before we draw a contour map, we need to go ahead and create data for it. And if you have contours, your data is all going to have 3 different values. So let's go ahead and create the data here. We have our, you'd import your matplot library, your NumPy, so we have our numbers array. And we'll import matplot.cm, and that's your color maps. So you have all these different color maps you can look at. There's like hundreds of color maps. So if you don't want to do your own color, you can even do your own color map. They're pretty diverse. And of course our PLT, our PyPlot. And to generate our different data, we're going to create a delta 0.025. And we'll start with x, and we're going to create an array between -3 and 3 in delta increments of 0.025. And we'll have our y, we'll do something similar, and then we'll create our xy into a mesh grid. Again, these are all NumPy commands, so if you're not familiar with these, you'll want to go back and review our NumPy tutorial. And we'll do an exponential on here, -x² -y² for our z1. We'll do a z2, so we have 2 different areas, and z equals z of 1 minus z2 times 2. So we've created a number of values here. And let me go ahead and run this, and let's plug that in so you can see where those values are going. So once we've set these, we're going to create our figure and our x from our PLT subplots. We're going to create the variable cs, and this is going to be our contour. So right here, cs is our contour surface, and we're feeding it x, y, and z. And if you remember, x, y we created as our x and y components using our mesh grid. And you know what? Let's do this just because it's kind of good to see this. Let's go ahead and print x, and let's print y. And I always like to do this when I'm working with something that's either is really complicated, in this case is what we're looking at, or you don't understand yet. So we've created a mesh grid. We have x, y, and when we're done with this, we end up with, here's our x, and this set of values, and our y. So these are x and y coordinates. And then we've also created z based on our x and y. So we have x, capital Y, and capital Z as our 3 components. X and y being the coordinates, while z is going to be our actual height, since we're doing a contour map. So we created our contour map from our x, y, and z coordinates. We want to go ahead and put in a C label. Maybe we want to go ahead and do a title on here. We'll put that in our set title, and this is a contour. There we go, contour map. And let's go ahead and run this and see what that looks like. And you'll see we generated a nice little contour map. There's different settings you can play with on this, but you can picture this being you're on a mountain climb, and here we have a line that represents 0, maybe that's sea level. And then moving on up, you have your contours of 0.5 and then -1 and different setups, little hills. I guess if it's minus, that's like a pit. So I guess you're going down into a pit at -5 and -1. But on the other side, you can see you're going up in levels. So here's a mountaintop, and here's like a basin of some kind. And in data science, this could represent a lot of things. This could also be representing 2 different values and maybe profits and loss. I don't know if I'd ever really do that as a contour map, but I'm sure you can be creative and find something fun to do with a contour map. And then we're going to look at one last map, which is the 3D map. And those can be really important as a final product because they can show so much additional information that you can't fit on 2-dimensional graphs. There we go. Draw a 3D image. And so we're going to import from our MPL toolkits the mplot3D and the axes 3D. We're going to import axes 3D. This is what's going to let us work with the 3D image. And this should look familiar. We're going to create another figure just like we did before. Figure size 14 by 6. That's a good fit on the screen. We'll go ahead and run that. So we have our figure, and let's go ahead and take our x, and we're going to set that equal to fig.add_subplot. That should also be familiar from earlier. And we're going to work with, this sets the settings for the projection. And we're going to use 1, 2, 1 projection 3D. And we'll see what that looks like in just a minute. And we just created some 3-dimensional data here before, where we had x, y, and z, capital X, Y, and z. So we're going to reuse that data. We're just going to use that since this is also a 3-dimensional image. So let's use that for a 3-dimensional graph. And we simply do axplot_surface, and our capital X, capital Y, capital Z. So there's our data coming in. And we're going to add some settings in here. We're going to do rstride 4, cstride 4, and line width 0. And I'll show you what that is here in just a minute. Let's go ahead and run that so we can see our graph. And of course it helps if I don't add an extra comma in there. And you can see it generates this really beautiful three-dimensional graph. So let's take a little bit time to explore some of these numbers we have going in here. We have the R stride 4, the C stride 4, and the projection 3D. Projection 3D is the important one because that's telling us that this is a 3D graph here. So what are these first numbers? 1, 2, 1. Let's just change one of these. I'm going to change this to 5, and it's going to give me an error. Let's change it to 1. And oops, that didn't work. Let's change this middle one to 3 instead. And you're going to see how it starts reshaping the size and how it fits on the screen. And we'll change the first one to 2. We'll run that one. And again, it's changed the dimensions and the size and how it fits on here. Play with these numbers so you get a nice look and feel for it. Part of it is the tilt and the angle. We'll do 7 on this one. There we go. You can see it really shifted it there. But again, that changes the size and how it fits on the canvas. But we'll leave it at the 1, 2. And just so you get a good look at what we're talking about here, this is column width and index from before. If we do 1, 1, 1, you can see that it now spreads it out all the way across. It uses the whole setup on there. So this has to do with the size and how big you want it to be. Now, there's one term that we didn't cover in this yet, but we've used it throughout the whole setup. And I'm just going to type that down here, even though we're not going to go into detail. And that's the term heat map. You might see that is kind of starting to lose ground as far as a common reference, but there sure are a lot of people who still talk about heat maps. What is a heat map? Well, it is simply a color map. That's all it is. So if you ever see the term heat map, that refers to the fact this is in different colors representing different heights. That one isn't a heat map, but you can see up here we switched into, let me go back up here, here we go. This one has different colors for the different values. A lot of times you'll use, like instead of X and Y, you might do a heat map where you have a fourth value, and the fourth value represents the color. And so you'll see this 3D image in a nice colors represented by a heat map. That's all it is. So if you see the term heat map, that only means we're plotting some of the data in color to make it stand out or to give it a fourth dimension in this case. So we've covered a lot of things on Matplot, and that brings us, covered all the basics, so that brings us to practice example. And this is going to be the challenge for you. And let me go ahead and change our cell type markdown and run that so it looks pretty. Practice example, write a Python program to create a pie chart of the popularity of programming languages. Okay, excellent. And if you're going to have a challenge, we need some data. And I'll just throw in import our matplot library at the beginning. You should do that automatically. And so for our data to plot, we're going to have our languages. We're going to have Python, we're going to have Java, PHP, JavaScript, C#, C++. So those are 6 categories. And then we have our popularity. Oops, misspelling there. Popularity. We'll give the first one 22.2%, Java 17.6%. And I don't know if these are real numbers they pulled. My guess is that they might have just been made up because I don't know if Python's really that much more popular than the other ones. Maybe specific to data science, because Python's very popular in data science right now because it has so many options. The only other program that's highly used and exclusively for data science is R. So Python's big, and Python also does a lot more. It's a full programming language, where R is primarily for data science. They didn't even put R in here. So we have Python, we have Java, we have our PHP, and you can see the different values they've given it, or different percentages. And I did add these up. It does not add up to 100%. It adds up to 71% or something like that. And then we're going to give colors. And we've chosen, these guys in the back brought in these colors. I'm not sure what these colors are. We'll find out in a minute, so it'll be exciting. But you can see they're using the actual color values you can pull off of a color wheel or something like that. You could have just as easily done blue, red, green if you're too lazy to pick the exact colors. And then let's go ahead and solve this and see what we got here. We're going to do something a little fancy just because we can. The first thing we're going to do is we're going to use a variable called explode. And you'll notice that there's 6 variables in here, so that matches our 6 different categories. And the first one we've done is 0.1 and then 0, 0, 0, 0, 0. 0.1, when we put this in here under the explode in the plot, it will actually push that square out. So it's a really cool feature to highlight certain information on a pie chart. And this is simply plt.py. And we're plotting popularity. There we go. And before we add in all the really cool settings for this, let's go ahead and run it. And you'll see we generate a nice flat pie. Not too exciting there. And then we'll go ahead and put in all the extras. I talked about explode, where we can explode one of the values out. So here's our explode equals explode. Labels is languages, because we want to know what the different colors mean. Here's our colors equals colors, our auto picture. And this is standard print format. So that's a Python setup on there. And that's just going to put the value on the pie slice. And then we're going to add shadow because it just looks cooler with a shadow. Gives it a little 3D look. And we'll do a start angle of 140. Let's go ahead and run this and take a look and see what comes out of that. And look how that changes the whole setup. So here's our labels. There's our value we put on there. There's our slice that's pushed out. There's our shadow, a 3D effect. And then we started at 140. We could also rotate this. Let's just do this angle 90. And if we run it, you'll see the blue pie slice has moved up a little bit. We could actually let's just take the whole starting triangle out and run. It'll default to 0. And this is what it looks like if it defaulted to 0. So depending on where you want the highlighted slice to appear, usually you want that to appear on the left because people read left to right. And so it draws a focus onto, in this case, Python and how great Python is. I'm a little biased. We're teaching a Python tutorial, so it should be understandable that we're looking at Python. And one last reference before we close. You can go over to the matplotlib.pyplot setup, and if you go underneath the different functions on there, you can look this up on their website. You'll see a full list, and this is why it's so important to go through a tutorial like this, because this list is just so massive. I'm trying to figure out, like, here's our bar plot. There's a bar H. You can add barbs. There's a box plot we didn't cover. C labels, a totally different kind of, for your contour plot you can set up in there. If you go down here, we have our figures we used on there. We showed you the basics of how to do the figure. You'll see some closer references on those. There's a histogram down here, HIST. There's also the hist2d, makes a 2D histogram plot. H-lines, all of this, these are all the different commands that are underneath of here. And you can see it's pretty extensive. We've covered all the basic ones so that you now have a solid ground to look at these different options. So when you come to these functions, some of them are going to look a little off, or not off, will look unfamiliar, but you'll still have the availability to probably understand most of this and have a basic understanding of your matplotlib library.
Today, we learned one such data science library, that is scikit-learn. It has various features and several APIs to support, and therefore it is the most popular data science library in Python. So let's move ahead.
So what is the scikit-learn? It's a simple and efficient tool for data mining and data analysis. It's built on NumPy, SciPy, and Matplotlib, so it interfaces very well with these other modules. And it's an open source, commercially usable BSD license. BSD originally stood for Berkeley Software Distribution License, but it means it's open source with very few restrictions as far as what you can do with it. Another reason to really like the scikit-learn setup, so you don't have to pay for it as a commercial license versus many other copyrighted platforms out there. What we can achieve using the scikit-learn, we use the two main things are classification and regression models. Classification, identifying which category an object belongs to. For one application very commonly used is spam detection. So is it a spam or is it not a spam? Yes, no. In banking, it might be, is this a good loan, bad loan? Today we'll be looking at wine. Is it going to be a good wine or a bad wine? And regression is predicting an attribute associated with an object. One example is stock prices prediction. What is going to be the next value? If the stock today sold for $23.05 a share, what do you think it's going to sell for tomorrow and the next day and the next day? So that'd be a regression model. Same thing with weather forecasting. Any of these are regression models where we're looking at one specific prediction on one attribute. Today we will be doing classification. Like I said, we're going to be looking at whether a wine's good or bad. But certainly the regression model, which is in many cases more useful because you're looking for an actual value, is also a little harder to follow sometimes. So classification is a really good place to start. We can also do clustering and model selection. Clustering is taking an automatic grouping of similar objects into sets. Customer segmentation is an example. So we have these customers like this, they'll probably also like this. Or if you like this particular kind of features on your objects, maybe you like these other objects. So a referral is a good one, especially on Amazon.com or any of your shopping networks. model selection, comparing, validating, and choosing parameters and models. Now, this is actually a little bit deeper as far as a scikit-learn. We're looking at different models for predicting the right course or the best course or what's the best solution. Today, like I said, we're looking at wine, so it's going to be, well, how do you get the best wine out of this? So we can compare different models, and we'll look a little bit at that, and improve the model's accuracy via different parameters and fine-tuning. Now, this is only part one, so we're not going to do too much tuning on the models we're looking at, but I'll point them out as we go. Two other features: dimensionality reduction and pre-processing. Dimensionality reduction is we're reducing the number of random variables to consider. This increases the model efficiency. We won't touch that in today's tutorial, but be aware if you have, thousands of columns of data coming in, thousands of features, some of those are going to be duplicated, or some of them you can combine to form a new column, and by reducing all those different features into a smaller amount, you can increase the efficiency of your model. It can process faster, and in some cases you'll be less biased, because if you're weighing it on the same feature over and over again, it's going to be biased to that feature. And pre-processing. These are both pre-processing, but pre-processing is feature extraction and normalization. So we're going to be transforming input data such as text for use with machine learning algorithms. We'll be doing a simple scaling in this one for our pre-processing, and I'll point that out when we get to that, and we can discuss pre-processing at that point. With that, let's go ahead and roll up our sleeves and dive in and see what we got here. Now, I like to use the Jupyter Notebook, and I use it out of the Anaconda Navigator. So if you install the Anaconda Navigator, by default it will come with the Jupyter Notebook, or you can install the Jupyter Notebook by itself. This code will work in any of your Python setups. I believe I'm running an environment of 3.7 setup on there. I'd have to go in here into environments and look it up for the Python setup. But it's one of the 3X's. And we go ahead and launch this, and this will open it up in a web browser. So it's kind of nice. It keeps everything separate. And in this Anaconda, you can actually have different environments, different versions of Python, different modules installed in each environment. So it's a very powerful tool if you're doing a lot of development. And the Jupyter Notebook is just a wonderful visual display. Certainly you can use, I know Spider is another one which is installed with the Anaconda. I actually use a simple Notepad++ when I'm doing some of my Python script. Any of your IDEs will work fine. Jupyter Notebook is Iron Python because it's designed for the interface, but it's good to be aware of these different tools. And when I launch the Jupyter Notebook, it'll open up, like I said, a web page in here. And we'll go over here to New and create a new Python setup. And like I said, I believe this is Python 3.7, but any of the three, the scikit-learn works with any of the 3X's. There's even 2.7 versions. So it's been around a long time. So it's very big on the development side. And then the guys in the back, guys and gals, they went ahead and put this together for me. And let's go ahead and import our different packages. Now, if you've been reading some of our other tutorials, you'll recognize Pandas as PD. Pandas library is pretty widely used. It's a data frame setup, so it's just like columns and rows in a spreadsheet with a lot of different features for looking stuff up. Seaborn sits on top of Matplotlib. So this is for our graphing. And we'll see that how quick it is to throw a graph out there to view in the Jupyter Notebook for demos and showing people what's going on. And then we're going to use the random forest, the SVC or support vector classifier, and also the neural network. So we're going to look at this. We're actually going to go through and look at 3 different classifiers that are most common, some of the most common classifiers, and let's show how those work in the scikit-learn setup and how they're different. And then if you're going to do your setup on here, you'll want to go ahead and import some metrics. So the sklearn.metrics on here, and we're going to use the confusion metrics and the classification report out of that. And then we're going to use from the sklearn pre-processing the standard scalar and label encoder. Standard scalar is probably the most commonly used pre-processing. There's a lot of different pre-processing packages in the sklearn. And then model selection for splitting our data up. It's one of the many ways we can split data into different sections. And the last line here is our percentage matplotlib inline. Some of the Seaborn and Matplotlib will go ahead and display perfectly inline without this, and some won't. It's good to always include this when you're in the Jupyter Notebook. This is Jupyter Notebook, so if you're in an IDE, when you run this, it will actually open up a new window and display the graphics that way. So you only need this if you're running it in a editor like this one, with specifically Jupyter Notebook. I'm not even familiar with other editors that are like this, but I'm sure they're out there. I'm sure there's a Firefox version or something. Jupyter Notebook just happens to be the most widely used out there. And we can go ahead and hit the run button. And this now has saved all this underneath the packages. So my packages are now all loaded. I've run them, whether you run it on top or you run it to the left, and all the packages are up there, so we now have them all available to us for our project we're working on. And I'm just going to make a little side note on that. When you're playing with these and you delete something out and add something in, even if I went back and deleted this cell and just hit the scissors up here, these are still loaded in this kernel. So until I go under kernel and restart and clear or restart and run all, I'll still have access to Pandas. Important to know, because I've done that before. I've loaded up, maybe not a module here, but I've loaded up my own code and then changed my mind and wondering, why does it keep putting out the wrong output? And then I realize it's still loaded in the kernel and you have to restart the kernel. Just a quick side note for working with a Jupyter Notebook and one of the troubleshooting things that comes up. And we're going to go ahead and load up our data set. We're using the Pandas, so if you haven't yet, go look at our Pandas tutorial. A simple read the CSV with the separation on here. And so let me go ahead and run that. And that's now loaded into the variable wine. And let's take a quick look at the actual file. I always like to look at the actual data I'm working with. In this case, we have wine quality-red. I'll just open that up. I have it in my open office setup. I'm separated by semicolons. That's important to notice. And when we open that up, you'll see we have, go all the way down here. It looks like 1,600 lines of data minus the first one, so 1,599 lines. And we have a number of features going across. The last one is quality. And right off the bat, we see the quality is has different numbers in it, 5, 6, 7. It's not really, I'm not sure how high of a level it goes, but I don't see anything over a 7. So it's kind of 5 through 7 is what I see here. 5, 6, and 7. 4, 5, 6, and 7, looking to see if there's any other values in there. Looking through the demo to begin with, I didn't realize the setup on this. So you can see there's the different quality values in there: alcohol, sulfates, pH, density, total sulfur dioxide, and so on. Those are all the features we're going to be looking at. And since this is a Pandas, we'll just do wine head, and that prints the first 5 rows of data. And that's, of course, a Pandas command. And we can see that looks very similar to what we were looking at before. We have everything across here. It's automatically assigned an index on the left. That's what Pandas does if you don't give it an index. And for the column names, it has assigned the first row. So we have our first row of data pulled off our comma-separated variable file, in this case semicolon separated. And it shows the different features going across. And we have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 features. 12 including quality, but that's the one we want to work on and understand. And then because we're in Pandas data frame, we can also do wine.info. And let's go ahead and run that. This tells us a lot about our variables we're working with. You'll see here that there is 1,599. That's what I said from the spreadsheet, so that looks correct. Non-null float 64. This is very important information, especially the non-null. So there's no null values in here. That can really trip us up in pre-processing. And there's a number of ways to process non-null values. One is just to delete that data out of there. So if you have enough data in there, you might just delete your non-null values. Another one is to fill that information in with like the average or the most common values or other such means. But we're not going to have to worry about that. But we'll look at another way, because we can also do wine is null and sum it up. And this will give us a similar, it won't tell us that these are float values, but it will give us a summation. Oops, there we go, let me run that. It'll give us a summation on here, how many null values in each one. So if you wanted to, from here you would be able to say, okay, this is a null value, but it doesn't tell you how many are null values. This one would clearly tell you that you have maybe 5 null values here, 2 null values here. And you might just, if you had only 7 null values and all that different data, you'd probably just delete them out. Where if 90% of the data was null values, you might rethink either a different data collection setup or find a different way to deal with the null values. And we'll talk about that just a little bit in the models too, because the models themselves have some built-in features, especially the forest model, which we're going to look at. At this point, we need to make a choice. And to keep it simple, we're going to do a little pre-processing of the data, and we're going to create some bins. And bins we're going to do is 2, 6.5, 8. What this means is that we're going to take those values. If you remember up here, let me just scroll back up here. We had our quality. The quality comes out between 2 and 8 basically, or 1 and 8. But we have 5, 5, 5, 6. You can see just in the first 5 lines of variation in quality. We're going to separate that into just 2 bins of quality. And so we've decided to create two bins. We have bad and good. It's going to be the labels on those two bins. We have a spread of 6.5 and an exact index of 8. The exact index is because we're doing 0 to 8 on there. The 6.5 we can change. We could actually make this smaller or greater, but we're only looking for the really good wine. We're not looking for the 0, 1, 2, 3, 4, 5, 6. We're looking for wines with 7 or 8 on them. So high quality. You know, this is what I want to put on my dinner table at night. I want to taste the good wine, not the semi-good wine or mediocre wine. And then this is a Pandas. So PD, remember, stands for Pandas. Pandas cut means we're cutting out the wine quality and we're replacing it. And then we have our bins equals bins. That's the command. Bins is the actual command. And then our variable bins, 2, 6.58. So two different bins. And our labels, bad and good. And we can also do, let me just do it this way. Wine quality, since that's what we're working on. And let's look at unique. Another Pandas command, and we'll run this. And I get this lovely error. Why did I get an error? Well, because I replaced wine quality and I did this cut here, which changes things on here. So I literally altered one of the variables that is saved in the memory. So we'll go up here to the kernel, restart and run all. That starts it from the very beginning. And we can see here that that fixes the error because I'm not cutting something that's already been cut. We have our wine quality unique, and the wine quality unique is a bad or good. So we have two qualities objects. Bad is less than good, meaning bad's going to be 0 and good's going to be 1. And to make that happen, we need to actually encode it. So we'll use the label quality equals label encoder. And the label encoder, let me just go back there since this is part of sklearn. That was one of the things we imported, was a label encoder. You can see that right here from the sklearn.processing import standard scalar, which we're going to use in a minute, and label encoder. And that's what tells it to use bad equals 0 and good equals 1. And we'll go ahead and run that, and then we need to apply it to the data. And when we do that, we take our wine quality that we had before, and we're going to set that equal to label quality, which is our encoder. And let's look at this line right here. We have dot fit transform. And you'll see this in the pre-processing. These are the most common used, is fit transform and fit transform. Because they're so often that you're also transforming the data, when you fit it, they just combine them into one command. And we're just going to take the wine quality, feed it back into there, and put that back in our wine quality setup, and run that. And now when we do the wine and the head of the first 5 values, and we go ahead and run this, you can see right here underneath quality 0, 0, 0. I have to go down a little further to look at the better wines. Let's see if we have some that are 1s. Yeah, there we go. There's some 1s down here. So when we look at 10 of them, you can see all the way down to 0 or 1. That's our quality. And again, we're looking at high quality. We're looking at the 7 and the 8s, or 6.5 and up. And let's go ahead and grab our, where was it? Here we go, wine quality. And let's take another look at what else, more information about the wine quality itself. And we can do a simple pandas thing, value counts. Hopefully I typed that in there correctly. And we can see that we only have 217 of our wines which are going to be the higher quality. So 217, and the rest of them fall into the bad bucket, the 0, which is 1,382. So again, we're just looking for the top percentage of these. The top, what is that? It's probably about a little under 20% on there. So we're looking for our top wines, our 7 and 8s. And let's use our, let's plot this on a graph so we can take a look at this. And the SNS, if you remember correctly, that is, let me just go back to the top, that's our seaborn. Seaborn sits on top of Matplotlib. It has a lot of added features, plus all the features of the Matplotlib, and it also makes it quick and easy to put out a graph. And we'll do a simple bar graph, and they actually call it count plot. And then we want to just do count plot the wine quality. So let's put our wine quality in there. And let's go ahead and run this and see what that looks like. And nice inline. Remember, this is why we did the inline, so make sure it appears in here. And you can see the blue space, or the first space, represents low quality wine, and our second bar is a high quality line. And you can see that we're just looking at the top quality wine here. Most of the wine, we want to just give it away to the neighbors. No, maybe if you don't like your neighbors. Maybe give them the good quality wine, and I don't know what you do with the bad quality wine. I guess use it for cooking. There we go. But you can see here it forms a nice little graph for us with the seaborn on there, and you can see our setup on that. So now we've done some pre-processing. We've described our data a little bit. We have a picture of how much of the wine, what we expect it to be, high quality, low quality. checked out the fact that there's none. We don't have any null values to contend with or any odd values. Some of the other things you sometimes look at these is if you have like some values that are just way off the chart. So the measurement might be off or miscalibrated equipment if you're in the scientific field. So the next step we want to go ahead and do is we want to go ahead and separate our data set or reformat our data set. And we usually use capital X, and that denotes the features we're working with. And we usually use a lowercase y. That denotes what, in this case, quality, what we're looking for. And we can take this and we can go wine. It's going to be our full thing of wine. Dropping, what are we dropping? We're dropping the quality. So these are all the features minus quality. And we'll make sure we have our axes equals 1. If you left it out, it would still come out correctly just because of the way it processes on the defaults. And then our y, if we're going to remove quality for our x, that's just going to be wine, and it is just the quality that we're looking at for y. So we put that in there. And we'll go ahead and run this. So now we've separated the features that we want to use to predict the quality of the wine and the quality itself. The next step is if you're going to create a data set and a model, we got to know how good our model is. So we're going to split the data, train and test splitting data. And this is one of the packages we imported from sklearn. And the actual package was train, test, split. And we're going to do x, y, test size 0.2, random state 42. And this returns 4 variables. And most common you'll see is capital X train, that's what we're going to train our set with. Capital X test, that's the data we're going to keep on the side to test it with. Y train, Y remember stands for the quality or the answer we're looking for. So when we train it, we're going to use X train and Y train, and then Y test to see how good our X test does. And the train test split, let me just go back up to the top. That was part of the sklearn model selection, import, train, test, split. There is a lot of ways to split data up. This is, when you're first starting, you do your first model, you probably start with the basics on here. You have one test for training, one for test. Our test size is 0.2 or 20%. And random state just means we just start with it's like a random seed number, so it's not too important back there. We're randomly selecting which ones we're going to use. Since this is the most common way, this is what we're going to use today, there is, and it's not even an sklearn package yet, so someone's still putting it in there. One of the new things they do is they split the data into thirds, and then they'll run the model on they combine each of those thirds into 2 thirds for training and 1 for testing. And so you actually go through all the data and you come up with 3 different test results from it, which is pretty cool. That's a pretty cool way of doing it. You could actually do that with this by just splitting this into thirds and then, or have a test set, one test set third, and then split the training set also into thirds, and also do that and get 3 different data sets. This works fine for most projects, especially when you're starting out. It works great. So we have our X train, our X test, our Y train, and our Y test. And then we need to go ahead and do the scalar. And let's talk about this because this is really important. Some models do not need to have scaling going on. Most models do. And so we create our scalar variable. We'll call it SC, standard scalar. And if you remember correctly, we imported that here, along with the label encoder, the standard scalar setup. So there's our scalar, and this is going to convert the values. Instead of having some values that go from 0, if you remember up here we had some values are 54, 60, 40, 59, 102. So our total sulfur dioxide would have these huge values coming into our model. And some models would look at that and they'd become very biased to sulfur dioxide. It'd have the hugest impact. And then a value that had 0.076, 0.098, or chlorides would have very little impact because it's such a small number. So when we take the scalar, we kind of level the playing field. And depending on our scalar, it sets it up between 0 and 1 a lot of times is what it does. Let's go ahead and take a look at that. And we'll go ahead and start with our X train. And our X train equals SC fit transform. We talked about that earlier. That's an sklearn setup. It's going to both fit and transform our X train into our X train variable. And if we have an X train, we also need to do that to our test. And this is important because you need to note that you don't want to refit the data. We want to use the same fit we used on the training as on the testing. Otherwise, you get different results. And so we'll do just, not fit, transform. We're only going to transform the test side of the data. So here's our X test that we want to transform. And let's go ahead and run that. And just so we have an idea, let's go ahead and take and just print out our xtrain. Oh, let's do first 10 variables, very similar to the way you do the head on a data frame. You can see here our variables are now much more uniform, and they've scaled them to the same scale, so they're between certain numbers. And with the basic scaler, you can fine-tune it. I just let it do its defaults on this, and that's fine for what we're doing. In most cases, you don't really need to mess with it too much. It does look like it goes between like probably -2 to 2 or something like that. That's just looking at the train variable. We'll go ahead and cut that one out of there. So before we actually build the models and start discussing the sklearn models we're going to use, we covered a lot of ground here. Most of when you're working with these models, you put a lot of work into prepping the data. So we looked at the data, noticed that it's separated, loaded it up. We went in there, we found out there's no null values. That's hard to say, no null values. We have, there's none null value. I can't say it. And of course we sum it up. If you had a lot of null values, this would be really important coming in here. So is there a null summary? We looked at pre-processing the data as far as the quality. And we're looking at the bins. So this would be something you might start playing with. Maybe you don't want super fine wine. You don't want the 7 and 8s. Maybe you want to split this differently. So certainly you can play with the bins and get different values and make the bins smaller or lean more towards the lower quality. So you then have like medium to high quality. And we went ahead and gave it labels. Again, this is all pandas we're doing in here. Setting it up with unique labels and group names. Bad, good. Bad is less than good. That can be so important. You don't know how many times people go through these models and they have them reversed or something. And then they go back and they're like, why is this data not looking correct? So it's important to remember what you're doing up here and double check it. And we used our label encoder. So that was to set that up as quality 0, 1. Good, in this case we have bad, good, 0, 1. And we just double check that to make sure that's what came up in the quality there. And then we threw it into a graph because people like to see graphs. I don't know about you, but you start looking at all these numbers and all this text, and you get down here and you say, oh, yes, you know, here, this is how much of the wine we're going to label as subpar, not good. And this is how much we're going to label as good. And then we got down here to finally separating out our data so it's ready to go into the models. And the models take X and a Y. In this case, X is all of our features minus the one we're looking for, and then Y is the features we're looking for. So in this case, we dropped quality, and in the Y case, we added quality. And then because we need to have a training set and a test set so we can see how good our models do, we went ahead and split the models up, xtrain, xtest, ytrain, ytest. And that's using the train test split, which is part of the sklearn package. And we did, as far as our testing size, 0.2 or 20%. The default is 25%, so if you leave that out, it'll do default setup. And we did a random state equals 42. If you leave that out, it'll use a random state. I believe it's default 1. I'd have to look that back up. And then finally, we scaled the data. This is so important to scale the data. Going back up to here, if you have something that's coming out as 100, it's going to really outweigh something that's 0.071. That's not in all the models. Different models handle it differently. And as we look at the different models, I'll talk a little bit about that. We're going to only look at 3 models today, 3 of the top models used for this, and see how they compare and how the numbers come out between them. So we're going to look at 3 different setups. Oh, let me change my cell here to markdown. There we go. And we're going to start with the random forest classifier. So the 3 setups we're looking at is the random forest classifier, support vector classifier, and then a neural network. Now we start with the random forest classifier because it has the least amount of parts, moving parts to fine tune. And let's go ahead and put this in here. So we're going to call it RFC for random forest classifier. And if you remember, we imported that. So let me go back up here to the top real quick. And we did an import of the random forest classifier from sklearn ensemble. And then we also, let me just point this out. Here's our SVM where we imported our support vector classifier. So SVM is support vector model, support vector classifier. And then we also have our neural network. And we're going to, from there, the multi-layered perceptron classifier. Kind of a mouthful for the P, perceptron. Don't worry too much about that name. It's a neural network. There's a lot of different options on there in setups, which is where they came up with the perceptron. So we have our 3 different models we're going to go through on here. And then we're going to weigh them. Here's our metrics. So we're going to use a confusion metrics, also from the sklearn package, to see how good our model does with our split. So let's go back down there and take a look at that. And we have our RFS equals random forest classifier, and we have n estimators equals 200. This is the only value you play with a random forest classifier. How many forests do you need? Or how many trees in the forest. So how many models are in here. That makes it pretty good as a startup model because you're only playing with one number and it's pretty clear what it is, and you can lower this number or raise it. Usually start up with a higher number and then bring it down to see if it keeps the same value. So you have less, the smaller the model, the better the fit, and it's easier to send out to somebody else if you're going to distribute it. Now the random forest classifier, everything I read says it's used for kind of a medium-sized data set. So you can run it on big data, you can run it on smaller data obviously, but it tends to work best in the mid-range. And we'll go ahead and take our RFC, and I just copied this from the other side, .fit xtrain, ytrain. So we're sending it our features and then the quality in the Y train, what we want to predict in there. And we just do a simple fit. Now remember, this is sklearn, so everything is fit or transform. Another one is predict, which we'll do in just a second here. In fact, let's do that now. Predict RFC equals, and it's our RFC model, predict. And what are we predicting on? Well, we trained it with our train values, so now we need our test, our X test. So this has done it. This is the 3 lines of code we need to create our random forest variable, fit our training data to it. So we're programming it to fit. In this case, it's got 200 different trees it's going to build, and then we're going to predict on here. Let me go ahead and just run that. And we can actually do something like, let's do predict RFC. Just real quick, we'll look at the first 20 variables of it. Let's go ahead and run that. And in our first 20 variables, we have 3 wines that make the cut, and the other 17 don't. So the other 17 are bad quality, and 3 of them are good quality in our predicted values. And if you can remember correctly, we'll go ahead and take this out of here. This is based on our test. So these are the first 20 values in our test, and this has, as you can see, all the different features listed in there, and they've been scaled. So when you look at these, they're a little bit confusing to look at and hard to read, but there's a -0.01, so this is 0.36, -0.01, so 0.164, -0.09, or no, it's still -1, so -0.9, all between 0 and 1 on here. I think I was confused earlier and I said 0 between 2, -2, but it's between -1 and 1, which is what it should be in the scale. And we'll go ahead and just cut that out of there. Run this. We have our setup on here. So now that we've run the prediction and we have predicted values, well, one, you could publish them. But what do we do with them? Well, what we want to do with them is we want to see how well our model performed. That's the whole reason for splitting it between a training and testing model. And for that, if you remember, we imported the classification report. That was again from the sklearn. There's our confusion matrix and classification report. And the classification report actually sits on the confusion matrix, so it uses that information. And our classification report, we want to know how good our Y test, that's the actual values, versus our predicted RFC. So we'll go ahead and print this report out, and let's take a look. And we can see here we have a precision out of the 0. We had about 0.92 that were labeled as bad that were actually bad. And out of precision for the quality wines, we're running about 78%. So you kind of give us an overall 90%. And you can see our F1 score, our support set up on there, our recall. You could also do the confusion matrix on here, which gives you a little bit more information. But for this is going to be good enough for right now. We're just going to look at how good this model was, because we want to compare the random forest classifier with the other 2 models. And you know what, let's go ahead and put in the confusion matrix, just so you can see that on there, with Y-test and prediction RFC. So in the confusion matrix, we can see here that we had 266 correct and 7 wrong. These are the mislabels for bad wine, and we had a lot of mislabels for good wine. So our quality labels aren't that good. We're good at predicting bad wine, not so good at predicting whether it's a good quality wine. Important to note on there. So that is our basic random forest classifier. And let me go ahead, change cell type to markdown and run that so we have a nice label. Let's look at our SVM classifier, our support vector model. And this should look familiar. We have our CLF we're going to create. We'll call it, just like we called this an RFC. And then we'll have our CLF.fit. And this should be identical to up above. X train, Y train. And just like we did before, let's go ahead and do the prediction. And here is our CLF predict, and it's going to equal the clf.predict, and we want to go ahead and use x_test. And right about now you can realize that you can create these different models and actually just create a loop to go through your different models and put the data in. And that's how they designed it. They designed it to have that ability. Let's go ahead and run this, and then let's go ahead and do our classification report, and I'm just going to copy this right off of here. They say you shouldn't copy and paste your code, and the reason is when you go in here and edit it, you invariably will miss something. We only have 2 lines, so I think I'm safe to do it today. And let's go ahead and run this. And let's take a look how the SVM classifier came out. So up here we had a 90%, and down here we're running about an 86%. So it's not doing as good. Now remember, we randomly split the data, so if I run this a bunch of times, you'll see some changes down here. So these numbers, this size of data, if I ran it 100 times, it would probably be within plus or minus 3 or 4 on here. In fact, if I ran this 100 times, you'd probably see these come out almost the same as far as how well they do in classification. And then on the confusion matrix, let's take a look at this one. This had 22 by 25. This one has 35 by 12. So it's doing not quite as good. That shows up here 71% versus 78%. And then if we're going to do a SVM classifier, we also want to show you one more. And before I do that, kind of tease you a little bit here, before we jump into neural networks, the big save all deep learning, because everything else must be shallow learning, that's a joke. Let's just talk a little bit about the SVM versus the random forest classifier. The SVM tends to work better on smaller numbers. It also works really good on, because a lot of times you convert things into numbers and bins and things like that. The random forest tends to do better with those. At least that's my brief experience with it. Where if you have just a lot of raw data coming in, the SVM is usually the fastest and easiest to apply model on there. So they each have their own benefits. You'll find though again that when you run these like 100 times, the difference between these two on a data set like this is going to just go away. There's randomness involved depending on which data we took and how they classify them. The big one is the neural networks, and this is what makes the neural networks nice is they can look into huge amounts of data. So for a project like this, you probably don't need a neural network on this, but it's important to see how they work differently and how they come up differently. So you can work with huge amounts of data. You can also, in many respects, they work really good with text analysis, especially if it's time sensitive. More and more you have an order of text, and they've just come out with different ways of feeding that data in, where the series and the order of the words is really important. Same thing with starting to predict in the stock market. If you have tons of data coming in from different sources, the neural network can really process that in a powerful way to pull up things that aren't seen before. And when I say lots of data coming in, I'm not talking about just the high lows that you can run an SVM on real easily. I'm talking about the data that comes in where you have maybe you pulled off the Twitter feeds and have word counts going on, and you've pulled off the different news feeds that business are looking at, and the different releases when they release the different reports. So you have all this different data coming in, and the neural network does really good with that. Pictures. Picture processing now is really moving heavily into the neural network. If you have a Pixel 2 or Pixel 3 phone put out by Google, it has a neural network for doing, it's kind of goofy, but you can put little Star Wars androids dancing around your pictures and things like that. That's all done with the neural network. So it has a lot of different uses, but it's also requires a lot of data and is a little heavy-handed for something like this. And this should now look familiar because we've done it twice before. We have our multi-layered perceptron classifier. We'll call it an MLPC, and it's just as what we imported, MLPC classifier. There's a lot of settings in here. The first one is the hidden layers. You have to have the hidden layers in there. We're going to do 3 layers of 11 each. So that's how many nodes are in each layer as it comes in. And that was based on the fact we have 11 features coming in. Then I went ahead and just did 3 layers. Probably get by with a lot less on this. But I didn't want to sit and play with it all afternoon. Again, this is one of those things you play with a lot because the more hidden layers you have, the more resources you're using. You can also run into problems with overfitting, with too many layers, and you also have to run higher iterations. The max iteration we have is set to 500. The default's 200. Because I use 3 layers of 11 each, which is, by the way, kind of a default I use. I realized that usually you have about 3 layers going down and the number of features going across. You'll see that's pretty common for the first classifier when you're working in neural networks. But it also means you have to do higher iterations. So we up the iterations to 500. So that means it's going through the data 500 times to program those different layers and carefully adjust them. And we do have a full tutorials you can go look up on neural networks and understand the neural network settings a lot more. And of course we have, you're looking over here where we had our previous model where we fit it. Same thing here, MLPC, fit, X-train, Y-train. And then we're going to create our prediction. So let's do our predict and MLPC, and it's going to equal the MLPC. And we'll just take the same thing here, predict X test. Let's just put that down here, .predict X test. And if I run that, we've now programmed it. We now have our prediction here, same as before. And we'll go ahead and do the copy print again. Always be careful with the copy paste, because you always run the chance of missing one of these variables. So if you're doing a lot of coding, you might want to skip that copy and paste and just type it in. And let's go ahead and run this and see what that looks like. And we came up with an 88%. We're going to compare that with the 86 from our tree, our SVM classifier, and our 90 from the random forest classifier. And keep in mind, random forest classifiers, they do good on mid-sized data. The SVM on smaller amounts of data, although to be honest, I don't think that's necessarily the split between the two. And these things will actually come together if you ran them a number of times. And we can see down here the amount of good wines mislabeled with setup on there. It's on par with our random forest. So it had 22, 25. Shouldn't be a surprise, it's identical. It just didn't do as good with the bad wines labeling, what's a bad wine and what's not. Let's see, yeah, because they had 266 and 7. We had down here 260 and 13. So it mislabeled a couple of the bad wines as good wines. So we've explored 3 of these basic classifiers. These are probably the 3 most widely used right now. I might even throw in the random tree. If we open up their website and we go under supervised learning, there's a linear model. We didn't do that. Most of the data usually just start with a linear model because it's going to process the quickest and use the least amount of resources. But you can see they have linear quadratic, they have kernel ridge. There's our support vector, stochastic gradient, nearest neighbors. Nearest neighbors is another common one that's used a lot. Very similar to the SVM. Gaussian process, cross decomposition, naive Bayes. This is more of an intellectual one that I don't see used a lot, but it's like the basis of a lot of other things. Decision tree, there's another one that's used a lot. Ensemble methods, not as much. Multi-class and multi-label algorithms, feature selection, neural networks, that's the other one we use down here, and of course the forest. So you can see there's in sklearn there are so many different options, and they've just developed them over the years. We covered 3 of the most commonly used ones in here and went over a little bit over why they're different. Neural network, just because it's fun to work in deep learning and not in shallow learning, as I told you. That doesn't mean that the SVM is actually shallow. It covers a lot of things, and same thing with the decision tree, the random forest classifier. And we notice that there's a number of other different classifier options in there. These are just the 3 most common ones, and I'd probably throw the nearest neighbor in there and the decision tree, which is usually part of the decision forest depending on what the backend you're using. And since, as human beings, if I was in the shareholder's office, I wouldn't want to leave them with a confusion matrix. They need that information for making decisions, but we want to give them just one particular score. And so I would go ahead and we have our sklearn metrics. We're going to import the accuracy score. And I'm just going to do this on the random forest, since that was our best model. And we have our CM accuracy score, and I forgot to print it. If you remember in Jupyter Notebook, we can just do the last variable we leave out there, it'll print. And so our CM accuracy score we get is 90%. And that matches up here. We should already see that up here in precision. So you can either quote that, but a lot of times people like to see it highlighted at the very end. This is our precision on this model. And then the final stage is we would like to use this for future. So let's go ahead and take our wine. If you remember correctly, we'll do wine head of 10. We'll run that. Remember our original data set? We've gone through so many steps. Now we're going to go back to the original data. And we can see here we have our top 10 on the list. Only 2 of them make it as having high enough quality wine for us to be interested in them. And then let's go ahead and create some data here. We'll call it xnew equals, and this is important. This data has to be, we just kind of randomly selected some data. It looks an awful lot like some of the other numbers on here, which is what it should look like. And so we have our xnew equals 7.3, 0.58, and so on. And then it is so important. This is where people forget this step. Xnew equals sc. Remember sc? That was our standard scalar variable we created. If we go right back up here, before we did anything else, we created an sc, we fit it, and we transformed it. And then we need to do what? Transform the data we're going to feed in. So we're going to go back down here and we're going to transform our x new, and then we were going to go ahead and use the, where are we at? Here we go. Our random forest, and if you remember, all it is our RFC predict model right there. Let's go ahead and just grab that down here. And so our y new equals, here's our RFC predict. We're going to do our x new in, and then it's kind of nice to know what it actually puts out. So according to this, it should print out what our prediction is for this wine. And, oh, it's a bad wine. Okay, so we didn't pick out a good wine for our X new. And that should be expected. Most of the wine, if you remember correctly, only a small percentage of the wine met our quality requirements. So we can look at this and say, oh, we'll have to try another wine out, which is fine by me because I like to try out new wines, and I certainly have a collection of old wine bottles, and very few of them match. But you can see here we've gone through the whole process. Just a quick rehash. We had our imports. We touched a lot on the sklearn, our random forest, our SVM, and our MLP classifier. So we had our support vector classifier, we had our random forest, and we have our neural network, three of the top used classifiers in the sklearn system. And we also have our confusion matrix and our classification report, which we used, our standard scaler for scaling it, and our label encoder. And of course we needed to go ahead and split our data up in our mplotline train. And we explored the data in here for null values. We set up our quality into bins. We took a look at the data and what we actually have and put a nice little plot to show our quality, what we're looking at. And then we went through our three different models. And it's always interesting because you spend so much time getting to these models, and then you kind of go through the models and play with them until you get the best training on there without becoming biased. That's always a challenge, is to not overtrain your data to the point where you're training it to fit the test value. And finally, we went ahead and actually used it and applied it to a new wine, which unfortunately didn't make the cut. It's going to be the one that we drink a glass out of and save the rest from cooking. Of course, that's according to the random forest on there because we used the best model that it came up with.
Bokeh is one of the Python library used to create data visualizations like graph plots, bar charts, interactive dashboards, and other applications. So in this video, we'll help you understand how to build all these creative and beautiful visualizations using Python Bokeh.
Before we dive into this video, let's get a basic overview of what you can expect to learn from this video. What's in it for you? So first, we will explain what exactly the meaning of Bokeh is. Then, we will take a look at scatter charts and see how we can implement them in Bokeh. Next, we'll understand what line charts are, the scenarios in which they are used, and how they can be coded in Python Bokeh. Then we'll move on to pie charts and understand how data distribution can be represented using them. Next, we will take a look at histograms. Then we'll move on to bar plot and understand the difference between histograms and bar plots. We'll then take a look at area plot and how to understand them. And then we will move on to the layout function in Bokeh, which is used to make interactive web pages. And finally, we will use a data set to understand how we can make interactive charts in Bokeh by using everything that we've already learned in this video. So the first question that probably comes to your mind is, what exactly is Bokeh? Bokeh is a Python library which is used to make highly interactive graphs and visualizations. This is done in Bokeh using HTML and JavaScript. This makes Bokeh a powerful tool for creating projects, custom charts, and web design-based applications. Now, Bokeh is a Python library for creating interactive visualizations for modern web browsers. It helps you build beautiful graphics ranging from simple plots to complex dashboards with streaming datasets. With Bokeh, you can create JavaScript-powered visualizations without writing any JavaScript yourself. This makes it a very powerful tool for data visualization. Next, let's take a look at scatter charts and how you can plot them in Bokeh. Now, scatter plots are a plot of each individual data point in the data. Two variables are plotted against one another, and each data point on the x-axis has a corresponding individually plotted value on the y-axis. As a result, the plot looks like a bunch of scattered points. These are some examples of scatter charts. Here, each point on the chart corresponds to a value on the x-axis and its respective value on the y-axis. Using scatter plots, we can see how two different variables correspond to each other. Now, let's see how we can plot scatter charts using Bokeh. So the first thing that we're going to be doing is importing all of the necessary modules for our Python project. The first module that we're going to need is the Pandas module, which is used to work on data frames. Next, we will also be importing the Pandas Bokeh module, which is used to implement Bokeh on Pandas data frames. Next, we will import bokeh.io, which we will use to show the various graphs that we are plotting. We will also import bokeh.plotting, which will help us in plotting all of the various graphs that we're going to be looking at. We'll also import glob, a module which will help us merge our files and get them in the required format. So the first line of code that we're going to be writing is pandas_bokeh.output_notebook. This is basically just a line of code which will help you see your output in the same notebook itself. Now let's see how we can plot scatter plots in Bokeh. We already have imported the figure function from bokeh.plotting. The figure function contains most of the plots that we want to plot, such as line plots, scatter plots, bar charts, etc. So this is what we're going to be using. The first thing that you're going to need to do is create a figure. So how do we do that? Let's create a random variable p, and this we're going to be initializing to the figure function. Now within this figure function, we're just going to add a couple of parameters for our figure itself. So let's say we want the plot width to be equal to 400 and the plot height to be equal to 402. We're going to be plotting a scatter plot in the form of a square here. Next, we know that a scatter plot is nothing but various circles which are plotted on top of our graph. So that's what we're going to do. We're going to be plotting circles at certain coordinates which are going to be given by our lists. So the first coordinate is going to be the x-axis, and the next list that you're passing in is going to represent the y-axis coordinates. So over here, let's just plot this as 1, 2, 3, 4, and 5. And over here, let's start with 4, 7. These are all just random points. This is just to show you how exactly you can plot a graph in Bokeh. And now let's just say that we want the size of the circles to be equal to 10. And the color of every circle to be navy. We're also going to give a random parameter called alpha and equate that to 0.5. This will just act as a placeholder. Now over here, you've initialized your figure function and given it certain parameters. And using this figure function, you're calling the circle attribute of it, passing in other parameters such as the x-axis coordinates and the y-axis coordinates, the size of the circle, the color of each circle, and a random parameter called alpha. So now we've imported all of our modules. And this is how you plot a scatter chart in Bokeh. The same thing can be done when you look at the line plot. All you have to do is initialize your figure function and call the line attribute of it, pass in your x-axis coordinates and your y-axis coordinates, maybe pass in a couple of other parameters that are required, such as the width that you want the line to be and the color that you want the line to be, and finally all you have to do is show the plot. This is a basic overview of how you can use Bokeh to plot graphs. And here we have a line plot. So the main difference between the scatter plot here and the line plot here is that the line plot has various different points which are connected to each other with the help of a line. So again, what exactly are line charts? A line chart is a chart that represents data as a series of points which are connected to each other with the help of a line. It is used to see trends in our data and track the way data changes over a period of time. So this is the same chart that we just plotted using Bokeh right now. So as you can see, so the parameters that were passed in were 1, 2, 3, 4 and 5 on the x-axis, and 3, 1, 2, 6 and 5 on the y-axis. So how exactly the line chart is plotted is that you plot each of these points and then you connect them or join them using a line. Next, let's take a look at pie charts and how they can be implemented in Bokeh. But first, what exactly is a pie chart? A pie chart is a circular chart which is divided into slices to represent how much of the data belongs to a certain category. It is a quick and easy way to see the categories in our data and the percentage of the data set that they represent. On the other hand, you have another type of chart called a donut chart. Donut charts are like pie charts with a hole in the center. And in this hole, you can use it to represent extra data, or you can draw a pie chart within that hole itself. So this is an example of a pie chart. Using this, you can easily get to know the various categories that our data is divided into and the percentage that each of these categories contribute towards our data. Like over here, we have a pie chart which represents crewmates and imposters in a game called Among Us. So using this, we can just say that around 75% of our data is crewmates and 25% of it is imposters. On the other hand, you have a donut chart, which is almost exactly the same as the pie chart, except the middle portion is missing values. And in this middle portion, you can do other things such as plot a pie chart or represent other data within it. So now let's see how we can plot our pie plots using Python Bokeh. But first, we need to import the data that we're gonna be using to plot all of this. So the data that we're gonna be looking at is the Among Us data. Among Us, as you might know, is a game that caused quite a frenzy in the past 2 years. So the data that we're going to be working at is the Among Us data set that you can find on Kaggle. Among Us was the new craze for people playing mobile games that suddenly exploded in popularity and became a hit video game during the pandemic. Now Among Us is basically a multiplayer game where 4 to 10 players are dropped in an alien spaceship. Each player has their own role of imposter or crewmate. The task of the crewmate is to run around the spaceship to complete various tasks which are assigned to them and also to not get killed by an imposter. Players can be voted off the ship, so each game becomes one of survival. So let's load this data set and create more features. So now we've imported our data set. As you can see, our data set has over 2000 rows and 14 columns. The first column that I want to show you is the user ID column. The user ID column tells us which user the game data was collected from. Now there are 14 columns. The game completed data tells us the date and time of game completion. The team tells us if the player is an imposter or a crewmate. The outcome tells us if the game was won or lost. So over here, this is each game that a certain user has played. The user ID is used to represent the user who has played the game, and as you can see, we've collected data from 29 different people. And the number of games that these 29 people totally have played is over 2000. The outcome tells us whether the user has won or lost in this game. The task completed tells us how many tasks was completed by this user in this game. All tasks completed tells us whether the user was able to finish their tasks. Murdered tells us if the user was murdered. And imposter kills tells us the number of kills by the imposter. So if the user was not an imposter, we do not have data on how many kills was committed by the imposter during that particular game. That's why this column has a lot of missing values. Game length tells us the total duration of the game, and ejected tells us if the player was ejected or thrown off of the spaceship by their fellow players. Sabotage is fixed is basically the imposter within the game can create sabotages, and it's the crewmate's duty to fix them. So this tells us the number of sabotages which was fixed by this particular crewmate. Time to complete all tasks tells us the duration taken by the crewmates to complete all the tasks, and the rank change tells us the change in rank after wins or losses of the game. The region or the game code tells us the server and the game code. Now first, let's just see how exactly the data is distributed. So this tells us how many counts each column has. So as you can see here, most of them have the same number of counts except rank change, which has a couple of missing values. Unique tells us how many unique values exist in each column. So obviously team, there will be 2 because there are only 2 possible outcomes. You can either be a crewmate or you can either be an imposter. Outcome also has only 2 unique values because you either win a game or you lose a game. Task completed has 12 different values, and this is because the number of tasks which have been completed probably range from 1 to 12. All tasks completed has 3 values, which is yes, no, and missing data. And the same goes for murdered. You have yes, no, or missing data. Imposter kills tells us how many kills the imposter has made. So in this case, the most kills that the person has made is probably 9. Game length, there are 988 different values, and ejected, again there are only 2 values because you can either be ejected or you can either stay in the game. Now the top value tells us the most frequently occurring value, and the frequency tells us the frequencies of all of the top values. Now let's create a feature called minute and extract data from game length. So we're going to be splitting the game length column, which is this column, and we're going to be converting it into minutes. And then we're going to be using that data and creating a separate feature column called minutes out of it. So let's do this. So these are the first top 2 values of our new minutes column. The 0th value is 7 because the first game length that you see here was of 7 minutes. So all that we're doing is that we're going to be splitting this value, which is 7 minutes 4 seconds, and we're going to be keeping only the first value, which is that of the minutes. The second minutes value is 16 minutes, and that corresponds to the second value in our minutes feature variable. Now let's take a look at the murdered column. The murdered column has yes no values and missing data set and missing values. So let's change those. We're going to be replacing no values with not murdered, yes values with murdered, and the simple dash with missing. And we're going to be doing this in place, which basically means that this is going to make a change to our main data frame. So this is done. Let's take a look at our data frame now. This is what our data frame looks like. We have a game's length column, we have a minutes column, and we also have made changes to our murdered column, which is represented here. So now we don't have any missing values or dashes in our murdered column. We have all of it represented as categorical data. And this is one of the main columns that we're going to be using to plot our pie plots. So now let's see how we can plot a pie chart. The first thing that we're going to be doing is that we're going to be getting the total value counts in our team column here. So we're going to be plotting a pie chart with the help of this team column, and we're going to be getting the value counts of each unique value in the team column. So you can do this with the help of the value counts function that Pandas data frames provides us with. And now that we have the value counts of each unique value which is present in our team column, let's plot it in the form of a pie chart. We're going to be doing this with the help of the plot bokeh function. and the type of chart that we want to plot is a pie chart. Let's give it the title as ratio of imposters versus crewmates, and let's run this now. And this is what your pie plot looks like after you've plotted it. So now the same thing can be done to plot a donut plot. The first thing that we want to see is if there are more crewmates or imposters murdered or not in the game. To do this, we will add two more features, angle and color, which are going to be used in the chart. So to get angle, we're going to be importing pi from math, and we're going to be converting our angle in the form of radians. And as for the color feature, we're going to be having 3 different shades of blue. So this is basically what our murdered data frame looks like. So over here you have not murdered, the total value counts of which is 894, and the angle that this gives us is 2.522302, and this is the corresponding color. The same goes for murdered, which is 867 values, and we've converted that into an angle in radians and given it its own color. And finally we also have missing values, of which there are 466. The angle is 1.314756 and it has its own corresponding color. So this is a data frame that we're going to be using to plot our donut chart. So from bokeh.transform we import cumulative sum, and the cumulative sum is what we're going to be using to find the start of our angle, or basically to find how much portion of our donut chart is going to be occupied by the angle. So the donut chart can be plotted using the angular wedge function from figure. So the x-axis here is 0 and the y-axis is 1. The inner radius is the radius that you are going to be giving to the inner smaller circle, and that we've given as 0.15. The outer radius is the radius of the bigger outer circle, and the direction in which our data is going to be plotted is in the anti-clockwise direction. So let's run this. And this is what our donut chart looks like. So the not murdered is this dark blue color portion of our donut chart, and when you hover over it, you can see how many values are present in the not murdered column. The same goes for murdered, and because we've plotted our data in the anti-clockwise function, this is how it's being plotted. So murdered, not murdered, and then finally you have the missing values. The way that you can interpret this graph is that you can say that most of the people were murdered during the game, but most of the data is missing. So we can't say for certain whether the majority of the people were murdered during the game or not, because the number of missing values can make a huge difference. And the number of people who were not murdered and the number of people who were murdered are very close to each other. Like their total values are very close to each other. Next, we will create a data frame of sabotages fixed and minutes and change the column name and add T in them. So this is basically what we're doing. We've created a data frame which has the number of sabotages fixed and the minutes. Now let's just take the 3 sabotages which were fixed, which is 0, 1 and 2, and create a data frame out of all of these. So each of these individual data frames just contains these individual columns. To make a simple scatter plot with only one legend, we can pass the data and use scatter to make the charts. So basically we're just plotting the scatter chart in Bokeh here. And this is what our minutes scatter chart looks like. Now we're plotting this for 1t. We're plotting the minute at which one sabotage was fixed. And another cool thing about Bokeh charts is that you can always zoom into them or zoom out of them to better see where your data is plotted. So this is a scatter chart which has only one variable, which is 1t and the minute at which it was plotted. To make a scatter chart with more variables, we are going to need to use circle, which is a method of figure object, which we've already seen before. The circle is one of the many plotting styles which are provided by Bokeh. You can also use triangles or many more. You don't have to make each point a circle. So we're gonna be plotting the sabotages fixed and the minute at which they were fixed. And we're gonna be plotting 3 different circles of 3 different colors. I mean, each of them correspond to how many sabotages were fixed at what time. 0 sabotages at what time, 1 sabotage at what time, and 2 at what time. So let's run this. So as you can see here, when 0 sabotages were fixed, these were the times. When 1 was fixed, this was the time at which it was fixed. And when 2 was fixed, this is the time that it was fixed at. Now the x-axis is our minutes and the y-axis is the sabotage. When you hover over it, you can see various information about where each circle is plotted. So this has an index of 10. The data xy will tell you the exact x coordinate and the y coordinate, and the screen xy will tell you the screen pixels on which it is plotted. So now we've taken a look at pie charts. Let's move on to histograms. So what exactly is a histogram? Histograms are used to plot numerical data according to the range that they fall into. The data is plotted in the form of bins or rectangles, and the y-axis corresponds to the amount of data present in a certain range or at a certain point. So this is what a histogram looks like. This is a histogram of the distribution of minutes. So the x-axis has the range within which this data falls. Like over here, the first range is from 0 to 2.9 and the second one is from 2.9 to 5.8. Each range has a value of 2.9 and the corresponding y-axis or the height of the bins tells us how much data is present within this range. So this is how you can read histograms. Now let's see how we can plot them using Python Bokeh. Now let's see the distribution of minutes in the Among Us game. We will use hist to plot a histogram. So basically just going to be plotting the minutes of our game. We're going to be using the df min column for this, and we're going to be converting it into an integer. So this is the column that we're going to be plotting. Let's plot this. Again, we're going to be using the plot bokeh function here because it makes plotting data frames very easy. The kind of data frame that we're going to be using is the histogram or hist, and the title of our graph is going to be distribution of minutes. So let's run this. Now this is what our histogram looks like. Now this is when we've only plotted one variable, which is minutes. Yeah, so another thing that you can plot is a stacked histogram. A stacked histogram is when you plot various histograms on top of each other. So let's see how this works. For a stacked histogram, we want to see if the game length has a correlation with the amount of imposters and crewmates in our game. So to do this, we're going to be creating a small data frame which has the game length and the team columns combined. So let's do that. And this is what this looks like. So all you have to do to plot this in the form of a stacked histogram is use the hist function again. So let's see how that is done. And let's give this figure a size of, say, 750, 350 size. So let's run this again. And this is the stacked histogram that you get. We have two different columns which are plotted on top of each other versus the game length. So basically this tells us that when the game length was between 0 to 0.9 minutes, the number of imposters was way higher than the number of crewmates. And the longer the game went on, the number of imposters decreased and the number of crewmates just kept getting longer and longer. Now, obviously, you can say that the number of crewmates is decreasing as the game goes on too, but this is because the imposters would have killed off most of the crewmates. As you can see here, towards the end, there are no imposters, which means that most of the imposters were ejected and the crewmates won. So now we've taken a look at histograms. Let's move on to bar plots and understand how exactly they're different from histograms. So in histograms, you have plotted numerical data distributions as of yet. In bar plots, you plot for categorical data. It also uses bins to plot the amount of data. When the bins are stacked on top of each other, it's called a stacked bar chart. This is basically what a bar chart looks like. The difference is this does not have its own range. Each bar is used to represent a categorical data, and the height is used to tell us how much of that categorical data is present. So now let's see how we can plot a bar plot. So again, we're going to be making a small data frame of the task completed and the value counts of how many tasks have been completed. To plot a bar plot, we're going to be using plot bokeh again, and the kind of plot that we want to plot is bar. So let's run this and see what we get. So here is your bar plot. The task completed in this case is categorical data, and the counts basically tells us how many value counts fall into each category. So 0 tasks completed are 69, 1 task completed is 117, 2 tasks completed is 10, and so on. From this bar chart, you can say that the most number of tasks completed is 7 and the least tasks completed are 10. Now let's create a stacked bar chart and let's see who wins, imposters or crewmates. To create a stacked bar chart, what we're going to be doing is that we're going to be creating a different smaller data frame of team and outcome. To make sure that the bar chart is stacked, all you have to do is include a stacked attribute in your bar function and change its value to true. So let's run this and see. And here you can see that we have a stacked bar chart. So you can see that crewmates who have a lot more data have won 981 times and lost 780 times, while imposters have lost 205 times and won 216 times. So the crewmates have won significantly far more than the number of times imposters have won. Now let's take a look at stacked vertical bar charts. So far the bar charts that we've been looking at have been horizontal, which means that the data goes upwards. For a vertical bar chart, we're going to be seeing if all tasks have been completed or not. So in the data frame column, all tasks completed, we're going to be replacing the values of yes and no with tasks completed and tasks not completed. We're also going to be creating a smaller data frame of the outcome column and the task completed column. To plot a stacked vertical bar chart, you are going to be using Python bokeh.bar h function, and you're going to be changing the stacked attribute to true. This is what a stacked horizontal bar chart looks like. So over here we can see that the missing values is represented by blue, task completed by orange, and task not completed by green. Here you can see the total outcome. You can see how many wins, how many tasks are completed, and how many tasks are not yet completed. And the same goes for losses. You can see how many losses have occurred, how many tasks are completed, and how many tasks were not completed. This is a very good way of representing a lot of data in a relatively smaller area. Now, the way we can interpret this graph is that we can say that finishing the task will automatically ensure that the crewmates have won. So there's a higher number of people who need to complete the task to win the game. Another very unique type of bar chart that you can have is a bidirectional bar chart. So let's plot a bidirectional bar chart in which the bars will be going both ways, to the left and to the right. We're going to be plotting a horizontal bar chart over here to make it easier for you to see. To have a bidirectional bar chart, you need positive values and negative values. The center is going to be at 0. So here we're going to be making the loss feature as negative by multiplying the loss feature with the -1 value. So here we go, the losses are all negatives and the wins are all positives, right? Now let's run this and see how many losses and wins have occurred for each user. So user 1 has 42 losses and 58 wins, but you can easily see whether they have won more or lost more by comparing the height of the bars for the wins and the losses. So we can easily say that in this scenario, user 1 has won more times than they've lost. The same can be said for user 2, where the wins bar is significantly higher than the losses bar. So this is how you can plot and understand a bidirectional bar chart. So we've taken a look at how we can plot bar charts and the various types of bar charts that are available to us in Python Bokeh. Now let's take a look at area plots. Area plots is a combination of the line and the bar chart when the area below a line is shaded. Using an area chart, we can see how the values of different groups change over a period of time. The area chart has different baselines to show the vertical range of data. Here we've plotted the sabotages fixed versus the minutes at which they were fixed at, right? So these are the minutes, and the sabotages fixed are of two types, 0t and 1t. So the number of minutes that we're considering here is somewhere around 28-ish, right? And 0t, as you can see, has a way higher value. So one really good thing about area plots, especially in this case, is that they have two ranges. And they have another range on the y-axis, which tells us how the number of sabotages fixed is ranging. So 0 sabotages fixed, you can see how the value keeps fluctuating and how the value changes for different minutes. And the same can be said for 1t. Now 1t has a baseline which is over here, which is just above the 0t baseline. This doesn't necessarily mean that this is where 1t starts and this is where it ends. This just means that it ranges from 0 all the way here, and we can compare very easily how 0 sabotage is fixed and 1 sabotage is fixed range or change with respect to each other at the same time. Now, the first thing that we're going to be doing to plot our area chart is that we're going to be creating another data frame. This is called df minutes, which is going to be comprising of the minutes column of our data frame and the sabotage is fixed column of the same data frame. For df min, we're going to be renaming the columns to 0t and 1t. And the only columns that we're going to be considering out of the 5 different columns that we have are the 0t and the 1t column. We're going to be combining all of these together in a format which can be plotted by using Bokeh, and column data source helps us do this. It helps us convert our various data frame columns into lists. Next, we're going to be using the figure function, and we're going to give our figure a width of 400, a height of 400, and the title of sabotage is fixed versus the minutes at which they were fixed at. To plot a stacked area graph, you're going to be using varea underscore stack function from the figure module. You're going to be passing in your y parameters, which is y0 and y1, because we have two different y parameters here, and the x parameter, which is df minutes. The color that you're going to be using is gray and light gray. The legend labels are the names that you've already put here, which is 0t and 1t, and the source of your data is going to be this column data source. Now let's run this and see how our area chart looks. So this is our area chart. We've gotten two different sabotages here and two different times at which they occur, which is 0t and 1t. The minutes tells us how many sabotages were fixed at each time, basically how long it took to fix a sabotage, and the minute during the game at which they occurred. Now let's take a look at the layout function of our Bokeh library. The layout function will let us build a grid of plots and widgets. We can have as many rows and columns or grids of plots in one layout. Using the layout function, we can see various graphs at the exact same time. Mainly used for designing dashboards, it lets you build grids of plots. So this is basically what your layout function will help you do. This is going to look very good in a website because it's going to arrange our plots in a way that we can easily see all of them and understand all of them without any loss of data. This is also arranged very neatly, which is exactly what the layout functions allow us to do. So now let's take a look at how the layout function can be implemented in Python Bokeh. Now of the layout functions, there are many different layout options which are available. You have the column function which allows you to display plots vertically. And you have the grid function which lets you display plots in the form of grids. Now, for example, let's say that we want to make a dashboard layout in Bokeh. We are going to be considering three different charts. The first one that we're going to be considering is a lollipop chart, which is done here. The next one that we're going to be considering are two pie charts. So this is how you plot a lollipop chart, and I'll show you what exactly a lollipop chart is in just a minute. The first thing that you need to know is that the first graph that we're going to be plotting is going to be a graph which has the user ID versus the outcome of the games plotted on it. So what we're going to be doing here is that we're going to be creating a single data frame which has all of the user IDs present in it along with the user and the wins that the user has obtained. Now using this, we're going to be plotting it in the form of a plot in decreasing order where we have the top 10 users who have won, which basically means that the users who have won the most number of games out of all the users in consideration. So figure 1 segment will basically help you plot a line which has a width of 2, and a circle will be at the very top of this segment. So lollipop chart is going to be a horizontal line with a circle at the very top. Sorry, the next graph that we're going to be plotting is going to be a murdered and not murdered and missing values pie chart. And the last thing that we're going to be plotting is a donut chart of the teams. and the values within them. So these are the three different graphs that we're going to be plotting, and these are just us creating the graphs and plotting them. The main logic is over here. The main logic is that you want to set a layout in Bokeh as to how you want to see the charts. So the layout that we are going to be looking at is that we're going to be having a lollipop chart at the very top and two smaller pie charts at the bottom, right? So we have three figures here. And the first thing that we're going to be doing is that we're going to be giving these figures a line color of none. The axis is not going to be visible and the axis labels are not present for these figures. This is the main function that you're going to be looking at. This is your layout. Using the grid layout function that you've imported here from bokeh.layouts, you're going to be creating a grid. And how does the grid know where the figures are? So you've divided the grid into two. This is evident because you have two main figures here, which are separated by a comma. So this tells the grid that the page is going to be divided into two. The first figure, which is on top, is going to be figure 1, and the figure at the bottom are figure 2 and 3. This means that the bottom half is going to be further split into vertically. Let's run this and see what our layout looks like. So here you have it. Your entire page is divided into two. The first one has the figure 1, which is the lollipop chart, and the bottom half of our page has two figures, which are the two donut charts. The bottom half is divided exactly into two, as you can see here. This is because that is the grid layout that we wanted. So this is how you can use the layout function in Python Bokeh. It is extremely easy. All you have to do is create a layout by using the grid function, or you can also use the column function. The column function will plot it in the form of a single column vertically. Using the grid function, you can plot figures vertically as shown here. So when you separate them by commas with respect to each other, they will be plotted vertically, and when you group them together and separate them with commas internally, they will be plotted horizontally. So now we've taken a look at how we can use a layout function. Now let's see how we can make interactive graphs with the help of Bokeh. Over here, we're going to be using Bokeh to design a dashboard which is used to represent the horsepower in cars. We are also going to make our graphs interactive and see how maximum information can be conveyed with the help of a single graph. So here we have multiple different cars, and along with the cars we're also going to be given their horsepowers, a little bit of other information about them, and their images. And over here, as you can see, we have a very simple vertical bar chart. But let's see how we can make it interactive and convey all the information that we have in our single data set on this one bar graph. So the first thing that we're going to be doing is importing all of our important necessary modules. We're obviously going to have the pandas modules, which is going to be imported to work with the data frame that we've given. Apart from this, we're also going to be importing figures, output file, show, save, and column data source from bokeh.plotting. We already know that the figure function is used to plot different types of graphs which are given. Output file is just used to see our file. The show is used to display our graphs, and save will help you save your graph. Now, the column data source is the core of most Bokeh plots. It provides the data to the glyph of your plot. When you pass sequences like Python lists or NumPy arrays to a Bokeh render, Bokeh automatically creates a column data source with this data for you. So this is basically what you're going to be using to pass data onto your Bokeh glyphs. Apart from this, we're also going to be using a hover tool function, and from the transform function, we're going to be importing factor CMap. We're going to be importing a palette color, which is going to be various shades of blue. And we're going to be importing components from the embedded function of Bokeh. Let's just see how we can use all of these and the different things that they do. the first thing that you're going to be doing is reading in your car's data frame and creating a column data source so that you can easily parse this data onto your Bokeh glyphs. So let's run and import all of our various required functionalities and import the data as well. So this is what your data set looks like. We have 8 different values in our data set, which are the names of different cars, their horsepower, their price, and a hyperlink of an image. This is what our data set looks like. We have only 8 columns. So using this data set, we're going to be plotting a horizontal bar graph. Again, we're going to be calling our figure function and we're going to be giving y range to our car list. The y range is basically just going to have the different values which are going to be present on the y-axis. We've given the plot a width of 800 and a height of 600. The title of the plot is Cars with Top Horsepower and the x-axis label is horsepower. The tools that we're using here is pan, box select, zoom in, zoom out, save and reset. So these are tools that you're going to be getting on the right side of your plot. Now let's render our glyph or render our graph. The graph that we're going to be using here is the horizontal bar graph. So the y-axis is going to have cars and the right, or basically the height of the entire bar, is going to depend on the horsepower. The left is going to start from 0 and the height of each bar is going to be 0.4. The color that we're going to be giving is going to be a palette of blue. So each different car will have a different color of blue associated with it, and the color of blue which is associated with it will depend on the car list. Now fill alpha 0.9. The source is your source data that you have over here, which is the column data source of our data frame. And the legend is going to be car, which basically means that your entire plot is going to have the legend of car. Now we're going to be adding the legend. This is us giving the legend its orientation. So the legend is going to be vertically oriented. The location is going to be on the top right, and the font size of the text car of our legend is going to be 10 px or 10 pixels. We're also going to be adding a hover tool. Inside this hover tool tips will basically tell you what you're going to be seeing in the hover tool box. So we're going to be creating this with the help of an HTML format. The first thing that you're going to be seeing is the name of the car. The next column will have the price of the car, the horsepower of the car, and the image. Now the image is in the form of a hyperlink, and this is going to be auto-populated in your hover tool. The width of the image is going to be 800. So we are going to add all of these hover tools to our P image, and we're finally going to be showing you the graph and what it looks like. So this is your Bokeh plot. Here the title of the plot is Cars with Top Horsepower. This is your legend, which is cars. The name of each car is given here along with the color which is associated with it. Here are the different tools that we have. You can save this, you can reset it, you can zoom out, you can zoom in, you can select the boxes, and you can pan your image. So here we're zooming in, here we're zooming out. If we save this, the plot automatically gets downloaded in your system, and if you reset it, the image goes back to exactly what it looked like when it was first opened. Now here you have the names of the different cars on the y-axis, and you have the various horsepowers on the x-axis. Let's take a look at our hover tool. So here you have the name of the car which is on top, you have the price, and you have the horsepower, and as you can see, you have the image which is populated instantly from the hyperlink that was available to us. Now the color palette associated with each car gets darker the more the horsepower of the car increases. So here we have cars with top horsepowers which are arranged in an ascending order from the top and a descending order from the bottom. So this is another way that you can use Bokeh to create extremely interactive and informational graphs. Here in just half a page, and this is us making a huge plot, right? We can also decrease the size of the plot if you want to. But basically in half a page, we've conveyed all the information ranging from the name of the car to its model to the horsepower that it has, its price, and also its image. And this is also a very good way to compare it. So these are just some functionalities which are provided in Bokeh itself. No other data visualization library will let you work so well with graphs and will let you customize your graphs to this extent.
Today, we'll discuss about Spotify data analysis using Python. So without further delay, let's get started.
Spotify is a Swedish audio streaming and media services provider founded in April 2006. It is the world's largest music streaming service provider and has over 381 million monthly active users, which also includes 172 million paid subscribers. The total number of downloads on the Spotify app in the Android store exceeded 1 billion in May 2021. So millions of people listen to music all day. Even I am hooked to music. As an analyst, what's better than exploring and quantifying data about music and drawing valuable insights? Before I move ahead, I have a quiz question for you people. The name Spotify comes from a combination of two words. So which are those two words? Please let us know your thoughts in the comment section below. I would like to repeat the question again. The name Spotify comes from a combination of two words. So what are those two words? We would love to hear from you. So please put your answers in the comment section below. Now, let's use Python libraries and functions to analyze and visualize our dataset. First, I'll show you the two datasets that we'll be using. So here is the first dataset that we'll be using for our demo. And then I have my second dataset called Spotify features, which is essentially about the genres of the different soundtracks. Now these datasets have been downloaded from kaggle.com. Now the links to the datasets have been provided in the description box. Please go ahead and download them. Now let me just go ahead and brief you about the columns that are present in our first dataset, which is about tracks. We have our column A, which is ID. This is the unique ID for each of the songs. Then we have the name column, which is essentially the name of the song. Then we have a column for popularity. So the popularity ranges from 0 to 100. Then we have duration in milliseconds. This is the duration of the track in milliseconds. Next, we have a column called explicit. Now we are not bothered about this column because we are not going to use it in our analysis. Then we have artist. So the name of the artist who has composed or sung the song. Then we have ID of the artist. Then we have a column for release date, which is basically the date on which the song was released. Then we have a column for danceability. So this describes how suitable a track is for dancing based on a combination of musical elements such as tempo, rhythm stability, beat, strength, and overall regularity. The value ranges between 0 and 1. Next, we have a column for energy. So the energy is a measure between 0.0 to 1.0 and represents a perceptual measure of intensity and activity. Typically, the energetic tracks feel fast, loud, and noisy. Higher the value, the more energetic is the song. Then we have a column for key. So key is the pitch, notes or scale of song that forms the basis of a song. There are 12 keys ranging from 0 to 11. Moving ahead, we have loudness. So the overall loudness of the track in decibels, it ranges from -60 to 0 decibels. Then we have mode. So songs can be classified as major and minor. 1.0 represents major or 1 represents major and 0 represents minor. Next we have speechiness. So speechiness recognizes the presence of spoken words in a track. More exclusive speech like the recording, example talk show, audiobook or poetry, the closer to 1.0 the attribute value. Then we have a column for acousticness. So a confidence measure of 0 to 1 of whether the track is acoustic or not. So 1.0 represents high confidence the track is acoustic. Then we have other information about instrumentalness. Then we also have a column for liveness. So liveness detects the presence of an audience in the recording. Then we have a column for valence. So valence is a measure between 0.0 to 1.0 and describes the musical positiveness conveyed by a track or a song. And finally we have the columns for tempo and time signature. Now even in the second data set we have almost the same columns, just that we have an additional column that is about the genre of the songs present in the data set. Cool. Now let's head over to our Jupyter notebook and we'll start with our analysis. Okay, so one more thing to remember, our data has information from 1922 onwards, so all the songs from 1922 till 2021. Cool. Okay, so I'm on my Jupyter notebook. So you can see I have a few cells that have already been filled up. So we'll start with our analysis. First of all, let's go ahead and import the necessary libraries. So I'm importing NumPy, Pandas, Matplotlib and Seaborn for my analysis and visualization. I'll hit Shift Enter to import the libraries. Alright. And in the next cell, I'm going to load my dataset using the pandas read_csv function. I have my location already put here. Let me show you the location where the data files or the data sets are located. So this is my location under Chrome downloads. I have a folder called Spotify datasets. Okay, so let's import and check the first 5 rows in the dataset. So for that I have used the head function. There you go. So here you can see I have my first 5 rows of information from the dataset, and on the top you can see the different columns. You have ID, name, popularity, artist, then we have the release date, danceability, energy, key, loudness, liveliness or liveness, valence, tempo and other information. Cool. Now let's check for null values in the dataset. I'll just give a comment as null values. Every time when you download a dataset from an open repository, there are chances that the dataset would contain null values, so it's better to check them beforehand. So I'm going to use the isNull function present in the pandas library. PD I'm using because I had imported pandas as PD. So pd.isNull. Then I'm going to use the variable name df_tracks because I imported my dataset and stored it in the variable df_tracks. So I have my data frame under df_tracks variable, and then I'll use the sum function to check the total number of null values present in the dataset for each of the columns. If I run it, there you go. So here you can see my name column has 71 missing values or null values, and we don't have any null values for the rest of the columns. Okay. Now let's use the info method that will give us the total number of rows and columns in the dataset, and we'll also check the data types and the memory usage. So I'll say my data frame name, that is df_tracks.info. If I run it, you can see here. Now if you mark, there are total 5,86,601 names or the names of the songs present in the dataset, while the rest all have 5,86,672. So clearly there are total 71 song names or soundtracks missing from our dataset. And below you can see the data types. We have float, integer and object, and then you can see the memory usage. Cool. Now before I move ahead with our next analysis, I have another question for you. Which artist or musician has the most number of followers on Spotify? I repeat, which artist or musician has the most number of followers on Spotify? Please put your answers in the comment section below. We would be happy to hear from you. Now let's move ahead and do our first major analysis in this demo. We are going to find the 10 least popular songs present in the Spotify dataset. So I'll create a variable called sorted_df that will be equal to my data frame name, that is df_tracks dot. I'm going to use the sort_values function and say my column name is popularity. So I'm going to sort the values based on the popularity and then say ascending equal to true, since I want only the least popular songs. And then I'm going to say head of 10, which means I want the top 10 least popular songs. Now let's go ahead and print sorted_df. If I run it, you can see we have the list of 10 least popular songs on Spotify. You can see that popularity is 0, and you can see the names of the songs. Some of them are songs which are not in English language, and you can see the artist names as well. Cool. Now moving ahead, let's see some descriptive statistics for the numerical variables that are present in our column. So I'll say df_tracks dot describe, which is the function to get some descriptive statistics, and I'm going to use the transpose function after that. If I run it, there you go. So we have the statistics about count, mean, standard deviation, minimum value, 25th percentile, 50th percentile, 75th percentile, and the maximum value for these columns like popularity, duration in milliseconds. Then we have energy, key, loudness, mode. Cool. Now if you see this popularity column, the minimum value is 0 and the maximum value is 100, and you can see the 50th percentile is 27, which is essentially the median. You have the standard deviation as 18.37. Then similarly you can check for the other features as well. Cool. Now we'll see the 10 most popular songs which are greater than 90. So we are going to check for the top 10 songs with popularity greater than 90. Let me show you how to do it. So in this cell, I'm going to create a new variable called most popular, and I'll say df_tracks dot. This time I'm going to use the query function that is part of Pandas library again. I'll use the column that is popularity, and we'll set the condition popularity should be greater than 90. I'll give a comma and say in place equal to false, because I don't want to change my original data frame. And then I'll say sort_values, and I'm going to sort it based on popularity in descending order. So I'll say ascending equal to false, and then let's take only the top 10 popular songs. So I'll say most popular, use square brackets, and we'll then pass the slicing operator and say :10. Now if I run this, there you go. So here you can see the 10 most popular songs that is present in our Spotify dataset. So first we have Peaches by Justin Bieber, Daniel Caesar and Gibbon. Then we also have a song name called Driver's License, Astronaut in the Ocean, Save Your Tears. We also have The Business, Streets and Heartbreak Anniversary. So these are the most popular songs that are present in our dataset based on their popularity. You can see Peaches has the highest popularity with 100. Alright, now moving to the next cell. So here we are going to set the index to be release date column in the main data frame. So I am setting my index using the set underscore index function. I have passed in my column name as release date and I'm saying in place equal to true, which means I want to change it in my original data frame, and then I'm changing the value to date time format, and let's print the head of the dataset. So you can see here we have successfully changed our index. Now here you can see instead of 0, 1, 2, 3 we have the release date column and the rest of the columns are intact. Cool. Now let's move ahead. So suppose you want to check the artist at the 18th row in our dataset. You can use the index location method for that. Let me show you how to filter only specific rows of information from the dataset. I'll use my data frame df underscore tracks, and using double square brackets I'll say my column name, which is artist, and I'll use the index location method and say, let's say I want to check the artist who is present in the 18th row in my dataset. So I'll use ilog18. If I run it, the artist's name is Victor Boucher. Cool. Now let's move ahead. We are going to convert the duration in milliseconds to just seconds. So if you see our dataset, we have a column called duration in milliseconds. So all our songs are present in milliseconds. Let's convert them into just seconds. So for that, I'm using the lambda function and dividing the values in milliseconds by 1000 so that they get converted into just seconds. I have used in place equal to true, so I want to change it in my original data frame. Let's run it and do the necessary changes. Alright, now we'll print the head of the dataset just to check the duration column. So I'll say df underscore tracks dot duration dot head. If I run it, there you go. So you can see the values have now been changed to just seconds. Cool. I have the final quiz question for you. Who has the most monthly listeners on Spotify? Please put your answers in the comment section below. We'd be glad to hear from you. Now coming to the next cell. So here we are going to create a first visualization that is going to be a correlation map. We are going to drop 3 unwanted columns, and those are key, mode and explicit, and then we are going to apply Pearson correlation method. Now I have set my figure size to 14,6, and then we are using the Seaborn heat map function to create our correlation map. I have put the variable that is correlation underscore df. You can see above we had created this, and then I'm setting annotation equal to true. So this will write the data value in each cell. I have set fmt equal to .1g. So this is a string formatting code to use when adding annotations. Then I have set my vmin and vmax. So these are the values to anchor the color map. Otherwise, they are inferred from the data and other keyword arguments. CMap here stands for color map. You can just search for SNS CMap. You will get the documentation. So you can choose whichever color palette or the color map you want. Here I have used Inferno, and I have set my line widths and line color. Finally, I am giving a title to my correlation map, and I have set the extic labels. Let's go ahead and run this to get our first visualization. If I scroll down, there you go. We have got a nice correlation map. So here on the right side you can see the scale. It ranges from -1 to +1. -1 means the variables have least or negative correlation, while the values which are above 0.0 means that the variables have a positive correlation. Now here you can see there are values like -0.7 for energy and acousticness, which means if the energy is high, the acousticness is really low. Again, for loudness and say speechiness, if the song is loud, the speechiness is low, so there is negative correlation. But if you see for energy and loudness, there is really high correlation between these two variables. You can see the value is 0.8. So if the song is loud, this implies the song has really high energy and vice versa. Now if you see for a few other variables, there is negative correlation between acousticness and danceability. There is negative correlation again between valence and acousticness. Similarly, there is positive correlation between energy and valence, which is 0.4, and even for danceability and valence, that is positive correlation, which is 0.5. Cool. So from the correlation heat map, you can note that acousticness appears to have a strong negative correlation with energy. So if you see for acousticness and energy, there is a strong negative correlation, and there is a moderately strong positive relation between loudness and popularity. So if you see for popularity and loudness, the color is orange, which means it lies in this positive region. And there is also a moderately strong positive relation between danceability and valence. So if you check for danceability and valence here, there is a moderately strong positive correlation. Alright, now let's move ahead. We are going to sample our data and take just 0.4% of the total data, and we'll create 2 regression plots using this data. So let me first sample my data. So I'll create a sample data frame using my original data frame, which is df_tracks, and say sample. I'm going to use the int function and say 0.004 multiplied by the length of my original data frame, which is df_tracks. Alright, now let's run this and we'll print the length of my sample data frame. If I run it, you can see 0.4% of my total data set is 2346 rows. Cool. Now we are going to create a regression plot between loudness and energy. Now in our correlation map, we saw there was a positive correlation between loudness and energy, which was 0.8. Let's plot it in the form of a regression line. So I'll use plt.figure. I'll set my figure size equal to, let's say, 10,6. I'll say SNS dot regression plot. So I'm using the function called regplot, and I'll use my data as sample_df, give a comma, and say in my y-axis I'll have my column loudness, and in the x-axis we'll have energy. I'll give a color to my data variable. Let's say the color is C. Then I'll set my title to loudness versus energy. Let's say correlation. Alright. Let's make sure everything is fine. Now we'll run and see our result. There you go. So you can see here clearly there is a very high positive correlation between loudness and energy. On the y-axis we have loudness and on the x-axis we have energy, and you can see all the data points or the songs are in one direction. So if the energy increases, the loudness of the song also increases, and similarly if the loudness of the song decreases, your energy of the song or the track also decreases. So there is a very high positive correlation, and you can see the regression line here. It has gone and is increasing gradually. Cool. Now similarly, I'll just copy this code and we are going to see another regression plot, this time for two different features. Let's say we have popularity in the y-axis. So I'll say popularity, and then in the x-axis we have, let's say, acousticness. I'll change the color to, let's say, B, which stands for blue, and will set the title to popularity versus, I'll have acousticness correlation. Just scroll down and we'll run it to see the result. There you go. So I have the different points for the songs, and here you can see the regression line is downwards, which means if the acousticness of the song increases, the popularity decreases, and similarly if the popularity increases, acousticness decreases. You can see the downward trend of the regression line. Alright. Now in the next cell we are going to create a new column called year from our release date column, and I have changed this to date time format. Let me just run it. Cool. Now after that we are going to create a distribution plot to visualize the total number of songs in each year since 1922 that is available on the Spotify streaming app. So I have used my Seaborn library and dist plot function. Now one thing to remember, you need to update your Seaborn library to this version if you haven't done it. So use this command pip install --user Seaborn and the version. So here in the distribution plot we are going to plot a histogram. So I have used kind equal to hist, which stands for histogram. Let's run and see the result. Okay, so here you can see I have my distribution plot. So the plot tells us that the number of songs for each year in the dataset according to their release date have increased in the recent years since music became more accessible to people globally with technological advancements. So earlier you can see there were very few songs available in the 1920s. Later on the number of songs increased rapidly, and now you can see we have a lot more songs available for people to listen. Cool. Now we are going to see the duration of songs over the years. For that again we are going to create a bar plot. So I'll first create a variable called total duration equal to df underscore tracks dot, I'll use the duration column that we created, with seconds, and then I'm going to set my figure dimensions. So I'll use figure underscore dims for dimensions equal to 18,7. After that, I'll have my figure axis defined. So I'll use the Matplotlib subplots function, and I'll set the figure size equal to my figure dimensions, and then I'll say figure equal to SNS dot, I'll use the bar plot function and say my x-axis to be years, my y-axis will be total duration or total underscore dr that we created here. I'll set my axis equal to ax, and then I'll set error width equal to false. Let's set the title for my plot as title equal to year versus duration, and finally I'll say plt dot xtix. I'll rotate it by, let's say, 90 degrees. Alright, let me just recheck once if everything is fine, and then we'll go ahead and run it. I have my axis, error width, title. Okay, let me just run it. We'll see the result in a moment. If I scroll down, you can see we have the bar plot for the different years and the duration of the songs in seconds in the y-axis. So earlier in the 1920s, you can see the duration of the songs were less, and later it increased around late 1930s, and this remained consistent until 2010, where the duration was high. But after 2010, you can see the duration of the songs have started decreasing. Now in the next cell, I'm going to create a line plot to analyze the average duration of the songs over the years. It is going to be similar to our bar plot, just that now we are going to visualize it in terms of a line. So I have my code ready. You can see here I've used my Seaborn library and the line plot function. In the x-axis I have years, and in the y-axis I have total duration. I've set my title to year versus duration, and I'm rotating my x labels by 60 degrees. Let's run it and we'll see the output. There you go. Now if I scroll down, you can see we have a nice line plot, and on the x-axis you have the years, and on the y-axis we have the duration. You can see that the songs from 1920s to 1960s have comparatively shorter duration, since most of the songs tended to be more singing based rather than instrument based. After 1960s, you can see the duration of the songs started increasing until, I would say, 2010, and in the present day the duration of the songs have started declining, since the attention span of the average listener is also declining. Alright, now let's move to our second data analysis project, which is based on genres of the songs. So I am importing my dataset using the pandas read underscore csv function. I have given my location, and here I have my dataset name followed by the extension of the type. So this is a CSV dataset. Let's go ahead and run it. Okay, now let's print the first 5 rows of the dataset. I have stored my dataset in a data frame called df_genre. I'll use the head function to get the first 5 rows of information. I'll hit Shift Enter to run it. There you go. You can see here I have my genre column, artist name, track ID, popularity, acousticness, duration in milliseconds again, and we have the rest of the other columns that we saw in our first dataset. Just one thing to note, here key is present in terms of C, D, E, C minor, F minor, and not in terms of numbers between 0 to 11. Now we'll see the duration of the songs for different genres. For that, I'm going to create a bar plot. So I'll start with setting the title for my plot as duration of the songs in different genres. I'll use the Seaborn library and I'll set my color palette to, let's say, rocket. I'll give a comma and say as CMap equal to true. This would be color palette. Now I'll say SNS dot bar plot. In the y-axis I'll have genre, and in the x-axis I'll have my duration column, which is in milliseconds, so duration underscore ms, and then I pass my data frame using the data argument. So I'll say data equal to df dot genre. Next we'll set the x labels, so I'll say plt dot x label. Let's say my x label is duration in milliseconds, and then I'll say plt dot y label as genres. Now let's go ahead and run this. There you go. So here you can see we have the different genres on the y-axis, and on the x-axis you have the duration in milliseconds. And if you see the graph for classical genre and for songs that belong to world genre, the duration of the songs are more compared to other genres. Now if you check for children's music genre, the duration is less or the least. Cool. And finally we'll move to our last demo where we'll see the top 5 genres by popularity. So I'll say SNS dot set underscore style. I'll set my style to dark grid, which will be my background, and then I'll say plt dot figure. I'll set my figure size to 10,5. Then I'll create a variable called famous, since I want to take only the most popular songs based on the genre. So I have created a variable called famous, and I'll pass my data frame name, that is df underscore genre, and I'll sort the values based on my popularity column. So I'll say popularity, and I want to sort it in descending order, so I'll say ascending equal to false, and I'll take the first 10 values. I'll tell you the reason why I'm taking the first 10 values and not 5. Then I'll say SNS dot bar plot, and in the y-axis I'll have genre, in the x-axis we'll have popularity, and I'll give a comma, and using the data argument I'll say my data to be famous, which is this variable that we created, and then I'll set my title as top 5 genres by popularity. Alright, now the reason why I took head of 10 is because there are a few genres which are repetitive. So if you see this, we have children's music appearing twice, so hence we have taken 10 instead of 5. Let me just go ahead and run it. There you go. So here if I scroll down, you can see I have my top 5 genres based on the popularity. So we have dance, pop, rap, hip hop and reggaeton. So these are the 5 genres which are most popular based on the data that we have collected from Spotify.
We'll go through World Happiness Report 2021 using Python. World Happiness Report is basically a survey of state of global happiness that ranks various countries around the world. Some of the factors that are taken into consideration for the report are social well-being, work-life balance, life expectancy, and other life factors. It also focuses on the COVID pandemic and how it impacted people's lives. So in this tutorial, we'll analyze and visualize a data set and derive insights on World Happiness Report using Python libraries. So without any further ado, let's get started.
The International Happiness Day is celebrated every year since 2013 on 20th of March to emphasize the importance of happiness in the daily lives of people. So the United Nations Sustainable Development Solutions Network published the World Happiness Report on 19th of March 2021 that ranks the world's 149 countries on how happy the citizens perceive themselves to be based on various indicators. The happiness study ranks the countries on the basis of questions from the Gallup World Poll. The results are then equated with other factors such as GDP, life expectancy, generosity, etc. This year it focused on the effects of the COVID-19 pandemic and how people all over the world have managed to survive and prosper. So using this 2021 data, we will answer critical questions such as the top 10 most corrupt countries. We will plot a graph to understand how the happiness score is related to the freedom of making life choices. We'll look at the life expectancy of 10 happiest and 10 least happy nations. So these are a few examples, but we will explore more about the data in detail in our demo session. Let's get started. So first I'll show you the data set we'll be using in this demo. So this data has been collected from Kaggle. Let me show you that. So this is the CSV dataset that we have downloaded from Kaggle.com. So you can see here World Happiness Report 2021, and we will share the dataset link in the description of the video. You can click on the link to download the dataset. Now we have information about 149 countries. You can see it here, count is 149. Let me go to the top and I'll run through the columns that are there in this dataset. So the first column is the country name. So we have 149 different countries, and then we have something called as regional indicator. We can call this as just the region. So you can see we have different regions. I've applied a filter. We have Central and Eastern Europe. Then we have Commonwealth of Independent States. So these include countries such as Russia. Then we have East Asia, Latin America and Caribbean. We also have South Asia, Southeast Asia, Sub-Saharan Africa, Western Europe and other regions. I'll just cancel this. And then we have the happiness score column that has been sorted in descending order. So we have Finland, Denmark and Switzerland, who are the top 3 happiest nations. Now if I scroll down, we have countries like Rwanda, Zimbabwe and Afghanistan, which are the least 3 happy countries. Now there are a few columns that we won't be using in our analysis, so we will learn how to exclude those columns and keep only the relevant ones. So columns such as standard error of ladder score, then we have upper whiskers and lower whisker column, so we are going to ignore these columns. We are only concerned about the GDP column, which is this one. Then we have the social support or the social status column. Then we have the health life expectancy, freedom to make life choices, generosity and perceptions of corruption. And there are a few other columns you can see to the right, and these columns are not of our interest, so we are going to ignore them. Now let's head over to our Jupyter notebook and we'll start by importing all the necessary libraries for analysis and data visualization. Okay, so I am on my Jupyter notebook. So first step, I'll just rename this notebook to, let's say, happiness report data analysis. I'll click on rename. Alright, now we'll start by importing our libraries. So first library I'm going to import is NumPy as NP. Then I have import Pandas as PD. Then I'll import 2 data visualization libraries, Seaborn and Matplotlib. So I'll say import Seaborn as SNS and then import Matplotlib dot pyplot, which is the module name, as PLT, and I'll say percentage matplotlib inline. Okay, now let me just go ahead and run this. Alright. Well, now let's set the parameters that control the general style of the plots. The style parameters control properties like the color of the background and whether a grid is enabled by default or not. So for that, I'll say sns dot set underscore style. I'll give it as dark grid. Next, I'll say plt dot rc params, which stands for runtime configuration parameters. I'm going to set my font size to, let's say, 15. Then I'll say plt dot rc params. Now I'm going to set the figure size, so I'll say figure dot fig size. Let's say 10,7. Next, I'll just copy this, paste it here. Now we are going to set the face color, so I'll say figure dot face color. I want to set it to peach color, so I'm going to pass in my RGB values for peach. I'm going to set it in terms of hex code. So for peach, the value is FF E 5 B and 4. Now let me run it. Okay. Now it's time to load our data set. So for that, I'll create a variable called data and I'll use the pandas library followed by the read underscore CSV function, because our data set that we saw is a CSV dataset, which is this one. Now inside the parenthesis, I'll pass in the location of my data file. So I have my data here, World Happiness Report 2021. I'll just copy this location and will paste it here, and make sure the location is within quotes, and you need to change it to either / or double backslash. So here I'm using double backslash, so let me just include one more backslash, and then I'm going to pass in the file name, which is world happiness report 2021 .csv, which is the extension of the file. Now let me run it. Alright, now to display the first 5 rows of information, you can use the head function. So I'm writing data, which is my variable that holds the data frame. So data.head, there you go. You can see here we have printed the first 5 rows from the dataset. You have the country name, regional indicator, happiness score, then we have information about the GDP, life expectancy, generosity, then we have corruption data, and these are some of the columns that we are not bothered about, so we are going to drop these columns from our analysis. Now we are going to do that, so I'll create a variable called data columns, which are of our interest. So I am going to take only specific columns. I need the country name, so I have taken country name. Make sure the column names are within single quotes. So I have my country name. Next I want the second column, which is regional indicator. I'll give a comma. We also need the happiness score. Next I need the logged GDP per capita data, so I'll take that column. I'll say logged GDP per capita, give a comma. My next column would be social support, give a comma here. My next column would be health life expectancy, so I'll write health life expectancy. Let's give another comma, and we'll take the next column as well, which is freedom to make life choices. So I'll write that column name, freedom to make life choices. And finally we'll take the next two columns, that is generosity and perceptions of corruption. So within single quotes I'll say generosity, give a comma, and we're going to include the final column, which is of our interest, that is perceptions of corruption. Let me have a recheck to ensure that I have put the column names correctly, otherwise it will throw an error. Now let me go ahead and run this cell. I'll hit Shift Enter. Alright, so we have successfully taken the columns that we'll be using for an analysis. Now I'm going to say data equal to data. I'll pass in my new variable, that is data underscore columns, and I'm going to copy all the data. So I'll say dot copy. Let's run it. Okay, this should be data underscore columns. Alright, now let's rename all these columns. We'll make it more simpler and easy to understand. So I'll say, let's say my new variable is happy underscore dear, which stands for data frame, equal to, I'll say data dot we'll use the rename function, and using a dictionary we will rename our columns. So I have used a curly bracket. I'm going to pass in my first column, which is country name. I'll just paste it here. Then I'm going to give a colon, and again within single quotes I'll say country underscore name. So this is going to be my new column name. I'll give a comma. We'll take the next column, which is regional indicator. I'll paste it here, give a colon, and the new column would be small r regional underscore indicator. Now similarly we'll do this for all the remaining columns in the dataset. Okay, now I have renamed all my columns. You can see it here. Let's run it. Now we are going to display the head of the dataset again. So I'll say happy underscore df dot head. There you go. So we have only those columns that are of our interest. So I have the country name, regional indicator, happiness score, GDP, social support, life expectancy, freedom to make life choices. Then I have generosity and perceptions of corruption. Cool. Now we are going to check whether any of the columns have any null values. So for that I'll say happy underscore df dot, I'm going to use the isNull function. I'll give another dot, and we are going to find the sum for each of the columns. You can see from the data we do not have any null values in any of the columns in the dataset. It is all 0. Okay, now let's get started with our first visualization. That is, we'll create a plot between happiness score and the GDP for different regions. So for that I'll give a comment as plot between happiness and GDP. I'll just scroll down. Cool. First I'm going to set the RC parameters. So I'll say plt dot RC params. Within square brackets I'm going to give my figure size. So I'll say figure dot fig size equal to, let's say my figure size is 15,7. I'll set the title, that is plt dot title of my plot, to, let's say, plot between happiness score and GDP. Next I'm going to say SNS dot, let's create a scatter plot. So I'll say SNS dot scatter plot. I'm going to define my x-axis and the y-axis for the plot. Let's say in the x-axis we have my data frame happy underscore df dot, this should be an underscore. I'll say a column name as happiness underscore score, give a comma, and in the y-axis we'll have my data frame name, that is happy underscore df dot, we'll have the GDP column, that is logged underscore GDP underscore per underscore capita. Let's give a comma, and we'll pass in hue for the color. Let's say for hue I'm going to use the regional column or the regional indicator column. So I'll say happy underscore df dot regional underscore indicator. and then I'm going to give the size of the dots as, let's say, 200. Then I'll give a semicolon. Come to the next line. I'll say plt dot, let me just scroll down. Now we are going to define the legend. So I'll say plt dot legend, and in legend we'll have the location. Let's say I want to put the legend at upper left corner. So I'll say LOC, which is for location, equal to upper left. Give a comma and then say font size of my legend, let's say be 10. Make sure this is within quotes. Then I'm going to pass my x-axis labels and the y-axis labels. So I'll say plt.x label. Let's say the x label is happiness score and my y label is GDP per capita. So I'll say plt.y label. Within single quotes I'll say GDP per capita. There's an error here. There should be plot. Alright, so I have written my code to create a scatter plot. Let's run it and see the result. There is some error here. Okay, this should be regional indicator and not indicatory. There's a spelling mistake. Let's run it again. Alright, so here you can see we have a nice scatter plot. On the top you can see we have the title of the plot, that is plot between happiness score and GDP. On the x-axis we have the happiness score from 0 to 8 and above, and on the y-axis you have the GDP per capita. And if you see here, in this region we have countries from Western Europe which have the highest happiness score and the GDP per capita is also the highest. Around this region you can see here, which is for green, and in the legend you can see green is for sub-Saharan Africa. So all these countries have low happiness score and even the GDP per capita is also low. And if you see the countries for Latin America and Caribbean, you see a lot of the values lie here. So they are all within the range of 5.5 to 7 in happiness score, and even the GDP per capita is more than 9 for most of them. Now even the happiness score is high for the countries that lie in the North America and ANZ region, and even their GDP per capita is also the highest. I can name a few countries such as Australia, New Zealand. We have Canada and United States of America, which belong to the North America and ANZ region. Cool. Now there is one country which you see here. This seems to be like an outlier, which means that this is the country which has the lowest happiness score, and even the GDP per capita is also low, but it is not the lowest, because you can see here there are a few countries up here from the sub-Saharan Africa which have the lowest GDP per capita, but the happiness score is higher than this value or this country. So we can assume that this country is Afghanistan, which has the lowest happiness score as per the 2021 happiness report data. Cool. Now we'll plot a pie plot to understand the GDP by region. So by this we can know which region has the highest percentage contribution to the world's GDP as per our data. So for that I'll create a variable GDP underscore region equal to, we'll use our data frame, that is happy underscore df dot, I'm going to use the group by function, and after that I'm going to use my column, that is region. So we have named the column as regional underscore indicator, so I'm going to group it by this region column, and I'm going to sum the values of GDP. So I'm going to use the logged underscore GDP underscore per capita column, and after that I'm going to use the sum function, and let me just print GDP underscore region. You can see it here. We have the sum of all the countries for different regions and their GDP all total. Now this data we are going to plot it in the form of a pie plot. So I'll say GDP underscore region dot plot dot pie. We are going to plot it in terms of percentage. So I'm going to use a parameter called AutoPCT equal to, then I'm going to pass in my format. So I'll say percentage 1.1 f percentage, then I'll say plt dot title. Let's say the title of my pie plot is going to be GDP by region, and I'll say plt dot by label, which is going to be blank. Let's run it. Okay, so here you can see we have the peach background at the back because we had assigned a peach face color. You can see it here. So for the first scatter plot also we had the peach color at the back, and now you can see we have Sub-Saharan Africa contributing 20.7% to the world's GDP. The reason being we have around 34 countries in the Sub-Saharan Africa, and we have the Western European countries contributing to 16.2% of the GDP. To check the least, we have North America and ANZ region because we only have 4 countries: America, Australia, Canada and New Zealand. So hence they are contributing only 3.1% to the world's GDP. Okay, now moving ahead, let's find the total number of countries in each region. So for this we are going to use the group by function that is part of the Pandas library, and we'll count the total number of countries in each region. So I'll just give a comment as total countries. Alright, I'll just scroll down. So I'll create a variable called total underscore country. I'm going to use my data frame that is happy underscore df dot. I'm going to use the group by function. I'll group the values based on the region column. So within single quotes I'll say regional underscore indicator, and then I'm going to find the total count of country names. So I'm using the column country underscore name, and after that I'll just use dot count. Now let's go ahead and print my variable that is total underscore country. Alright, now let me hit shift enter. Okay, so here you can see. Alright, so for Sub-Saharan Africa there are total 36 countries and not 34 as I mentioned earlier. So hence you can see, because it has the highest number of countries, it is contributing the most to the world's GDP, that is 20.7%. Then we have the least number of countries in North America and ANZ, that is only 4. We have 6 countries in East Asia, and then we have 20 countries in Latin America and Caribbean, 12 countries in Commonwealth of Independent States, then we have 17 countries in Central and Eastern Europe. Cool. Now I'm going to show you how to create a correlation map so that we can see the relationship that exists between each of the variables that are present in our dataset. I'll just run through the code and we'll see the output. Okay, so here I have my code written for the correlation map that I want to create. So first of all, I'm going to compute the correlation matrix. So I have used the CORR function, which stands for correlation, and the method I'm going to use is Pearson method. Now here I have a Wikipedia page opened for Pearson correlation coefficient. So this is a nice article where you can understand what the Pearson correlation is all about. And then I'm going to set up the Matplotlib figures. So I have used the subplots function and I have given the figure size as 10,5, and after that we are going to draw the heat map with the mask. So I'm using the heat map function present in the Seaborn library, and then I have passed in my variable that is COR, which essentially stands for correlation. And then I have used mask, which is a Boolean array, or it can be a data frame, and it is an optional parameter. If it is passed, the data will not be shown in cells where the mask is true, and the cells with missing values are automatically masked. After that, I have used the CMap parameter, which stands for color map, so you can customize the colors in your heat map. And I'm going to create a heat map which is in square shape, so I have said square equal to true, and the axis I am going to pass it as AX, which I have defined here. So this is the Matplotlib axis and it is optional. So axis in which you want to draw the plot, otherwise you can use the current active axis. Now let me just go ahead and run this and we'll see the heat map. There you go. So if I scroll down, here we have the correlation matrix, and since I had given my CMap as blue, and here you can see it is mostly blue, and we have the scale here. Now I'll tell you how to read this correlation matrix. So wherever the cells are in blue or dark blue color, this means that the variables have very high correlation, and all these cells where you see light blue color or grayish and white color, this indicates that the variables have very low correlation. For example, there is very low or almost negative correlation between happiness score and perceptions of corruption. So obviously if the citizens of a country feel that there is a lot of corruption in the country, their happiness score would obviously be less or low. And if you see, there is also low correlation between happiness score and generosity. There is again low correlation between health life expectancy and perceptions of corruption. And if you see these places, there is really high correlation between the happiness score and GDP per capita. Again, for social support also there is very high correlation. Now if you see, even for social support and healthy life expectancy, there is very high correlation, but there is low correlation between making life choices and generosity, and there is negative correlation between corruption and freedom of making life choices. You can see it is almost white color, which means it falls around this region, so negative correlation. Similarly, for logged GDP per capita and corruption, there is negative correlation. Alright. Okay, now we are going to visualize a bar plot that will tell us the corruption in different regions. So I'll just give a comment: corruption in regions. Let me just scroll down. Okay, so I'll create a variable called corruption, which will be equal to my data frame, that is happy_df. Now first of all, I'm going to use the group by function to group all my regions. So I'll say regional_indicator, which is my column name present in the data set. And after this, I'm going to find the average of the corruption, that is perceptions of corruption. So I'm going to pass in my variable name, that is perceptions of corruption, and I'm going to use the mean function to find the average corruption in each of these regions. Now let me just go ahead and print my variable, that is corruption. If I run it, you can see here I have the values for the different regions, and from here you can see that Central and Eastern Europe has the highest perceptions of corruption as per the questions answered in the poll. And if you see the table, we have Western Europe and the North America region with the least perceptions of corruption. Now we are going to visualize this using a bar plot now. So first of all, I'll set my parameters by giving the figure size. I'll say fig size. It's rather figure dot fig size. I'll just add figure here. Okay, and now let's say I'll assign it as 12,8. Now I'll give a title to my plot, so I'll say plt dot title, and my title of the plot is going to be perception of corruption in various regions. Alright, then I'm going to define my X label. So I'll say X label will be regions, and we'll set the font size of the X label to, let's say, 13, or let it be 15. Then we are going to set the Y label. In Y label I'll have corruption index as the label name. Again we are going to set the font size to 15. Now I'm going to use X ticks parameter, since I want to rotate the axis labels in the x-axis by 30 degrees. So I'll say rotation equal to 30, and I'll say HA, which stands for horizontal alignment, equal to right. Make sure this right should be within single quotes. And finally I'll say plt dot bar, because I'm going to plot a bar graph. I'll say corruption dot index, comma, and then I'll say corruption dot perceptions of corruption, which is my column name. Alright, so I have my code ready for the bar plot. Now let me just go ahead and print the bar plot. Make sure everything is correct. I'll just hit shift enter. Okay, there is one mistake here. It says, okay, this should be X ticks and not X tick. Let me run it again. There you go. So if I scroll down, on the top you have the title, which is perception of corruption in various regions. On the x-axis you have the regions label, on the y-axis you have the corruption index. And if you see this, as per our table that we created, we have least corruption in North America and ANZ region. Then we have the next least corruption in Western Europe, but we have the highest corruption in Central and Eastern Europe as per their citizens' perception. Similarly, we have the second and third highest corruption in Latin America and Caribbean as well as South Asia. Cool. Now moving ahead, I'm going to show you how you can find the life expectancy of the top 10 happiest countries and bottom 10 happy countries. So for that I'm going to run you through the code and we'll see the visualization side by side. Okay, so I have my code written in these two cells. So first I'm going to find out the top 10 happiest countries, and then I'm going to find the bottom 10 happiest countries. So for that I'm using the head function, and I have passed in 10 since I want the top 10 country names. And to get the bottom 10 countries as per their happiness score, I am using the tail function. So let me just run it. So we have saved the result in two variables, top underscore 10 and bottom underscore 10. And to create the bar plots, we are using two different codes. So here you can see I have set my figure size and axis, and then I have my X label as country name. After that I am setting my title of the bar plot to top 10 happiest countries life expectancy. I've used my X tick labels and I'm rotating it by 45 degrees, and I have my horizontal alignment as right. You can see it here. We have used the bar plot function. I have the x-axis as country name and y-axis as healthy life expectancy column, and I have set my axis. Then I am using the X labels and Y labels as country name and life expectancy. And similarly I have my bar plot for the bottom 10 least happy countries life expectancy. Let's just run it and we'll see the result. There you go. Now if I scroll down, you can see we have two different bar plots. The first one is for the 10 happiest countries, and then we have the bottom 10 least happy countries. So if you see, on an average, the top 10 happiest countries life expectancy is above 70 years. So if you are from one of these countries, you are expected to live for more than 70 years. Now if you check the bottom 10 least happy countries, you see here Lesotho has less than 50 life expectancy age, and most of them are less than 60 years. So if you are from one of the top 10 happiest countries, you are expected to live 10 years more than these countries that lie in the bottom 10 region. Cool. Now moving ahead. Alright, so now we are going to see the plot between freedom to make life choices and the happiness score. For this I am going to use a scatter plot. So I'll first define my figure size. So I'll say plt dot rcparams, which stands for parameters. I'm going to pass in my figure size. So I'll say figure dot fig size equal to, let's say 15,7. Then using the Seaborn library and the scatterplot function, we'll pass in the x-axis. Let's say the x-axis is my data frame name happy underscore df, and I'll have the freedom to make life choices in the x-axis. So the column name is freedom underscore to underscore make underscore life and choices. I'll give a comma and we'll pass in the y-axis. Again I'm going to use my data frame name dot, and I'll have the happiness score. I'm also going to pass in a hue parameter to differentiate the different regions. So I'll say df dot regional underscore indicator, and I'll give the size of the dots or the bubbles as, let's say, 200. Now I'll say plt dot legend. I'll place the legend at upper left corner, so I'm giving the location, which is LOC equal to upper left, and font size, let it be 12. I'll say plt dot xlabel as freedom to make life choices, and my y label would be happiness score. Alright. Now we have the code written for the scatter plot that I want to create. Let me just run it. There you go. So here we have the legend for the different regions, and we have the different colors for each of these regions. And you can see here I have on the x-axis freedom to make life choices, and on the y-axis we have the happiness score. So you can see it very clearly. For the countries that lie in the Western Europe region, the blue dots, the freedom to make life choices is more, and so is the happiness score. Then if you see the values in the green region, which is for Middle East and North Africa, the freedom to make life choices is lower, and hence the happiness score is also low. And for all these countries that are part of the sub-Saharan Africa, some of them have decent score for freedom to make life choices, but the happiness score is low again. Now if you focus on the pink dots, which is for the Southeast Asian countries, the happiness score is comparatively lower, but the freedom to make life choices is more than 0.8. Cool. And again we have one data point which is lying at the bottom. We can assume this is Afghanistan. So in Afghanistan the freedom to make life choices is very low, and even the happiness score is really low. Cool. Now moving to our next analysis, we are going to see the top 10 most corrupt countries. So first I am going to sort the perceptions of corruption column and find out the top 10 countries in the list. So for that I'm going to create a variable called country. I'll have my data frame name, that is happy underscore df dot sort underscore values by, I'm going to sort by column that is perceptions of corruption dot head, and I want to find the top 10 most corrupt countries as per the poll. And then I'm going to pass in the figure size. So I'll say plt dot rc params, and then I'm going to set the figure size. So I'll say figure dot fig size. Make sure there is no spelling mistake. Let's say the figure size is 12,6. I'll pass in the title. So I'll say plt dot title. Let's say the title of my plot is going to be countries with most perception of corruption. After that I'll say plt dot x label. In the x label I'll have country, and I'll set the font size to 13. Then I'll say plt dot y label. In y label I'll have the corruption index. Next I'll pass in the font size for the y label, Again it is going to be 13. Now I'll say plt.x ticks. I'm going to rotate it by 30 and I'll say horizontal alignment equal to right, and then I'll have my bar function or the bar plot function. So I'll say plt.bar. I'm going to pass in country underscore name, and then we'll have a variable country dot the column name, that is perceptions of corruption. Alright, now if I run it, you can see here, so these are the countries with the least perceptions of corruption. So Singapore has the lowest corruption index, and then we have Rwanda, Denmark, Finland. Now if you want to see the countries with the highest perceptions of corruption, you need to change this head to tail of 10, since we are sorting it in ascending order. So we would want to know the bottom 10 countries. If I run it, there you go. So these are the countries with the most perception of corruption. You have Slovakia, Lesotho, Kosovo, there's Ukraine, Afghanistan, Bulgaria, Romania and Croatia. All of these countries have a corruption index of more than 0.85. Cool. Now coming to the final section of this interesting video on happiness report data analysis for 2021, I want to visualize a scatter plot that will tell us how the corruption varies in terms of happiness score. So I'll just say a comment as corruption versus happiness. Okay, so first of all I'll set my figure size. So I'll say plt.rc params. Within single quotes I'll give the figure size as 15,7. Then I'm going to use the scatterplot function that is part of the Seaborn library. In the x-axis I'll have my column that is corruption, or rather we'll have the happiness score in the x-axis. So I'll say happy underscore df dot column name, that is happiness score. Let me give a comma, and in the y-axis we'll have the corruption column. So I'll say happy underscore df dot perceptions of corruption, and then in hue we'll have the region, that is regional underscore indicator. So I'll say happy underscore df dot regional indicator, and I'm going to give the size of the dots. So I'll say s equal to 200. Then I'm going to say plt dot legend. I'm going to put it at lower left corner this time. So I'm giving my location as lower left, and the font size of the legend I want is 14. After that I'll just say plt dot x label as corruption and plt dot y label as happiness score. Now this should rather be the opposite, since in the x-axis we have taken happiness score. So we'll put the happiness score label in X and I'll have corruption in Y. Alright, so I have my scatterplot code ready. Let me just run it. There you go. So here you can see on the lower left I have the different regions, and on the x-axis I have the happiness score. On the y-axis I have the corruption index. Now you can see the general trend as per the scatter plot that the countries with greater happiness score have lower corruption index. So you can see these countries which are from the Western European regions have highest happiness score and their corruption is also really low. So all these blue countries, you can name a few: Finland, we have Sweden, we have Belgium, France, Netherlands, lying in these regions. We also have a few countries from North America and ANZ, which are essentially Australia. Then we also have Canada, US and New Zealand. Okay, now if you focus on these green region, this region, now these are the countries from the sub-Saharan Africa, and most of the countries from these regions have a very low or less than 5 happiness score, but the corruption is also really high. You can see here they have almost more than 0.7 in the corruption index. Now you also have a country here which is from the Southeast Asia. We would like to give you a task. It would be really great if you can tell us in the comment section which country is this. It has more than 6 happiness score, but the corruption index is really low, which is less than 0.2. Now if you consider Middle East and North African regions, the darker green countries, here also if you see the happiness score is less than 5 and the corruption index is also high. Now there are a few countries, the Commonwealth of Independent States, for example countries such as Uzbekistan, then you also have Kazakhstan, we have Russia, Armenia belonging to these grey color dots. You also have Georgia and Ukraine as part of Commonwealth of Independent States. So here you see the corruption is below 0.6 for these countries and the happiness score is more than 5. Alright, so with that we have come to the end of this demo session on World Happiness Report 2021 data analysis using Python.
And this time it's Olympic data analysis using Python. The dataset was taken from Kaggle, and we will use this dataset to learn how you can use different Python libraries to extract key details and make some conclusions. Without further delay, let's begin.
The Olympics is one of the biggest sporting events on the planet. It is held every 4 years. The first modern Olympics took place in Athens, Greece in 1896. As per National Geographic, the original Olympics took place in 776 BC. So they began as part of an ancient Greek festival which celebrated Zeus, the Greek god of sky and weather. The rings in the Olympics logo represent the 5 continents: Europe, Africa, Asia, the Americas and Oceania. From 1924 to 1992, the Winter and the Summer Olympics took place in the same year, but now they alternate every 2 years. Before I move on, here is an interesting question for you. Only 2 people have ever won gold medals at both the Summer and the Winter Olympics. Who are those 2 people? Please share your answers in the comment section of the video. We would like to know from you. The Summer Olympics in Tokyo began on the 23rd of July and recently concluded on the 8th of August. We got to witness some thriller matches that went down to the wire, some amazing victories, and sadly there were a lot of heartbreaks as well. Winning and losing are part and parcel of any game. Fans across the world were really happy to see this global event happen this year following last year's postponement due to the coronavirus pandemic. With our Olympic fever high, let's take this opportunity to work around a project to perform exploratory data analysis using Python to analyze and visualize past Olympics data and answer specific questions. In this video, we will be using specific Python libraries such as NumPy, Pandas, Matplotlib and Seaborn to make sense of our data and extract meaningful information. We are going to visualize our results with different charts and graphs. Before I show you the dataset that we are going to use for our analysis, I have another general question for you. Which is the first Olympics where all the participating countries sent female athletes? I repeat, which is the first Olympics where all the participating countries sent female athletes? Put the year and the city name where the Olympics was held in the comment section of the video. We'll be more than happy to hear from you. Now, let me go ahead and show you the datasets that we'll be using in this video. So here you can see I have my Olympics dataset folder that has two datasets. These are CSV files. One is called the athlete_events and the other one is called NOC_regions. So we'll be using these two datasets. These datasets can be downloaded from Kaggle. We will post the dataset links in the description of the video. Please go ahead and download them. These datasets have been directly taken from the internet. Now I'll show you the datasets. So this is my first dataset. You can see on the top athlete_events. So I have around 15 columns. You can see the count here, and there are nearly 2,71,116 rows of information. So this is a huge dataset that we are going to use. The other dataset we are going to use in this demo is called NOC_regions. Now here one thing to note is NOC stands for National Olympic Committee. This is a 3-letter code that is given by the Olympic Committee. You have the region names, so AFG is for Afghanistan, you have ALB for Albania, ALG for Algeria. We have also a column called notes. You find some notes about the region. For example, here Antigua is actually Antigua and Barbuda. Alright, let's move to the first dataset that I showed you. This is our primary dataset for our demo. So these datasets have been directly taken from the internet and were not validated. So the results that you will see in the demo is purely based on the data that we have collected. So the file athlete_events.csv contains nearly 2,71,116 rows of information and there are 15 columns. So each row corresponds to an individual athlete competing in an individual Olympic event. So here ID is actually a unique number for each athlete. Then we have the name, which is basically the athlete's name. We have the sex or the gender, which is male or F for female. Then we have the age of the athlete, which is in terms of integers. We have the height in centimeters of the athletes. Then we have the weight in kilograms. We have the team name. These are the country names. You have China, Denmark, Netherlands. There are around 200 country names. Then we have the NOC. As I said, NOC is a 3-letter code that stands for National Olympic Committee. We have the games. This games contains the year and the season. You can see here 1992 summer. You also have the Winter Olympic information. Alright. Then we have a specific year column to tell you in which year this event had occurred. Now the year column is also an integer column. We have the season, so whether it was Summer Olympics or Winter Olympics. Then we have the city name. This is the host city. Then we have the sport name. You can see here we have basketball, judo, football, tug of war, speed skating. There are so many. Then we have another column called event, which is the complete event name. As you can see, the sport name is basketball, but the event name is basketball, men's basketball, to be very specific. Again, for speed skating, you have different categories like women's 1000 meters, 500 meters. Alright. Now the final column is the medal column. So it has the information about the athlete, whether the athlete had won a medal, be it gold, silver, bronze, and NA means the athlete did not win any medals. So we'll use these two datasets. Now let's get started with the demo. We'll be using Jupyter Notebook for our analysis. So I'll take you to my Jupyter Notebook right away. I have opened it on Chrome. So this is my Jupyter notebook that we are going to use. You can see here Olympics dataset analysis. I have already have a few cells that have been filled with some piece of code, and you can see there are some comments written as well. We are going to use this dataset. So let's get started. First and foremost, we'll import the datasets. So we are going to use NumPy, Pandas, Matplotlib and Seaborn. Let me hit Shift Enter to import all the libraries. Alright, now the next thing is to load the datasets using Pandas read_CSV function. So I'll create a variable called athletes. I'll say equal to pd dot, I'll use the read_CSV function, and inside this function we'll give the location of the files. So I'll copy this location and here I'll paste. Make sure this is within quotations, and these are all forward slash. I'll give another forward slash, and after that I'll give the file name, that is athlete underscore events dot csv. I'll close the quotation. Let's run it. Okay. Similarly, we will load the second data set. I'll create another variable called regions. So it will have my data frame. I'll use the same function pd.read_csv. I'll just copy this file path till here. We'll paste it, and I'll give my second file name, which is noc_regions.csv. You can verify here. The first one is athlete_events, the second one is noc_regions. Okay, I'll close the quotation and we'll run it again. Okay, there seems to be some error. I think this is the regions. Cool. Now moving ahead, let's see the first few rows of both the datasets. I'll use the head function for that. I'll say athletes.head. So this will print the first 5 rows from my dataset athletes. You can see here from 0 to 4 you have 5 rows of information: the ID, name, sex or the gender, age, height, weight. If I go to the right, you have games, year, season, sport, event and medal. Now let's see the second dataset that we imported or loaded. I'll say regions.head. It says regions is not defined. Let me cross check it. Okay, I have taken it as region. Let's make it regions. Cool. Now let's run it. There you go. So these are the first 5 rows from our second dataset. You have NOC, region and some notes. Alright. Now the next step is to combine both the datasets. So we'll join the data frames using the pandas merge function. Let me show you how to do it. So this is going to be a horizontal join. I'll create a variable called athletes_df. Then I'll use my first variable, which is athletes. I'll say dot merge, which is my function name. I'm going to merge the regions data frame. I'll use the how parameter. In how, I'll give my value as I want to do a left join, and my common column in both the datasets is actually NOC. So I'm going to use the NOC column as my common column to merge both the datasets. Now let's go ahead and print the merged data frame. I'll say athletes_df.head. Let's run it. There you go. So if you see clearly, if I move to the right, you can see here we have added 2 more columns that were present in the second dataset, which was regions. So we have regions and nodes added to my first dataset, that is athletes underscore events. Cool. Now one thing to note here is, see, the column names are not consistent. If you see here, the rest of the columns start with a capital letter, but if you see the last 2 columns that we just added now start with a lowercase letter. So we'll use the rename function to make the column names consistent. But before that, let's see the shape of the data frame. So I'll print the shape of the data frame to know the total number of rows and columns. I'll say athletes. If I hit tab, you will see it will give me the prompt. I'll select athletes underscore df. I'll use the shape attribute. Let's run it and see the result. You can see here it gives me the total number of rows, so 2,71,116 rows, and earlier we had 15 columns in the first dataset, and now that we have added 2 more columns, so the total number of columns becomes 17 now. Cool. So now it's time to make the column names consistent. So I'll show you how to do it. I'll say athletes underscore df dot, I'll use the rename function, and then I'll say columns equal to, I'll use curly braces, my first column, that is region. I want to change it to region, but the R should be capital now or uppercase. I'll give a comma and then say my second column, this should be region actually. My second column, that is nodes, I want to change the first letter to uppercase, so I'll say capital N. The rest all remains same. I'll give a comma here and say in place equal to true. So it will change the column names and will reflect in this athletes underscore df data frame. Let's run it. Now to verify, you can again use the head function. I'll run this again. Let me scroll down and move to the right. You can see the difference. There you go. So we have successfully renamed the last 2 columns, region and nodes. Alright. Now moving ahead. Now I'll show you how you can use the info method to print information about a data frame, including the index data type, the column data types, non-null values, and memory usage. So for that you just need to use the info function. So I'll write athletes underscore df dot info. Let's run it. There you go. So here we have the data columns. You can see total 17 columns. You have 2,71,116 rows or entries. Then you have the different column names, and it says non-null and the data type of the column. Below you can see some information about the memory usage. Alright. Next, the describe method is used for calculating statistical information such as mean, standard deviation, the percentiles of the numerical values of the data frame, and much more. It analyzes both numeric and object series and also the data frame column sets of mixed data types. So let me show you how using the describe function you can display some statistical summary. I'll just write describe and give parenthesis. Let's run it. Okay, if I scroll down, you can see here by default the describe function will only give information about numerical columns. So here you can see we have the total count, the mean of each of these columns, you have the standard deviation, the minimum and maximum value, and then we have the 25th percentile, the 50th percentile, and the 75th percentile value of the columns ID, age, height, weight, and year. Alright, now one thing to notice here is, if you see the year column, the minimum year is 1896. So this is when Olympics started, and until recently the Rio Olympics that was held in 2016. Alright, now moving ahead, now let's check if there are any null values present in the columns of the dataset. So first I am going to create a variable called nan values, give equal to, I'll say athletes underscore df, and the function to check is, I'll say is na. I'll create another variable called nan underscore columns, and here I'll use the any function. I'll say nan underscore this variable, which is underscore values dot, I'll say any, and I'll print my nan columns variable. So this will display the result in terms of Boolean values. So if there are any null or nan or missing values in any of the columns, it will say true, otherwise it will say false. Let's display the result. There you go. So if you mark here clearly, so there are nearly 6 columns where we have missing values. You have age, height, weight, medal, region, and notes columns that have missing values, so hence it has given us true. The rest of the columns do not have any nan or missing values, hence they are false. Alright, let me scroll down. Now let's see the total number of null values for the above 6 columns. So I'll say athletes underscore df dot, I'll use the function is null, and again I'll use the sum function. Okay, this should be is null. If I run it, you can see it here. So our age column has 9474 rows where we have null values. Then we have some null values for the height column as well, for the weight column. So these are the total number of rows where we don't have any information regarding age, height, weight, or region. Notes, this medal is self-explanatory because a lot of the athletes who participate in Olympics don't win any medals, so for them the value is NA. Now before I move ahead, I have a question for you people. So the question is, I want you to print the column names containing null values or missing values in the form of a list. So please answer this question and put it in the comment section of the video. We would be happy to know your approach. So the question, I'll repeat it again. I want you people to print the column names containing null values or missing values in the form of a list. So basically on the top we saw there were 6 columns that had null values. I want you to print these 6 columns in the form of a list. Alright, now moving ahead. Now let's see the data for specific countries. Let's say you want to see the athletes who have participated in the Olympic Games from the beginning for India. For that, you can filter your result using a function called query. So let me show you how to do it. I'll say athletes underscore df dot, we'll use the query function, and then I'll say team, which is my column name, should be equal to, and the value I'll give is India. Now let's display the first 5 rows of information or the details for the athletes who are from India. If I run this, okay, there is some error here. Okay, so we need to make sure this entire expression or the condition should be within single quote. I'll just delete this single quote from here and we'll add it in the end. Now let's run it. There you go. So here you can see we have the top 5 rows of the athletes who are from India. You can see here the region is India, you can see the NOC is India, the team is India, and let me go to the left. You can see the name of the athlete, the sex, age. So for age you have some missing values, you have the weight, team, year and everything. Alright. Similarly you can also check for Japan. Let me just copy the above code. I'll paste it here and instead of India I'll say Japan. I'll run it. There you go. So if you see here, you can see all the details are for the athletes who are from Japan. Alright. Now moving ahead. Now I want to know the top 10 countries who have participated since the inception of Olympics in 1896. So for that I'll create a variable called top_10_ countries. I'll say equal to, I'll use my data frame that is athletes_df. I'll say dot team, then I'll use the function value_counts. I'm going to sort my count in ascending order. Just mark the way in which I'm writing the functions. Any error in terms of syntax or the flow will throw you an error. I want to display the top 10 countries. Now let's go ahead and print it. I'll say top_10_ countries. Alright, let me run it. Okay, it has given us an error. Let's debug it. Okay, so this should be value counts and not count. Let's run it again. Another error. Okay, so this should be short_values and not value. Let's run it again. There you go. So here you can see the top 10 countries participating in Olympics since 1896. You have United States, then we have France. So these are the number of participants who have taken part since 1896. So the most number of participants have come from US, then we have France, Great Britain, Italy, Germany, Canada, Japan, Sweden. We also have Australia and Hungary. I'll scroll down. Now we are going to convert this table that we got or the output that we got in the form of a graph. So I'm trying to create a bar plot to plot the top 10 countries who have participated in Olympics. So here I'm using the figure function to give the figure size. So these are the dimensions 12,6. Now I'll tell you what this PLT_x means. Just wait for a while. I have given a title to my plot saying overall participation by country, and then using the Seaborn library and the bar plot function I am plotting the x and the y-axis. So my x-axis has top. I should make this top 10 countries because above we used top_10_ countries. Similarly for y-axis I'll make it top_10_ countries, and then I'm using a color palette called set2. Let's run it. There you go. So if I scroll down, you can see here we have a nice bar plot. This is a vertical bar plot, and here you can see the bars which represent the different country names. First we have United States, which has the highest participation since the beginning of the Olympics. Then we have France, Great Britain, Italy, Germany, Canada, and we have the rest of the countries. Cool. Now moving ahead, the next visualization we are going to see is the age distribution of the athletes. So for this, we are going to create a histogram. I'll be using the Matplotlib library specifically for this visualization. So I'll say plt.figure will give the figure size using the argument fig size equal to, and this will be a tuple actually. My size is going to be 12,6. I'll say plt dot title. Now you can give any title that you want. I'll say age distribution of the athletes. Then we'll also give the x labels. I'll say plt dot x label. This will have age. Then we'll say plt dot y label, and this will have the label as number of participants. Next, I'm going to use the hist function, so I'll say plt.hist, and I'll pass in my data frame, that is athletes underscore df dot age, which is my column name, comma, I'm going to pass in the bins. For that I'm going to use the np.arange function, so np is for numpy, and inside this I'll say 10, 80, 2. So my bins will start from the value 10 and go until 80 with a size of 2, comma, I'll give another parameter that is going to specify the color of the bins. I want my color to be orange, and then I'll use the edge color to separate the bins. I'll say edge color, this is the parameter or the argument name, and the color I want is white. Let's give a semicolon here, and this should be edge color. There's a spelling mistake here. Now let's run it and we'll see the output. So there you go. So this is a nice histogram that shows the distribution of the age of the athletes. You can see the title age distribution of the athletes. On the y-axis you have the number of participants. On the x-axis we have the age values ranging from 10 to 80 with a size of 2. And if you see this, we have most number of athletes who have an age between 20 to 30. You can see here. So early 20s we have maximum number of athletes participating in the Olympics. We also have a few athletes who are beyond 40 years of age. You can see here we have a few athletes even closer to 60 also, and similarly we have a few athletes who are under 18 years of age. Alright, now you can see here the bins we had taken orange color, so all the bars are represented in orange color, and the edge you can see here we have the white color. Alright, now moving ahead. Now in the initial slides of the video we discussed the summer and winter Olympic Games. Let's look at the different sporting events that are part of the summer and winter Olympic Games. Just to give you a heads up, the winter Olympic Games are held once every 4 years for sports practiced on snow and ice. So here I have my variable name winter underscore sports, so I'm extracting for season equal to winter, and I am going to display only the unique values. Now let me run this cell. Okay, so you can see here these are the different winter sports that are held during the winter Olympics. Now similarly, let's see for summer Olympics. So what I'm going to do here is I'll just copy this cell of code and we'll edit the variables. I'll say summer underscore sports, athletes underscore df remains the same. Here season we'll change it to summer. Dot sport dot unique remains the same, and here I'll say summer underscore sports. This should be small. Now let's run it. There you go. So here you can see we have more number of Olympic sports that are held during the Summer Olympics compared to Winter Olympics. So these are the sports that are played on snow and ice, and these are the sports that are played during summer. Moving ahead, now it's time to analyze the total number of male and female participants who have taken part in different games since 1896 till 2016 Rio Olympics. Alright, so I'll say gender underscore counts, which is my variable name. I'll use my data frame, that is athletes underscore df dot my variable name, that is sex, dot value underscore counts, and then we are going to print gender underscore counts. Let's run this. There you go. So since the inception of Olympics, we have more number of male participants than female participants. Now here in this current cell, you can see we are trying to plot a pie chart for male and female athletes. So I have given my figure size, then I have my title as gender distribution. I'm using the Matplotlib library and the pie function. I'm using the variable gender counts that we used here. Then I'm giving my labels as gender underscore counts dot index. Now I'm using this auto PCT. The auto PCT parameter enables you to display the percent value using Python string formatting. So this is my string formatting that I have used, and I'm initialized my start angle for the pie chart as 150 degrees, and I'm also giving shadow to my pie chart. So I have written shadow equal to true. Let's run it. Alright, so you can see here this is my pie chart that shows you the distribution of the male and female participation. So for male it is 72.5%, for female so far it is 27.5% as per the dataset that we have. Now you can change this start angle to, let's say, 180 degree, and it will change the pie chart to this direction. Cool. Now moving ahead, this time we are going to find the total number of medals that the athletes have won. So I'll use my data frame athletes underscore df dot, and then my column, that is medal, I'll say dot value underscore counts. Let's run it. There you go. So you can see the gold medals, the bronze medals, and the silver medals are very much similar to each other. The numbers are pretty much the same. Alright, now it's time to focus on the total female athletes who have taken part in each Olympics. So I'll create a variable called female underscore participants. I'll say equal to, and then use my data frame name, that is athletes underscore df. Using square brackets, I'll say athletes underscore df dot the gender should be equal to female, and I'll use ampersand. I'll say, just copy this, paste it here. I'll say dot season equal to, we'll check for Summer Olympics, and I want to extract only the gender column. So here it is sex, comma, my year column, which is year. Okay, and then I'll say female underscore participants equal to, I'll just copy this, paste it here, and then I'll use the group by function, say group by, which is part of the pandas library. I'll say year, and then I want to find the count. I'll reset the index, say reset underscore index is a function, and finally we are going to print female underscore participants, and let's say the head. Alright, so what we are trying to do is I'm trying to filter my data only for the female athletes for Summer Olympics, and here I am printing the participation based on each year, so I'm finding out the count. So here we need to add one more square bracket. Alright, now we'll run it and see the result. There you go. So you can see here from 1900, 1904, all these years you can see the female participation. Let me change it to tail so that we have the recent data of the Olympics. You can see it here for the Beijing Olympics, 5,816 women athletes participated. In 2012 London Olympics we had 5,815 Olympics. Similarly for the 2016 Rio Olympics we had more participation than the London Olympics, so 6,223 women athletes had participated. Alright, now here this is another way in which you can filter your data for female athletes. So I'm using two parameters. My gender should be equal to female and season is Summer Olympics. Let me just run it. I have stored it in a variable called Women Olympics. Now here I am trying to find a count plot, or I am trying to create a count plot using my Seaborn SNS library. I have set my style to dark grid, then my figure size I have given as 20,10. My count plot will have the x-axis as year, the data is Women Olympics, and palette I am using as spectral, and then I have given a title Women Participation. Let's run and see the output. There you go. If I scroll down, you can see on the top I have the title for my count plot which says Women Participation, and on the y-axis I have the count, and at the bottom you can see the different year values from 1900 till 2016, and 2016 had the highest number of female participation. Cool. Let me scroll down. So in this cell of code we are trying to plot a line graph. Let me run it and show you the output. So this line graph shows the trend which says plot for female athletes over time. So here you can see the line graph. So gradually the women participation has increased in Olympics since its inception. There was a slight decrease here. This is around 1950s, and again you can see here there's a decrease with the women participation in 1980, but since then, since 1980, there has been continuous increase in the participation of female athlete numbers. Cool. Now coming to the next section of our analysis. Now we are going to filter the data to see the details of the athletes who have won gold medals. So I'll create a variable called gold medals. It's equal to, I'll use my data frame as athletes underscore df, and within parenthesis I'll use my data frame name which is athletes underscore df dot, I'll use the condition medal equal to, and my value would be gold. Next I'm going to say gold medals dot head. Let's run it. There you go. So here we have the top 5 rows of the athletes who have won a gold medal. You can see all the records have medal as gold. Now we are going to use this subset of the data and perform some more analysis. So here I want to take only the values that are different from NaN. So I'm going to use is finite function, and inside that I have set gold medals age. Let me just run it. Cool. Now I want to see the athletes who have secured a gold medal beyond the age of 60 years, which is very rare. So we'll see the total number of athletes with more than 60 years of age having won a gold medal. So here I'm going to say gold medals. I'll use my column as ID, and then I'll use my variable gold medals, and then I'll say age should be greater than 60, and then I'll close my square bracket and say count. Okay, let me just verify if everything's fine. Yeah, I'll run it and we'll see the result. So there are total 6 athletes who have won a gold medal having age more than 60 years. Cool. Now let me check for which sport these 6 gold medals have come. So I'll say sporting underscore event. This is going to be my variable name, equal to, I'll use the same variable name, gold medals. I'll going to choose my sport column, and then I'll give my condition age greater than 60. Now let's go ahead and we'll print the variable sporting event. If I run this, you can see it here. So for art competitions, even for archery and shooting, and this one called rook, we have had gold medals from athletes who had an age more than 60 years. Now we are going to plot this result or the table that we achieved on the top. So I'll say plt dot figure. I'll give my figure size equal to, let's say 10,5. Then I'll say plt dot, we'll use the tight layout, say tight underscore layout. Then I'm going to use the cbound library and create a count plot for my variable sporting underscore event. Then I'll say plt dot title. I'll give the title as gold medals for athletes over 60 years of age. Let's run it, and if I scroll down, you can see here we have a nice count plot. I have my title gold medals for athletes over 60 years, and since for archery we had 3 players who secured a gold medal having an age more than 60 years. You can see here archery is 3, art competition 1, rook is 1, and shooting we had 1 medal. Alright. Now we'll see the total gold medals from each country. So for that, I'll say gold medals dot, we'll use the region column, and followed by that I'll use the value underscore counts function, and I'll reset the index with name equal to, I'll provide the medal column. Then we are going to print the head for the top 5 countries. Let me run it. You can see it here. So USA has secured the most number of gold medals. Then we have Russia, Germany, UK, and then we have Italy. Cool. Now in this cell I am going to create a plot to visualize the table that I got above. So I've used my labels, my titles. I'm using the cat plot function that is present in the Seaborn library. I have my x-axis, my y-axis, the data which is total gold medals. Let me just verify. Okay, and we'll run it. If I scroll down, you can see this is a different palette that I had used, which is a rocket, and you can see USA has got the most number of gold medals. Then we have Russia, Germany, UK, Italy, and France. Now we also have included France here, which was not present in this table. The reason being I have used head as 6, so it will give me the top 6 countries. Alright, now we will analyze and look at the data for the most recent Olympic event that is present in our dataset. I'm talking about the 2016 Rio Summer Olympics. So first of all, I'll create a variable called max year, which will be equal to my data frame name athletes underscore df, my column name year, and I'll use the max function. Then let's go ahead and print my max year. I'll just show you the output. You can see here my max year present in the dataset is 2016, the Rio Olympics. Next, we will create another variable called team underscore names that will be equal to my data frame name athletes underscore df. Within square brackets, I'll give parenthesis and then say athletes underscore df dot year should be equal to my output, that is max year, which is actually 2016, and then I'll say ampersand. I'll just copy this, we'll paste it here. This time I'll use the medal column and say equal to gold. I'll say dot team, then I'll say team underscore names dot value underscore counts dot head, and will display the top 10 countries. Let me run this. There you go. So in Rio Olympics, United States secured the most number of gold medals. Now the reason this is 137 is we have also counted the team events, for example basketball. Similarly, Great Britain had 64 gold medals in total, Russia 50, we have Brazil 34, Argentina 21, France 20, and Japan 17. Alright, now using the above result, we are going to create a bar plot. I'll just change this team underscore list to team underscore names. Similarly here also I'll make the corrections as team_names. Cool. Now we'll run it, and you can see here we have a nice horizontal bar plot. So we have United States at the top, Great Britain, Russia, Germany, China, Brazil. So here I am displaying the top 20 nations since I have used head as 20. So these are the top 20 nations who secured the most number of gold medals in the Rio Olympics. Alright. Now in the final section of this video, we will create a scatter plot to visualize the height and weight of male and female athletes who have won a medal. Now it can be a gold medal, a silver medal, or a bronze medal. But before that, we need to filter the data only for athletes who have won a medal. Now if you had noticed here, our medals column also had a few null values, so we are not going to consider those null values here. We are only going to consider for the athletes who have won a medal. So for that, I'll create a variable called not_null_medals equal to, I'll say athletes_df, then I'll give my, let's make it df, I'll give my condition. Let me just copy this, I'll paste it here, and then I'll give my condition height and use the not_null function, and then I'll say ampersand, create another parenthesis, I'll say athletes_df. This time we'll consider the weight column. Again, I'll use the function as not null, and I'll close the parenthesis. Okay, I had missed one S here. Cool. Let me just run it now. Alright. Now we are going to create our final plot. I'll say plt.figure. I'll give my figure size equal to, I'll say 12,10. I'll say axis equal to SNS dot. We'll be creating a scatter plot to plot the height and weight of the athletes who have won a medal. I'll say scatter plot. In my x-axis I'll have height, comma, in my y-axis I'll have weight, comma, my data should be not_null_medals. So this is what we created here, not_null_medals, comma, I'll use hue equal to my sex column. Cool. Finally, I'll say plt dot, I'll give a title to my plot saying height versus weight of Olympic medalists. Cool. Now let's see our scatter plot. This might take some time to give the result because there are so many athletes present in a dataset who have won a medal, and also we are filtering in terms of hue, which is for male and female. There you go. So if I scroll down, you can see here we have a nice scatter plot On the top we have the title of the plot saying height versus weight of Olympic medalists. You can see our age as the hue. So blue points are for the male athletes and orange points are for the female athletes. And on the y-axis we have the weight in terms of kilograms, and you have the height in terms of centimeters. Cool. So that brings us to the end of this demo session on Olympics dataset analysis. So we used two datasets to carry out this exploratory data analysis, and we created some visualizations to analyze and visualize the data. Alright.
As you guys know that IPL is a cricket league played by different franchises across the nation over a period of 2 months. So in this tutorial, we'll go through some of the performances and statistics of different IPL teams and players. We'll export different data sets and try to derive meaningful insights from it. We'll also create beautiful data visualizations like graphs and plots using these data sets. Without any further delay, let's get started.
So in this video, we'll be using two datasets to perform our analysis. Now let me show you the CSV files. So this is my IPL dataset folder which is on my desktop, and these are the two files that we are going to use. The first dataset has information about matches played between 2008 and 2020. Let me open this dataset. Alright, you can see here there are total, let me just go to the top and I'll show you the number of rows we have. We have around 817 rows of information. Alright, you can see this is the match ID. So these are all unique IDs of the matches held between 2008 and 2020. Then we have the city in which the match was held. We have the date on which the match was played. We have the player of the match, which is man of the match basically. Then we have the venue column, that is the name of the stadium where the match was conducted. We have a column called neutral venue, whether the venue is neutral or not. Then we have the teams, team 1 and team 2. We have information about who won the toss. Then after winning the toss, whether they decided to field first or bat first. Then we have the winner who won the match. We have the results, whether it was won by runs or by wickets. Then we have the margin. So these big numbers are basically runs, 140, 33, all these are runs. If you see here, one of the match was a very close contest where the winning team won by just 6 runs. We have information about whether the match was an eliminator or a league match. We have a method, whether there was any DL method applied for deciding the result. And we have information about the 2 umpires. These are basically field umpires. Next, coming to the second data set. Now in the second data set, let me open it. Alright, so this dataset has all the information for each ball bowled since 2008 till 2020. You see you have the match ID, then we have the information about innings, whether it was a first inning or a second innings. We have which over it was, then we have which ball it was, basically the number of ball in an over. Then we have the batsman who faced the delivery. Then we have the batsman who was at the non-striker end, or the player who was at the non-striker end. Then we have information about who the bowler was and how many runs were scored of that ball, whether there were any extra runs, and the total runs that were scored in each ball. We have whether it was a boundary or a non-boundary. Then we have whether there was a wicket taken in that delivery. Now we have information about player dismissed. Let me apply a filter and show you the values that we have. You can see here these are the players who have been dismissed. Now similarly, let's see for extra types. You have byes, leg byes, no balls, penalty, wide deliveries. Then we have the batting team and the bowling team. Alright. So we will be using these two data sets to perform exploratory data analysis and answer particular questions like the total number of matches played in each season, the total number of runs scored in each season, We'll also look at the number of tosses won by each team, the toss decision for each season. Then we'll see whether the team opted to bat or to field first after winning the toss. We'll also understand how a certain player has performed so far in IPL, the player who has scored the most number of runs, and who has won the most number of Man of the Match awards. Alright, so let me take you to my Jupyter notebook. So this is the Jupyter notebook we'll be using for our demo. I have already written a few lines of code. You can see it here. Alright, so let's begin with the first step, which is to import the necessary libraries. So to perform our data analysis on the IPL dataset, I would need the NumPy library for numerical computation. We'll also need Pandas library, so I've imported it as PD and NumPy as NP. Then we have two visualization libraries, Matplotlib and Seaborn. The next step is to load the dataset. So here I am loading two of my datasets, which is match_data and the balls dataset. So to load the dataset, I'm using Pandas library and the read_csv function, and within this parenthesis I'll pass in my file location followed by the file name and the extension of the file. So here I have my dataset. Now let me copy this location and I'll paste the location here. We'll convert all the backslash to /, and finally I'll give my dataset file name. Let me just copy it and I'll paste it there. Okay, followed by the file name extension, which is .csv. Now I will just copy this, and similarly I'll paste for my second dataset. We'll replace the file name. I'll copy this file name and I'll paste it here. Okay, now let me go ahead and first run the first cell to import all the necessary libraries. You can see we have successfully imported all the libraries. Then let's run the second cell, which is to load the datasets. So the first dataset, which is IPL matches, I'm storing in a variable called match_data. This will be stored in the form of a data frame. And the second dataset, which is IPL ball by ball, I'm storing in a variable called ball_data. Let's run it. Okay, there is some error. Alright, we need to put these within double quotes. Don't forget to put the location on within double quotes, otherwise it will throw an error. Now let's run it again. There you go. So I have successfully imported my datasets. Now let's print the top 5 rows from both the data frames. Now to print the top 5 rows, I'll use the head function. First I'll write match_data, which is my variable name for the first data frame, followed by the head function. If I run this, you can see I have the top 5 rows from my matches dataset. You see here we have the ID, the city, date, player of the match. If I scroll to the right, you can see winner, result, result margin, eliminator, method, and the 2 umpires. Similarly, let's see the top 5 rows from the ball dataset. So I'll write ball_data, which is my variable name, followed by the head function. Let's run it using Shift Enter. There you go. So we have the top 5 rows from the ball by ball dataset as well. Next, let's check if there are any null values in both the datasets. Now to check for null values, you can use the isNull function, and to find the total number of null values, you can use the sum function. So I'll write match_data dot. I'll use the isNull function to see if there are any null values, and to find the sum, I'll use the sum function. There you go. If I scroll down, you see here there are 13 null values or missing values in the city column. Then you have 4 null values in the player of the match column. Method, you have 797 null values. Similarly, you have some null values for eliminator and result margin as well. Let me just copy this. Now we'll check for null values present in our ball dataset. I'll replace this by ball. Let's run it. There you go. If I scroll down, here you can see for dismissal underscore kind, then you have player underscore dismissed, fielder, extra types. These all have a lot of null values. Okay. Now you can print the shape of the data frame and also all the columns present in it. For that, I'll use the shape method. I'll write match underscore data dot shape. You see here in our match dataset we have 816 rows of information and 17 columns. Similarly, if you want, you can check for the ball dataset. There you go. So the first value represents the number of rows and then we have the number of columns. Now if you want to print all the columns present in a dataset, you can use the columns attribute. You can see it here in the result. We have all the columns printed that are present in the match dataset. Now let's look at the total number of matches played so far, the cities where the matches have been played, and the team which have participated. So for this I will be using 3 print statement. So I'll write print match played so far. I'll give a colon and then with a comma I'll write my variable name, which is match underscore data, and I'll give shape as 0. Let's print this. You can see matches played so far is 816. I'll write another print statement. This is to check the cities in which the matches have been played, and I'll only print the unique cities. So I'll give a \n. I'll write cities played at. Let's give a colon now, and I'll use my variable which is match underscore data, and within square brackets I'll give my column name, that is city, so that it will extract only the city values, and I'll give my function as unique since I want to know only the unique cities in which the matches have been played. If I run this, there you go. So these are the cities in which the matches have been played from 2008 till 2020. You have Bangalore, Chandigarh, Delhi, you have Durban, Port Elizabeth, you have Centurion, there's Ahmedabad, Cuttack, Nagpur, Kochi, Kanpur, Bangalore, Dubai, and other cities as well. Okay, now we'll print one more result, that is the total number of teams that have participated so far. So I'll write print within single quotes. I'll give \n so that there's a space. I'll write teams participated, give a colon, and then I'll give a comma. I'll pass in my variable name, which is match underscore data. Then within square brackets I'll give team 1, and again I'll use the unique function. If I run this, in the result you can see these are the teams that have participated so far. You have RCB, the Kings 11 Punjab, Delhi Daredevils. Last year there was Delhi Capitals. You have the Rising Pune Super Giants, Chennai Super Kings, Kochi Tuskers, Deccan Chargers, and other teams as well. Alright. Now we will add a new column to our table that will have the year value extracted from the date column of the matches data frame. Now if I go to the top, I'll show you what I want to do. So in this matches data frame you have a column called date, which has all the date values in which the matches were played. From this date value I want to extract only the year. So let me show you how to do it. Now to extract the year value from the date column, I'll use a function which is datetime_index. Now let me show you how to use it. I'll write my variable name, which is match underscore data, and I'll create a new column called season. Now this season column will have only the year values. I'll give pd dot and I'll use my function date time index, and within this function I'll pass in my variable which is match underscore data, and within square brackets I'll give my date column. I'll come out and I'll give my attribute which is year. Now in the next line, let me print the head of the data frame. Now I'll write match underscore data dot head. If I run this, scroll down a bit and I'll go to the right, you see the last column we have added a new column called season which has only the year values. Now we will use this column, which is the season column, to perform multiple operations. Okay. Now let's look at the total number of matches that have been played or held each season from 2008 to 2020. So I'll give my variable name which is match per season equal to, I'll write match underscore data dot, here I'm going to use group by function which is present inside my pandas data frame. So I'm going to group all the season values. So basically I'm going to group all the year values so that I can know how many matches have been played each season. Now I'm going to count all the match IDs for each season. So I'll pass in my ID column dot and I'll use my count function. Then I'll reset my index using the reset underscore index function, and then I'll rename my column. So I'll write rename within brackets, I'll give columns equal to, I'll pass in a dictionary. So I want to convert the ID column to matches. Alright, let me just see it again if everything is fine, and I am going to print my new variable that I have created which is matches per season. Let's run this. Some error has occurred, let me check. It says match per season not defined. There's a small typo here, I have missed a S. So I'll run this again. There you go. You can see in the result we have all the seasons starting from 2008 till 2020, and here we have all the matches that were played in each season. So you can see here in season 2013 there were the highest number of matches that were played, which was 76. Then in 2012 there were 74 matches. Similarly in 2011 we have 73, and if you see this result, in 2008 less number of matches were played overall, which was 58. Oh no, it's actually 2009 where 57 matches were played. Okay. Now we will visualize the above result by creating a bar graph that will show the number of matches held each year. So I am going to make use of this table, and using this table we'll create a bar graph. Now to create a bar graph, I'll use my Seaborn library which I had imported as SNS. I'll write sns.countPlot, which is to count the number of matches. So I'll pass in my data frame which is match underscore data, and I'll give my variable as season, or the column name as season. Next we'll use our Matplotlib library. I'll write plt.xticks, which is an attribute to edit our X labels. I'll give the parameters rotation equal to 45, and I'll give my font size as, let's say, 10. Similarly, I'll use plt.yticks and I'll give my font size as 10. Now I'll edit my x labels. I'll write plt.x label. In the x label we'll have the season values. I'll give my font size as 10. Then let me just copy this. We'll have our plt.y label, and our y axis would have the count. Font size, let it be 10. Then we'll give the title to our bar graph. So I'll write plt.title, and within single quotes I'll give a title to my plot, which is total matches played in each season. We'll also give a font size of, let's say, 10 again, and I'll use font weight as bold. Alright, let me now run this and show you how our graph looks like. There you go. So we have a nice bar graph. On the top you can see the title of the graph, which says total matches played in each season. On the y-axis we have the label as count. On the x-axis we have the label as season. And now let me show you what I meant by x ticks and y ticks. So I had rotated my x values by 45. So you can see the year values have been tilted and printed with 45 degrees. And then I had set my font size to be 10. So this is font size 10, and similarly count also we have font size 10. Now let's say if I want to rotate this by 90 and I print it, you see here the year values are now rotated in 90 degrees. Now what happens if I just remove this parameter and we'll only have font size? If I print it, you see this has been printed in horizontal order like we have it in the count column. I'll just paste it here again. Okay, now let's run it. So I have my year values. Okay, we'll move ahead and perform some more analysis. So in my current cell, which you see here, I'm merging two columns from the matches data frame to balls data frame using a left join. So here I'm adding the ID column and the season column present in my match underscore data frame with the ball data frame, and I'm using a left join, and I'm joining using the common column, which is ID, which is present in both the tables or both the data frames, and then I'm dropping my ID column. Let's go ahead and run this. Okay, you see here I've added my season column to my ball underscore data frame. Now we'll use this data frame now to perform some analysis. Now in the current cell which I have selected, let's visualize the total runs scored in each season. So what I have done is I have grouped my season values and applied a sum function to the total runs column, and then I have reset my index, and I'm plotting a line graph. You see here I've used sns.lineplot, which means I'm plotting a line graph to see the trend of runs scored each season. I have set my face color as black. We have a title called total runs in each season. I've given a font size, a font weight. Now before I run this cell, let me change my face color from black to gray so that my plot is clearly visible. Again, this palette you can choose whatever you want. Let me show you how you can select the Seaborn palette. If I search for SNS palette, there's a nice blog or an article from Seaborn, and here you can see we have all the palettes here. Whichever you want you can choose. There is Hustle, We have set to, paired. There are so many. You can use whatever you like. Now let me go back. Let's run this cell. There you go. So here we have a nice line graph. Now if you see this line graph, in year 2009, least number of scores or minimum number of runs were scored compared to other seasons. We had the highest number of runs scored in 2013, which responds to this. So more than 22,000 runs were scored in 2013. Similarly, we had a drop in 2014, which was around 19,000 or less than 19,000 runs were scored in 2014. And if you see for 2020, which was last season, more than 19,000 runs or nearly 19,500 runs were scored in 2020. Okay, now moving ahead, let's see our next operation that we want to perform. I'll scroll down. Now I want to find the runs scored per match in each season. To do this, I'm concatenating the match per season data frame with the second column season data frame. So I am dividing the total runs scored each season. You can see it here. So I have divided the total runs by the matches played per season. Now I have set my index to season and I am printing runs per season. The result, I am storing it in a variable which is runs scored per match. Let's just run this. There you go. If I scroll down, you see we have the seasons, the different seasons from 2008 till 2020, and you have the total matches that were played in each season. You have the total number of runs that were scored in each season, and then we have our last column which is runs scored per match. So here you have the total number of runs or the average runs scored in each match. Okay. Now we'll look at the number of tosses won by each team. For this, I'm finding the count of toss winners and then I'm creating a horizontal bar graph. So I'm using the value underscore counts function and I'm counting the toss winners for each of the teams. And here I have used my face color as gray, and then you can see I have set my title to number of tosses won each season. My X label is number of tosses won. On the Y label I have the teams. Let's just run this. Okay, if you see here on the Y axis I have the different teams, and on the X axis I have the number of tosses won by each team. You see Mumbai Indians so far have won the highest number of tosses, followed by Kolkata Knight Riders, then we have Chennai Super Kings, then we have Royal Challengers Bangalore, and if you see at the bottom we have Kochi Tuskers and Rising Pune Super Giants. Alright, the next cell of code will help us analyze the toss decision across different seasons. So if you want to find out whether the teams decided to bat or bowl first, I'm using a count plot or a frequency plot. Let me just run this and show you the results. So this is how the distribution looks like of the toss decisions across seasons. The purple color represents field and the red or the orange color represents batting, which means after winning the toss the team decided to bat first, and the purple color represents after winning the toss the team decided to bowl first. Now let me explain you what this graph tells us. In most of the seasons, the team that won the toss decided to field first. Only in certain cases, for example in 2009, the toss winning team decided to bat first. Similarly, if you see for season 2013, most of the teams preferred to bat first. And do we have anything else? No. If you see the other season, even in 2010, if you see, most of the teams preferred to bat first after winning the toss, but the rest of the seasons, be it 2008 or be it 2011, be it 2016, 17, 18, 19 and even 2020, most of the teams preferred to field first after winning the toss. Okay. Now we will look at the match results to analyze how many matches have been won in terms of wickets, meaning that the chasing team won the match. We will see how many matches have been won by runs, meaning that the team batting second could not chase the target. We will understand how many matches have been a tie so far. Now to get that result, I'll just write one line of code. I'll give my data frame name, which is match underscore data, and I'll use my result column, and then I am going to use my value underscore counts function. If I run this, okay, there is some error here. This should be value underscore counts and not count. There you go. If you see, most number of matches have been won by wickets, which means the team batting second won the highest number of matches, and there are less number of matches that have been won by runs, which means the team bowling second won the match. And then we had 13 ties so far from 2008 to 2020. Alright, now let's address some more questions. For example, if you want to know which stadium is best for winning by wickets, so I'll write match underscore data dot, I'll use the venue column which is present in my match underscore data frame, and then I'm going to use my condition as result not equal to runs, and then I'll use the mod function. If I run this, you see here Eden Gardens is the best stadium for winning by wickets. So you have higher chances if you bat second at Eden Gardens, you will win the match. Now see, you want to know which stadium is best for winning by runs. To do that, I'll just copy my above line of code, and instead of not equal to runs, I'll write not equal to wickets. If I run this, it says Firozshah Kotla. So Firozshah Kotla is the best stadium for winning the match by runs. So you have higher chances if you choose to bat first. Alright, now we want to know for any given IPL team which stadium is best when they win the toss. So to answer that question, I'll use my data frame which is match underscore data. Again, I'm going to use my column that is venue, and then I'll write match underscore data dot toss underscore winner. Let's say I'll write equal to my team I'll select is, let's say, Kings 11 Punjab, and then I'm going to use another square brackets and give match underscore data dot winner equal to I'll write again Kings 11 Punjab. Let me copy this, I'll paste it here, and then I'm going to use the mod function. If I run this, you see here the result is Punjab Cricket Association Stadium, Mohali, which is the home ground for Kings 11 Punjab. So for any given IPL team, if you want to know which stadium is best when they win the toss, most of the times you will find it is going to be their home stadium or the home ground. Now let's verify this with another team. Let's say I want to know in which stadium Mumbai Indians have won the maximum number of matches. So I'll choose my team as Mumbai Indians this time, and let's see which stadium it returns. If I run this, there you go. It says Wankhede Stadium, which is again the home ground for Mumbai Indians. Let's see for one more. Now I want for Kolkata Knight Riders. I'll copy this and I'll paste it here as well. If I run this, again it says Eden Gardens, which is the home ground for Kolkata Knight Riders. Okay. The next question I want to answer is, which is the best chasing team? That is the team that has won the maximum number of matches batting second. So for that, I'll write match underscore data dot. I'll use my winner column, and within square brackets I'll write match underscore data dot result not equal to runs, and then I want to use the mod function. If I run this, the result says Kolkata Knight Riders and Mumbai Indians are the best chasing team, which means they have won the maximum number of matches batting second. Now if you want to know the best defending team, that is the team that has won the maximum number of matches batting first, I'll just copy this line of code. Let me scroll down. I'll paste it here, and instead of result not equal to runs, this time I'm going to use result not equal to wickets. If I run this, it returns me the result Mumbai Indians, which means Mumbai Indians is the best defending team, that is the team that has won the maximum number of matches batting first. Now this one typical question that I want to answer now is, does winning the toss mean winning the match? To answer that, I'll create a variable called toss equal to, I'll write match underscore data. I use my column, that is toss winner. Then I'm going to compare it with equal to match underscore data, and then I'll see the winner. So here I'm choosing who won the toss and whether the same team was the winner. I'll create a plot here. I'll write plt.figure. I'm going to give a figure size. I'll write fig size, which is my attribute present inside the matplotlib function, and I'll give my figure size as 10,5. I'll use my count plot function present in the Seaborn library, and I am going to count the toss, and I'll display it using plt.show. Let's run this. Okay, we have a nice bar graph which says winning the toss doesn't necessarily mean winning the match. You can see we have a lot of false values here, which means after winning the toss the team did not win the match, but there are a lot of true values as well. Now I want to answer one more question, which is, does choosing batting or bowling first help in winning matches? So for that I'll create another bar plot. I'll write plt figure. I'll give my figure size equal to, let's say 12,4. Then I'll write sns dot count plot. I'll write match underscore data dot toss underscore decision, which is my column. Then I'll write match underscore data dot toss underscore winner equal to match underscore data dot winner. Then I'll just plot it or display it using plt.show. Let's run this. If I scroll down, you can visualize the result. We can say that choosing to field first for the toss winner helped in winning the match than batting first in IPL from 2008 to 2020. So there are higher chances if you choose to field first, you will win the match. Okay. Now we will use our ball by ball data set to see how a player has performed throughout IPL. Now, for all these visualizations that we have created and we have seen so far, we were using the match dataset, which had information about the matches played from 2008 to 2020. From now on, we are going to use our ball by ball dataset. So the first thing I want to do is we'll analyze a performance of a player throughout IPL. So I'm going to take one of the popular players in IPL, that is Suresh Raina. So I'm going to create a variable called player equal to, I'll use my data frame name, that is ball underscore data, and then within square brackets I'll write batsman equal to I'll give SK Raina, because that is the name present in our dataset for Suresh Raina. Then I'll write data frame underscore Raina equal to ball underscore data, within square brackets I'll write player. Then let me print the head of the data frame. I'll write df underscore Rana dot head. There is an issue here. Let me debug the issue. Instead of dot, this should be an underscore. Let's run it. Now the key here should be capital and not small. Let's run it again. There you go. If you see here, we have created a data frame only for the player name, that is Suresh Raina. You can see here SK Raina. Cool. Now moving ahead. Now in the current cell of code tells us how Suresh Raina has been dismissed throughout the IPL in all the seasons. So here I'm using the value counts for dismissal kind, and I'm going to use a pie chart. So let me run this. If you see here, okay, we have the dismissal kind and there is a nice pie chart. Now this pie chart tells us that Suresh Raina has been caught for 68.8% of the times, and then he has been bowled for 10% time. He has got run out 7.5% of the times, been caught and bowled for 5%, he has been stumped for 5%, and he has been given leg before wicket for 3.8% of the times. Alright, now moving ahead. In the next cell of code, we are trying to find the runs scored by Suresh Raina in 1s, 2s, 3s and in boundaries, that is 4s and 6s. So for that I am creating a user defined function called count, which will count the runs scored by Raina. I'll just run this so that you get an idea. Alright, if you see the results, Raina has scored the maximum number of runs by a boundary, which is 4. Then he has scored the second highest number of runs by taking singles. Then he has scored the third highest number of runs by hitting 6s, and has scored the least number of runs by running a triple. Okay. Now if you want to know the details of the match that had the biggest win in terms of run margin, let me show you. If you want to analyze the match that had the biggest win in terms of margin, so you can use match underscore data, and then within square brackets I'll write my variable name again, match underscore data. Again I'll give a square bracket. I'll say result underscore margin. I'll give a condition equal to match underscore data. Then I'll say result underscore margin. I'll use my function, that is maximum. If I run this, okay, so we have the details of that match. So this match was played in 2017 in the city Delhi. So I'm assuming this match was played at Firozshah Kotla, which is the home ground for Delhi Daredevils, which is currently known as Delhi Capitals. The player of the match was Simmons, who is from West Indies. You see here we have the venue, which is Firozshah Kotla. It was played between Delhi Daredevils and Mumbai Indians. The toss was won by Delhi Daredevils, but they lost the match, and the match was won by Mumbai Indians by runs, and the result margin was 146 runs, which is a huge number when it comes to T20 cricket. And you can see the season as 2017. Okay. Now let's find the players who have scored the maximum number of runs so far in IPL. To do that, I'll create a variable called runs equal to, I'll use my ball underscore data, and I'm going to use my group by function. So here I'm going to group the batsmen. So within single quotes I'll use my column, which is batsman, and then I'm going to use the sum function over the column that is batsman runs. I'll write batsman underscore runs, and I'll give a dot and use my sum function, and I'll reset the index. Okay. Now in the next line I'll write runs dot columns, I'm going to create two new variables, which is batsman, and the second column would be runs. Next I'm going to give a variable called y, which is runs dot, I'm going to sort it. I'll write sort underscore values in terms of runs. So I'll write by my new column, that is runs, comma, I'll give ascending equal to false, which means it will order my result in descending order. I'm going to find the top 10 batsmen in IPL who have scored the maximum number of runs. I'll write reset dot index, and then I'm going to drop my index, and I'll give axis equal to 1, which means I'm going to drop it in terms of columns. Let's print y. So what I'm doing here is, first I'm grouping all the batsmen, and then I'm going to find the total runs that they have scored. So I'm using the sum function. Then I'm creating two new variables or columns called batsmen and runs. I'm sorting the runs scored by the top 10 batsmen in terms of runs. Let's run this. Okay, let me check what is the error. It says column not found, batsman underscore run. This should be batsman underscore runs. Let's run it again. There you go. So we have Virat Kohli, there's Suresh Raina, David Warner, Rohit Sharma, Shikhar Dhawan, then we have Chris Gayle, De Villiers, Dhoni, Uthappa and Gambhir, who are the top 10 batsmen in IPL that have scored the highest number of runs. Okay. Now we will visualize the top 10 players who have scored the highest number of runs. So this is the code I have written already. Now you can use whichever palette you want. I have used face color as gray. Let's just run this and visualize the result. There you go. You have a nice bar plot, and on the top it says top 10 runs scorers in IPL. On the y-axis you have the total number of runs they have scored. On the x-axis you have the player names. So the first player who has scored the maximum number of runs is Virat Kohli. If you see the runs he has scored is close to 6,000 runs. Next we have is Suresh Raina. The second graph or the second bar is for Suresh Raina, followed by Warner, Sharma. We have MS Dhoni, Uthappa, Gambhir and other players. Cool. Now coming to our final visualization, where we'll see the players who have won the Man of the Match award maximum number of times. For that I'm using my column that is player of the match column. Let's run it. If I scroll down, you see here AB de Villiers from South Africa, who currently plays for RCB, has won the highest number of man of the match awards, which is actually more than 25, I believe. Next we have Chris Gale, Rohit Sharma, David Warner, you have Yusuf Pathan, Suresh Raina, Virat Kohli and Gautam Gambhir, who have won the highest number of man of the match awards. Okay, so let me go to the top and just give you a brief on what we did in this IPL data analysis demo. So first we imported our two datasets, match_data and our ball by ball dataset. Then we checked using the isNull function to see whether there are any null values present in any columns of the datasets. We used the shape function to display the shape of the dataset. We printed the total number of columns that are present in one of the datasets. We saw how you could extract the season or the year value from a date column. Then we printed the total number of matches played in each season. Then we converted that same result into a nice bar graph. Then we merged two columns from one of the datasets to another dataset, which was ball data. Then we saw the total number of runs in each season. We also saw the runs scored per match in different seasons. Now we visualized the number of tosses won by each season. We saw the toss decision across all the seasons, where we found out that most of the teams preferred to field first. Then if I scroll further, you saw how to answer different kinds of questions. Then we also learned how you can analyze a particular player and their performance throughout IPL. We saw for Suresh Raina and the dismissal kind. We also checked the pattern in which he has scored the runs. Finally, we found out the top 10 run scorers in IPL and saw who has won the highest number of man of the match awards. So if you want to get the source code files and the datasets we have used in this demo, then please put your email IDs in the comment section. We will share the files over email.
Web scraping is a process of collecting and analyzing massive amounts of data from the internet. So we'll see how we use Python language in order to perform web scraping. Without any further ado, let us dive straight into the topic.
You can actually read a little bit about it. Currently, Beautiful Soup 4 is the current version. If you don't remember the full website for it, you can always do what I do, which is go over and do a search for Beautiful Soup official site. And it almost always comes up right at the top, and you click on there and it'll take you to the crummy.com software site for Beautiful Soup. Now, we're going to use our whatever Python interface you want, IDE. I'm going to use Jupyter Lab, which is built on Jupyter Notebook through Anaconda. So when I open up my Anaconda Navigator, you'll see that I have my different tools available. Again, you might be using a different editor, and that's okay. You might be in PyCharm or something like that where you don't need to do this. And Jupyter Lab is Jupyter Notebook with added tabs and some added features. It's basically in beta testing, so it's got a few little glitches when you're saving things and moving between projects. But for the most part, it's a great upgrade to the Jupyter Notebook, and you can use them together. So you don't have to, it's built on Jupyter Notebook. So anything you do in Jupyter Notebook, you can open up in Jupyter Lab. And the first thing we need to do is we need to go ahead, in this case I'm going under my environments since it partitions the environments out, and I'm going to open up a terminal window. We have to install some packages in here to work with. Now there's a lot of choices on this. Because of the simplicity, will be using conda install. Now you can use pip install for the same thing, and we're going to install our Beautiful Soup 4. And you have to type out the whole thing, Beautiful Soup 4, and you can use a pip install if you're using a different environment. And I am using Python version 3.6, although according to Beautiful Soup they also work on 3.7 all the way from 2.7 through all of 3x. Now according to the Beautiful Soup website, the Beautiful Soup 4 works on anything, you can install on anything from Python 2.7 all the way through any of the Python 3 versions. This just happens to be Python 3.6 because there's a lot of other packages that don't work on 3.7 yet. And we'll go ahead and run this install on here and let it go through its environmental setup. And of course with conda, it goes in there and finds all the dependencies. Pip doesn't do as much as far as finding dependencies, but you know exactly what's on there with pip. So if you're doing a huge distribution, you probably want to use your pip install so you can track what's going on there. With the Conda, I like to just let it take over since this isn't a major distributed package going out. Another quick note between pip and Conda is that if you start on a project in one of these environments and you're using pip in there, stick with pip. If you're using Conda, stick with Conda. They track the packages, and you can run into some issues where they're not tracking the same packages and something gets overwritten. So it's important to stay very consistent with your install on your environments. And we'll also need to go ahead and install our NumPy environment and our Pandas on here. So go ahead and do that. If you haven't added those packages in, go ahead and install those into your environment that you're working in. And of course, Pandas is just simply install Pandas. And let's just install a couple more packages. In this case, let's get our install our Matplotlib library, because we're going to plot at the end since we're going to be collecting data. And for this project, that will be all the packages we'll need. So we can go ahead and close out of our installer or whatever setup you have. And we'll go back to home and we'll just launch our Jupyter Lab, and that will open up in our browser window. Now, if you're coming from Jupyter Notebooks and first time in lab, we can go ahead and just create our first notebook, Python 3. You can also do it under File, Launcher, and you'll see New Notebook. It automatically opens up and we can just click right on there. It'll pop open on the left, and I'll right click this and we'll rename this. We'll rename it just Beautiful. And it is a IPyNB file on there. So that should look familiar because that's a Jupyter Notebook file. This is a new one. Now, I have multiple tabs, and in the past I usually hid this on the other computer, all my notes for the lesson today. But this is my notes going down, and we'll go ahead and just start going through this and see what it looks like to do a data pull from front to end and see how that works as a data scientist pulling that information in from the website. And the first thing I want to do is I want to go ahead and close this side window. That way it get the nice full screen. And we can also up the size a little bit. One of the wonderful things about working in a browser window. Just do that Control+ thing. The packages we talked about is Pandas. So we imported our Pandas if you haven't already. That's our data frame. If you haven't done our Pandas tutorial, definitely worthy of the time to go through there and understand Pandas because it's such a powerful tool. This basically turns your data into a spreadsheet data frame. Our NumPy is our number array, so it kind of works with Pandas very closely as far as manipulating data in arrays. Matplot, we want to go ahead and bring that in, our PLT, so that we can plot the data at the end. And this line right here that says Matplot library inline is for the Jupyter Notebook specifically. It tells it to print that on this page. A lot of the newer versions don't actually require to have that line. They'll still print it on the page, but you should still include that if you're in the Jupyter Lab setup. And then we have our URL library.request. We're going to import URL open for opening up the website. And then we have our BS4, that's your Beautiful Soup 4. We're going to import Beautiful Soup. And then our last one is our RE. That is for manipulating our regular expressions. So when we get to that part of importing our data, we have to do a lot of reformatting so it's something we can use. And the RE is one of those tools. We'll go ahead and run this and just bring all that in. So this is all imported. All these packages are now into our web scraping program we're going to run. Now, if we're going to dive in and pull data, we should have a nice website to pull from. And let's go ahead and we'll use the HubberTiming.com results for the 2018 Martin Luther King race. And if we take this, you can actually just take this, where did we get this from? Well, you can go in here and find the website you're going to scrape from, and you'll see right here it says you just copy that link right in there, that HTTP. And this is the website that we're looking at. You can see right here all the information that we're looking at. Let's say we wanted to run some statistics on this. It sure would be nice to be able to pull it off of here. And if they don't have a direct API, that means we need to pull it from their website. Some of these will have a download, although if you've ever done it where you have a download click and maybe you're paging through 100 websites. In one case, I was pulling all the different United States bills that are passed to track who voted on them for a project. And you can imagine that there's hundreds and hundreds of those, thousands of these documents that they voted on, who voted on it. It goes through the Senate, it goes back to the Congress. So I opened up a website, pull all the links off of there that match a certain criteria, and we'll look at that in just a minute, how we go through the HTML. And then I had to reformat them, or I could hand download each one at a time, which would just be a nightmare. So it's nice to automate it. In this case, we're going to be pulling up this chart. We want to figure out how to pull this chart off of this website. And so when we go back into our Jupyter notebook, I've got my URL, just our name for it, and it's just a string. That's all this is. Nothing fancy there. You'll notice that on the slashes, we now have // You can do a single forward, and HTTP is a double forward. This is just how you have to switch it to match setup in there. And then it's going to go ahead and use the HTML equals URL open URL. And that's from our URL library request. So it's opening a link to that website, or at least pointing to it. And if we run this, this just sets it up. So this is all set up. And then once we've done our setup, let's go ahead and create an object called soup. This will be, and if you remember up here, here's our beautiful soup that we imported from the BS4. And this is the package that we're working with. And so we're going to do our beautiful soup on here. And on this, we need to go ahead and send it our HTML so it knows what it's opening. And then the second part is we have to tell it how the format is coming in. And the most common one for your HTML polls is an LXML setup. And so almost all of them you'll end up using the LXML. There's a few other options. And because this is so common in the newer versions, a lot of times they just leave it out just because it's already on the default. We'll go ahead and leave it in here just to remind us that it's there, and we'll go ahead and run that. And on the newer versions, they actually default it to the XML setup and the HTML. We'll just leave it out and call it HTML. So it's just going to pull from this URL. And when we run that on here, we've now created an object soup that has pulled the website into it. So soup contains the information along with information on that website and what's going on. So let's just go over what we did real quick before we start digging into the actual soup, before we start scooping out stuff. We imported our different modules that we're going to use with our package, specifically the beautiful soup. We did install the beautiful soup. If I remember correctly, you have to call it beautiful soup 4 specifically, so it knows what you're bringing in. And this line right here is very key. From BS4, because that's how it installs the module, we're importing our beautiful soup. And then we found our URL. In this case, we're going to go pull information from the Martin Luther King Dream Run. And then we set our HTML to our URL open URL. And you can see right here we imported that. So here's our URL.request, import URL open. So we're requesting a connection. And once we send that connection into the beautiful soup, it creates an object called soup. And then this one, of course, we chose soup just because it goes with beautiful soup. I guess we could have chosen beautiful. And now we can start extracting information from our website because we've pulled it down onto our computer under soup. And we can start by looking at the title of the website, soup.title. And if we print title.text, you'll see this a lot in beautiful soup because title contains all kinds of information, and if we want just the text from that title, you add the .text on the end. And you can see right here we have our 2018 MLK Dream Run 5K race results. If you look at the tab, that's the actual title up here, 2018 MLK Dream Run 5K race. That's what the title is on the website. And then you might be curious, what's in title? What's the whole title that it's storing up there? Well, let's go ahead and print it out. Here's print title and print title.text. And when we run that, you can see it has the HTML tags title on it, and then the / title to end it. And so we're really just pulling off this piece of the HTML code, and then we look at the text inside that particular part of the HTML. And earlier I mentioned links. What if you want to get all the links off this page? Well, that would be fun. We could do soup dot, and we'll do find _all, put this in bracket, and then quotation marks, we'll go ahead and put A. A is the key find, and you'll start seeing a div and all the different options you have for finding these entities in a website. And then let's go ahead and just print our links, and you can see here that it now shows all the different links in here that are marked by A, because we did a find all A. And then we can also, because this is a little bit hard to pull off the H reference, so we can also add in our find all, fine tune that. In this case, the H reference equals true. We'll actually filter that out. And then finally, we might do a for link in links, and we can simply do something like this for each link. We want to actually find the H reference because we know there's an H reference in it. And if I run this, you can see it just comes through and prints them out one at a time. Some of these are really useful. So you might be looking for something that has HTTPS in it, and you know that's a link running to something else. Or you might be looking for the mail to tag, so you know that's all the mail addresses. But either way, you can easily find all the links in your HTML document that you're paging through. And of course, any packages that have evolved over time, you can also do link.get hrefs, which should do the same thing as our other format. And you can see it certainly does. We get the same printout up here. In this particular case, we really want to get the data off the page. So let's go ahead and do that. Let's see what that looks like. And in data, let's call it all rows. There we go. Equals. And then we have our soup.find underscore all. There's our brackets. And then if we're looking for each row in a database, you'll remember your HTML code, we're looking for the tag tr. So we want to find all tr. And we can take this, and let's go ahead and just take all our rows and do a print all rows. And about this time, you're going to guess that we're going to get a huge amount of information just dumped onto our page. And sure enough, we do. If you look at this, it just kind of goes on forever. But this is an array. Each row is considered an array. So because of that, we can do something simply as putting brackets and just print the first. Let's do the first 5 rows. So from beginning to 5. And you can see here's our first 5 rows on here. I sometimes like to just do, let's just do row 0. And we see that row 0 is finishers. Finishers 191. And just out of curiosity, if that's 0, what's row 1? Mel. Okay, so we're starting to see titles going across here. So if we come up here and we do rows, we did what, up to 10? Let's just take a look and see what 10 does again. And just take a look at that information that comes across. Place, bib, name, gender, age, city, state, chip paste, gender, and so on. So it comes all the way down here. We kind of have an ending right here, and then we have 1, and then we actually, it looks like we start to have information. So we have our 1, our 1191, Max Randolph, that must be the name, Mel 29, and so on. You can start seeing how the information starts getting displayed going down. So the next thing we want to do with this, and I'll go back up here and just edit the space we're in so it starts to make a little bit more sense. Keep it all together. And so we want to do for each row in all rows, we're looking at, what information are we looking at? Well, we have our TH up here, that's the header, our TD down here, which looks like the individual information. And we really are looking for the actual data. So we're looking for our TD tags in the rows. And we can do that because remember when it stores the row, it also stores the tags underneath that. So all rows have all the different tags in it. And you can see right here as we print each one of those out. And so when we look at each row, we can create another variable and we'll call it row list. And we'll set this equal to, in this case, row, because we've already pulled all the rows out of soup. So now we want to find for each row, and in there we want to find our TD. And if we go ahead and just print, I'm going to do it, if you notice I changed the indent, so I'm just going to print row list. What this does is the last value to go into row list, our last row is going to print now. And of course make sure you have an underscore instead of a period when you're typing. So row.find underscore all TD, and if we print the last row, you can see I have all the data coming across here. We have our 191, our 1216, Zuma, Ochoa, I hope I said that right, female, I believe that's age 40, and so on. And then we can take our row list, and there's a lot of things we can do with the row list. But we'll do let's do object, or let's just do cell in row list. And so we're going to look at each cell, because this is, if you look at this, they have commas separated between the different objects. And then we're going to go ahead and print cell.text. Let's just take a look and see what that looks like. And we can see here for each row we get 191, there's our 191, there's our 1216, 1216, our individual who's in the race, and so forth all the way down for those different settings. And let's go ahead and create a new variable up here. We'll call this all, let's just call it data. We'll keep it simple. So here's our data, and then we have our row. We take our row and we break it up into individual cells. So we'll call this data row, and we'll set this empty to an empty row. And we're going to take our cells, tab this, and we know that each cell generates a text. And so what we want to do is I want to take my data row, let's just replace that. And let's take our data row and let's append our cell.text. So I'm going to add each row is going to be a row of the different text on here. And then once I create each row, I want my data, which is going to be everything, to append each row. And here's our data row. And then if we go ahead and come down here and let's just print data. Now, if we were working with large data, we'd be very careful about just throwing all our data on the page. But you can see here, we throw the data on the page and we get finishers, 199, male, 78, female, 113, 1, and so on. And if you look at this, this is the headers on the file. We have finishers, male, female. It's just like some general statistics on the first one. And then we have actually an empty data set, and then we have our data that continues, which the actual information we're looking for. So we have 1, 1191, Max Randolph, male, 29, Washington, D.C., runtime, 1 of 78, and so on here. So we could really quickly get rid of that. A number of different ways to do that. One of them is just to do, we're going to set, if we do data 2 on, we should get rid of everything, but we want to keep Randolph, so make sure Randolph is in there. Oh, we lost Randolph. Let's try 1 on. There we go. There's Max Randolph on there. So we can just simply redo our data on here, and we can do data. Probably want to do it in all rows from 1 on, but I'm just going to do my data equals data 1 on down here. There's reasons to split it this way. In data science, sometimes you don't want to touch the original data in case you need it, in case we do need the first row. So we'll put it down here, and maybe we'll just call this titles. Titles equals data of 0. And so we could do something here where we print, and we'll print up our titles, and we'll print our data. In this case, instead of 1 on, let's go -2. Let's look at the last 2 rows of data. So here we have our titles, and for some reason just put in finishers of 191. I was expecting a little bit more up there. And we have our last couple people, and they look like the data on these looks just fine on here. Turns out this is just some generic statistics up here. So we'll get rid of titles completely. It doesn't really do us any good. But we know that data comes in here, and we can look at our data and look at the very end of the data too, the -2 to the end. And we can see it pulls the data in pretty good. We don't have anything too funky in here we're looking at. It looks pretty clean. Now you got to be a little careful, because at some point we might have to come back here and clean up the data if we get an error for running data analysis. We might find out there's some unusual characters or something is misset in the data itself. And you also notice that everything is a string. So when we're bringing it in, we might have to do some conversions to test it out and convert them to whatever kind of data format we're working with. So at this time, we want to go ahead and bring in our pandas. And let's go ahead and call this df for data frame. We'll set it equal to, and if you remember correctly, we imported pandas as PD, and that's standard. You'll see that in most code examples where they import pandas as PD, and it is capital D, capital F for data frame. And we're just going to bring in our data. That's what we called it on here. And let's take this and we'll print. Now, when you're working with data frames, you're usually talking large amounts of data. And so you almost never want to print the whole data frame out. We're going to go ahead and do that anyway, just so we can see what that looks like. And you can see in here, it brings in our data frame coming in here. And we just have a mess of information. This is our data. Let's go ahead and print df and see what that looks like in the data frame. And this is nice because it organizes it into a very easy to read table. And we have, they set the label 0, 1, 2, 3, 4, 5, 6, and so on. And then we have each row. We have male, 78, none, 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 going across. When we get all the way down here, we'll see Max Randall about number 3. And the first thing this does is this flags me that I brought in a bunch of information up here that we really didn't want. It's from 3 on that we want. And we can clean this up in one of 2 ways. We can try to clean it up under the data, or we can clean it up under the data frame, depending on what it is we're trying to do. And so to fix this, I want to go ahead and just change it up here in the actual data pull in. We don't need that information. So I'll rerun it, reload our data from 4 on. And then when I run this, we see we have Max Randolph is right at the top of the list like he should be, and we have all the data going down. Now with the data frame, remember I said we don't usually print the whole data frame. We'll go ahead and do df.head. And this prints the first 5 rows. And you can see that we have 13 columns. Here's Max Randall all the way to Theo Kinman. And I usually also print df tell. And the reason I like to do these particular 2 setups, and I'm going to change it just to 2 rows, because you can do that, you can print as many rows as you want, is it's good to look at the first part and the end, because those are usually where you have extra data brought in, something's messed up. And you can also see that we have 190 rows in here. And it comes in with our Zulma, Lisha, and they're both on here on the list. So now we have a nice data frame, columns and rows. We can easily look at it, we can see the setup on here, and we can look at the names and everything. Now, at some point, you might be looking at these individual columns and find different information that needs to be re-edited. If you can, you try to do it with the whole column under Pandas. You can, up in the upper part of the code where you went from cell to cell or row to row, you could look at individual cells, maybe you find a marker in that cell that's something specific, like remove all colons or semicolons or something in there, or brackets. So there's a lot of options in there, but you'll find that this one actually comes in pretty clean on here all the way down. And the next thing we really want to do is we want to look at the headers. I don't know about you, but it doesn't make any sense to me when I have column 1, I don't know what 1191 is or 1080, need name Kaiser runner. I'm guessing that's column 2 is names. Third one, it looks like male or female, probably age, but I don't want to guess. I want this to bring in my column so I know exactly what I'm looking at. So how can we make Beautiful Soup do that for us? Well, let's take our column headers. We're going to set that equal to our soup find underscore all, and then we're going to look for our headers, our th files. And since we're in Jupyter Lab, in this case Jupyter Notebook, I can just type out column headers. If it's the last variable I have listed, it will automatically print it. So it's kind of a shorthand. And we can see right here we have place, I'm guessing that's bib, name, gender, age, city, state, chip time, chip pace, and so on. So we have all our headers right there. I shouldn't have to type them all in. And we'll go ahead and do it before. We'll go ahead and do a header list equals our empty array, and then we can do for column in column headers, and we can take our header list and just append. And what do we want? We want the text from the column, so we'll just do column.text. And then if we come down here and we print our header list, let's see what that looks like. If we did it right, we should get a nice list of all the different column headings we want. So we have place, bib, name, and so on. And then Pandas, just because Pandas is so cool, we can simply do df columns equals our header from our header list. We can simply set df columns set to df headers, and then if I print df.head, we'll take a look at that, and we'll see right here it has nicely placed our values on here. Place, bib, name, gender, age, and so on. So very quickly we've created this nice data frame. We have the data displayed in nice rows and columns and easy to read. And then as a data scientist, the first thing we want to know is the info. What is in these columns and rows and headers? And you see right here they all come up with non-null object. There's a big flag. So if I want to do anything with this, these are all coming through as strings or an object. I usually mean strings in this case, that they're a string variable. And we have, you can quickly read through this, 191 entries, date columns, total 14 columns. There's a total of 14 columns in the data, and it shows you all the different names and what type of column they are. And it's probably good also to look at the shape of the data. df.shape, we'll go ahead and just run that. You can see it's 191 by 14, 14 columns, 191 entries. This is more like the way you look at a NumPy array, 191 by 14 for the shape. And remember, this is a variable, so if I put it on, if it's a last variable or last value in the set of cells, Jupyter automatically prints it out. So if you're in a different IDE, you'd want to go ahead and use the print statement on here. And then one of the things you'd want to also go through, we'll create a second one, df2 equals df.dropNA. Now the axes is automatically equal to 0. So a lot of times you'll see something like axes equals 0, comma, how equals any. Axes equals 0 is default. That means we're looking at going down the rows. You could look at the column going across. Let's remove the how any because that's just going to confuse you. The axes is whether you're going down the columns or if you're looking at it row by row by row by row. Or you could be looking at it by column by column by column. This would drop any column and it would drop off the NA in any column. And how equals, and we want any. I always confuse all and any because they both start with A. All means that all of them have to be non-value, where any means that any of them can be there to drop it. So this would drop any column with a null value in it. But we want 0, and it'll drop any value with a null value. And then because 0 is always the default, we'll just leave it out. And then it's curious as to what the shape is now. Did we lose anything? Was there any null values in our df2 that we dropped from the df? And we'll go ahead and run that. And we see 191 and 14. So we didn't really drop anything. But it's always good to check. There's other ways you can also do, are there, let's see, any NAs? You can detect NAs in here. Null values, infinite values. That's another one you got to watch out for. we're working with data that we're going to do something with here in a minute, so you got to be a little careful also in the conversions. Are you going to convert something where people typed in weird characters to describe the data a certain way? So now we've got to this point where we have all our different columns, we have our different data, and at this point maybe you're asking, or maybe the shareholder of the company is asking, hey, can we look at the, based on the chip time, here's our chip time, can we plot that versus gender? How does gender versus chip time compare? And so we can do that. We can take that, and the first thing we look at is we say, hey, well, chip time came in as a string, and that's going to be an issue. Now, there's a number of ways you can change this. One of them is we could go all the way back up here where we created the data and find a way to tag it and say, hey, whenever this cell text, maybe instead of appending this, I noticed that anytime there's 2 colons in it, that's probably a time signature, and let's convert all the time signatures to date time field or whatever. A lot of times you don't get that. You don't get that option. And that's always a question in bringing in data. Whether you convert the data coming in at the beginning, or do you wait till you have it, open it up, and then convert it when you go to use it. We're going to go ahead and convert it after we got it into our data frame. So we have our df2 here. We've dropped all of our NAs. We have a shape. In fact, let's do this. Since there's no difference between df and df2, well, we'll just go ahead and use df2. So let's go ahead and take our df2, and we want to take that specific field and convert it into some kind of numerical value we can use. And let's add another column. A lot of times this is something you want to do is where you want to go ahead and keep all the original columns and just add a new column in there. And this new column is going to be based on the, if we remember correctly, we had chip time. That's what we're going to look at. Okay, we want chip time versus gender. If we go into our pandas, we find out we have pandas to delta, and this is actually time delta. And then we just want to take our df2, and we're going to use the chip time column. So this is going to say, hey, let's look at, let's convert everything in df2 chip time into a time delta format. That's the data type we're going to put it as. And we can go ahead and just run this. And if we go in here and we do info, df2, and we'll keep our, we're going to look at this particular column, but we want to keep it as a data frame. So this is a list of all the columns we want to look at. We'll just do .info on here and run that. And we do an info on that. You can see it's now a time delta 64 nanoseconds. Well, we really don't want nanoseconds. We actually probably want to do it in minutes. So let's take a look at that. And let's take this whole thing, df2. Let's just set the df2. We have our df2. This is a column we're working with here. And we can use the as type property in Pandas. And so we can set this equal to df2. We'll take our same column in here, and we'll set it as type time delta second. So it's still a delta time here. So if I run this, you'll see that it still comes up as, where is it? Oh, it turns it into a float. So we're now at a float 64. So it's a number of seconds in that delta time. And then finally, we want to go ahead and turn that from seconds to, say, minutes. And you know, there's 60 seconds in minutes. And so now we divide by 60. We still have a float. We have our info that shows us it's a float. And then we can go ahead and just do a print df2. And let's just keep it small. We don't want to look at all our data. We just want to do the head of it. And we run this, and you can see right here where we go to, it'll be the last one. Here's our chip time in minutes. And a lot of times, just to make life easy for viewing, since we're only looking at this particular element, we can do chip time in minutes. And now we just see that, oops, we take off. We'll go ahead and take off our info. Done with that. And we'll run this. And you can see we have our minutes. 16.8 minutes, 17.51 minutes, and so on. It's a float number. Now keep in mind, this is 0.8. That's not 16 minutes and 80 seconds. That can always throw you if you're going through so many numbers you forget. So important to remember that. And we're also going to look at, the other one we're looking at is what? Gender. We want to look at gender to chip time in minutes. And so we can see here under the head we get male, 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 and a number of different setups. And let's switch this to tail real quick and just look at the end of it. And here we have female, female, male, female, female. So we have two different genders, and we have our chip time in minutes. And if you remember, we brought in our PLT. If you haven't used the plot library, the Matplotlib library, you have a drawing place you're putting stuff on. So we have our PLT. We're going to do a bar graph, and we just want to simply use use our df2 gender and df2 chip time in minutes. So that's going to plot the two bars. And to make it pretty, we'll go ahead and give it the X labeled gender, the Y labeled chip time minutes. And that simply is, remember, it always plots X and it plots Y. We have our gender, our chip time. Give it a nice title, comparison of average minutes run by male and female. And if we go ahead and run this with the correct titles in here and everything matches, you'll get a nice graph. We can see here the comparison of average minutes run by male and female. Here's our chip time in minutes. The men seem to be slackers in this particular case. And it's actually, there's a number of studies that show that women tend to have, as far as doing cross-country, there's a lot of women who have a longer endurance than men. So it's not too surprising. But we can see here the average chip time around 70, and for women over 100 minutes. And then another really cool thing we can do is we can describe the data. So df2.describe, this again is a pandas function, just like info is. And we're going to include np number, the NumPy number. And if we run that, you'll see here it comes up and it says chip time in minutes, count, it gives you the average or the mean, standard deviation, the minimum, the maximum, all the different descriptive information you're going to want from your data set on there. And just because there's all kinds of fun ways, let's do a box plot to display your information. We can do a box plot where the column equals chip time in minutes. And let's go ahead and run that. Keep mistyping my chip time in minutes. And you can see it puts out a nice box plot showing you the information. We have our different values and floaters. And this is always interesting because this is a nice way of seeing where we have these floaters, one up here and there's two up above, and of course your nice spread on the box plot. And we can also modify this a little bit, and we can add in by equals gender, and then we'll just give it a blank title. I don't know why we're giving it a blank title. We'll just add a Y plot, Y label on there for runtime. And if we run this, you can see here box plot grouped by gender, chip time in minutes, and now we have our female and male, two different areas, and you can see how they vary. You have your two different your outlier up here, and you can also see how there's such an overlap between the two different values. So if I was looking at this, I'd be like, wow, I really could not draw a conclusive thing on this saying that women's runtime was more in general because they overlap too much. That would be one of the conclusions I'd have to come up with on here. And then we get to maybe the partners come in from the company and say, hey, we'd like to know the age versus chip time in minutes. That'd be something worth knowing on the statistics on this. And the first thought is we can simply plot it. And we can do this. We can actually plot the scatter plot, chip time versus df2 of age. There's our XY coordinates. But if you remember from df2 when we did the info, let's go way back up here, we're looking at a data object as far as our chip time on this and our age. Now we converted the chip time, but we also need to convert the age. And if we do it right here, we just plot it, and it'll actually let us plot it. It shouldn't. It should give us an error, but it does let us plot it. You'll see the ages come up a mess over here because they're converting it to weird float numbers and all kinds of things. So what we want to do is we want to take our age, and we'll just call this age underscore I. So we're going to take our age and we're going to create another column for df2 age underscore I. And the I is just going to stand for integer. It's our own choice of values. There is a number of ways to do this, but we're going to do pandas to numeric is the best way in pandas. And the reason we're doing this is that numeric creates a float value. So right off the bat, we want all our stuff converted. It converts it to the least common denominator. So if they're all integers already, you'll get integers. As you can see from here, it's doing some kind of conversion that converts it to a float value. The other thing that numeric does is if there's a null value or they put in like a blank line or a dash to represent no information, it'll convert it to a null. So it goes from like a string to a null versus just having some kind of made up number that Python somehow created for the graph we have below. And then we want to add our df2 age because that's what we're converting to numeric, and then we want to coerce it. And there's a couple different options on this, like you can have it where it just doesn't process it in pandas, but coerce means that if it gets a weird value, that is a null value now. And since we're dealing with errors, this is what happens when you get an error converting it. We want to coerce it. There we go, and put the end bracket on there. And then finally we want to go ahead and round this off. So we'll put brackets around all the way around it, and this rounds off everything in this series. So what we've done here is I've taken df2 age, which is a D-type object, which in this case is mostly string, strings with a couple of blank ones in there. And we're going to convert it to a numeric, which will automatically go to float. And then we're going to take wherever there's an error, wherever it says, hey, this doesn't convert. And usually that's a blank string. Like I said, I've worked with so many databases where someone puts down none, someone types in space, some types in a dash to mean none, and you get this really weird conversion coming up. This covers all of that in Pandas. So it's really a nice way of just coercing it and saying, hey, if we don't have a number in there, let's make it a null value. And then we're going to round it off. And then finally, let's go ahead and take our df2. Here's our df2, and let's drop those null values. Drop NA. And we want how equals any. So that means if there's any null values in the data set. Now this might get you in trouble because you might have null values in a different column, and so you might lose data that way. At this point, we could also do like certain parts of like drop just certain columns with null values. There's all kinds of other options in here. But we're just going to do we're going to just drop any, and we want to do it in line equals true. So that means it's going to reassign it to df2. So df2 now has rounded out, so it's rounded to the integer. We didn't do any places. The age, and it's going to be age I, and then we've dropped all our null values. That way we're not going to get any errors when we try to plot a null value. And it also makes sure that data, by deleting out the rows, because that's what this does, it automatically does axis 0, which is your rows, axis 1 is your columns. By doing this, it automatically removes all the rows with null values. So it just cleans out the rows. And then when we go ahead and plot this, we see we have a nice clean data, and we have age all the way up to 70. So we have our chip time set, and then our age going across. And it makes a nice plot that you can easily show for display and for and you can easily show that to your shareholders or whatever group you're working on. It makes a really nice and quick, easy display.
In today's session, we'll be discussing about web scraping using Python. Web scraping is a process of collecting and analyzing massive amounts of data from the internet. So we'll see how we use Python language in order to perform web scraping. Without any further ado, let us dive straight into the topic.
You can actually read a little bit about it. Currently, Beautiful Soup 4 is the current version. If you don't remember the full website for it, you can always do what I do, which is go over and do a search for Beautiful Soup official site. And it almost always comes up right at the top, and you click on there and it'll take you to the crummy.com software site for Beautiful Soup. Now, we're going to use our whatever Python interface you want, IDE. I'm going to use Jupyter Lab, which is built on Jupyter Notebook through Anaconda. So when I open up my Anaconda navigator, you'll see that I have my different tools available. Again, you might be using a different editor, and that's okay. You might be in PyCharm or something like that where you don't need to do this. And Jupyter Lab is Jupyter Notebook with added tabs and some added features. It's basically in beta testing, so it's got a few little glitches when you're saving things and moving between projects. But for the most part, it's a great upgrade to the Jupyter Notebook, and you can use them together. So you don't have to, it's built on Jupyter Notebook. So anything you do in Jupyter Notebook, you can open up in Jupyter Lab. And the first thing we need to do is we need to go ahead, in this case I'm going under my environments since it partitions the environments out, and I'm going to open up a terminal window. We have to install some packages in here to work with. Now there's a lot of choices on this. Because of the simplicity, will be using conda install. Now you can use pip install for the same thing, and we're going to install our Beautiful Soup 4. And you have to type out the whole thing, Beautiful Soup 4, and you can use a pip install if you're using a different environment. And I am using Python version 3.6, although according to Beautiful Soup they also work on 3.7 all the way from 2.7 through all of 3x. Now according to the Beautiful Soup website, the Beautiful Soup 4 works on anything, you can install on anything from Python 2.7 all the way through any of the Python 3 versions. This just happens to be Python 3.6 because there's a lot of other packages that don't work on 3.7 yet. And we'll go ahead and run this install on here and let it go through its environmental setup. And of course with conda, it goes in there and finds all the dependencies. Pip doesn't do as much as far as finding dependencies, but you know exactly what's on there with pip. So if you're doing a huge distribution, you probably want to use your pip install so you can track what's going on there. With the conda, I like to just let it take over since this isn't a major distributed package going out. Another quick note between pip and conda is that if you start on a project in one of these environments and you're using pip in there, stick with pip. If you're using Conda, stick with Conda. They track the packages, and you can run into some issues where they're not tracking the same packages and something gets overwritten. So it's important to stay very consistent with your install on your environments. And we'll also need to go ahead and install our NumPy environment and our Pandas on here. So go ahead and do that. If you haven't added those packages in, go ahead and install those into your environment that you're working in. And of course, Pandas is just simply install Pandas. And let's just install a couple more packages. In this case, let's get our install our Matplotlib, because we're going to plot at the end since we're going to be collecting data. And for this project, that will be all the packages we'll need. So we can go ahead and close out of our installer or whatever setup you have. And we'll go back to home and we'll just launch our Jupyter Lab, and that will open up in our browser window. Now, if you're coming from Jupyter Notebooks and first time in Lab, we can go ahead and just create our first notebook, Python 3. You can also do it under File, Launcher, and you'll see New Notebook. It automatically opens up and we can just click right on there. It'll pop open on the left, and I'll right-click this and we'll rename this. We'll rename it just Beautiful. And it is a IPyNB file on there. So that should look familiar because that's a Jupyter Notebook file. This is a new one. Now, I have multiple tabs, and in the past I usually hid this on the other computer, all my notes for the lesson today. But this is my notes going down, and we'll go ahead and just start going through this and see what it looks like to do a data pull from front to end and see how that works as a data scientist pulling that information in from the website. And the first thing I want to do is I want to go ahead and close this side window. That way it looks, get the nice full screen. And we can also up the size a little bit. One of the wonderful things about working in a browser window. Just do that Control+ thing. The packages we talked about is Pandas. So we imported our Pandas if you haven't already. That's our data frame. If you haven't done our Pandas tutorial, definitely worthy of the time to go through there and understand Pandas because it's such a powerful tool. This basically turns your data into a spreadsheet data frame. Our NumPy is our number array, so it kind of works with Pandas very closely as far as manipulating data in arrays. Matplot, we want to go ahead and bring that in, our PLT, so that we can plot the data at the end. And this line right here that says Matplotlib inline is for the Jupyter Notebook specifically. It tells it to print that on this page. A lot of the newer versions don't actually require to have that line. It'll still print it on the page. But you should still include that if you're in the Jupyter Lab setup. And then we have our URL library.request. We're going to import URL open for opening up the website. And then we have our BS4, that's your Beautiful Soup 4. We're going to import Beautiful Soup. And then our last one is our RE. That is for manipulating our regular expressions. So when we get to that part of importing our data, we have to do a lot of reformatting so it's something we can use. And the RE is one of those tools. We'll go ahead and run this and just bring all that in. So this is all imported. All these packages are now into our web scraping program we're going to run. Now, if we're going to dive in and pull data, we should have a nice website to pull from. And let's go ahead and we'll use the HubberTiming.com results for the 2018 Martin Luther King race. And if we take this, you can actually just take this, where did we get this from? Well, you can go in here and find the website you're going to scrape from, and you'll see right here it says you just copy that link right in there, that HTTP. And this is the website that we're looking at. You can see right here all the information that we're looking at. Let's say we wanted to run some statistics on this. It sure would be nice to be able to pull it off of here. And if they don't have a direct API, that means we need to pull it from their website. Some of these will have a download, although if you've ever done it where you have a download click and maybe you're paging through 100 websites. In one case, I was pulling all the different United States bills that are passed to track who voted on them for a project. And you can imagine that there's hundreds and hundreds of those, thousands of these documents that they voted on, who voted on it. It goes through the Senate, it goes back to the Congress. So I opened up a website, pull all the links off of there that match a certain criteria. And we'll look at that in just a minute, how we go through the HTML. And then I had to reformat them, or I could hand download each one at a time, which would just be a nightmare. So it's nice to automate it. In this case, we're going to be pulling up this chart. We want to figure out how to pull this chart off of this website. And so when we go back into our Jupyter Notebook, I've got my URL, just our name for it, and it's just a string. That's all this is. Nothing fancy there. You'll notice that on the slashes, we now have // You can do a single forward, and HTTP is a double forward. This is just how you have to switch it to match setup in there. And then it's going to go ahead and use the HTML equals URL open URL. And that's from our URL library request. So it's opening a link to that website, or at least pointing to it. And if we run this, this just sets it up. So this is all set up. And then once we've done our setup, let's go ahead and create an object called soup. This will be, and if you remember up here, here's our beautiful soup that we imported from the BS4. And this is the package that we're working with. And so we're going to do our beautiful soup on here. And on this, we need to go ahead and send it our HTML so it knows what it's opening. And then the second part is we have to tell it how the format is coming in. And the most common one for your HTML polls is an LXML setup. And so almost all of them you'll end up using the LXML. There's a few other options. And because this is so common in the newer versions, a lot of times they just leave it out just because it's already on the default. We'll go ahead and leave it in here just to remind us that it's there, and we'll go ahead and run that. And on the newer versions, they actually default it to the XML setup and the HTML. We'll just leave it out and call it HTML. So it's just going to pull from this URL. And when we run that on here, we've now created an object soup that has pulled the website into it. So soup contains the information along with information on that website and what's going on. So let's just go over what we did real quick before we start digging into the actual soup, before we start scooping out stuff. We imported our different modules that we're going to use with our package, specifically the beautiful soup. We did install the beautiful soup. If I remember correctly, you have to call it beautiful soup 4 specifically, so it knows what you're bringing in. And this line right here is very key. From BS4, because that's how it installs the module, we're importing our beautiful soup. And then we found our URL. In this case, we're going to go pull information from the Martin Luther King Dream Run. And then we set our HTML to our URL open URL. And you can see right here we imported that. So here's our URL.request, import URL open. So we're requesting a connection. And once we send that connection into the beautiful soup, it creates an object called soup. And then this one, of course, we chose soup just because it goes with beautiful soup. I guess we could have chosen beautiful. And now we can start extracting information from our website because we've pulled it down onto our computer under soup. And we can start by looking at the title of the website, soup.title. And if we print title.text, you'll see this a lot in beautiful soup because title contains all kinds of information, and if we want just the text from that title, you add the .text on the end. And you can see right here we have our 2018 MLK Dream Run 5K race results. If you look at the tab, that's the actual title up here, 2018 MLK Dream Run 5K race. That's what the title is on the website. And then you might be curious, what's in title? What's the whole title that it's storing up there? Well, let's go ahead and print it out. Here's print title and print title.text. And when we run that, you can see it has the HTML tags title on it, and then the / title to end it. And so we're really just pulling off this piece of the HTML code, and then we look at the text inside that particular part of the HTML. And earlier I mentioned links. What if you want to get all the links off this page? Oh, that would be fun. We could do soup dot, and we'll do find _ put this in bracket, and then quotation marks, we'll go ahead and put A. A is the key find, and you'll start seeing a div and all the different options you have for finding these entities in a website. And then let's go ahead and just print our links, and you can see here that it now shows all the different links in here that are marked by A, because we did a find all A. And then we can also, because this is a little bit hard to pull off the H reference, so we can also add in our find all, fine tune that. In this case, the H reference equals true. We'll actually filter that out. And then finally, we might do a for link in links, and we can simply do something like this for each link. We want to actually find the H reference because we know there's an H reference in it. And if I run this, you can see it just comes through and prints them out one at a time. Some of these are really useful. So you might be looking for something that has HTTPS in it, and you know that's a link running to something else. Or you might be looking for the mail to tag, so you know that's all the mail addresses. But either way, you can easily find all the links in your HTML document that you're paging through. And of course, any packages that have evolved over time, you can also do link.get hrefs, which should do the same thing as our other format. And you can see it certainly does. We get the same printout up here. In this particular case, we really want to get the data off the page. So let's go ahead and do that. Let's see what that looks like. And in data, let's call it all rows. There we go. Equals. And then we have our soup.find_all. There's our brackets. And then if we're looking for each row in a database. You'll remember your HTML code. We're looking for the tag TR. So we want to find all TR. And we can take this, and let's go ahead and just take all our rows and do a print all rows. And about this time, you're going to guess that we're going to get a huge amount of information just dumped onto our page. And sure enough, we do. If you look at this, it just kind of goes on forever. But this is an array. Each row is considered an array. So because of that, we can do something simply as putting brackets and just print the first. Let's do the first 5 rows. So from beginning to 5. And you can see here's our first 5 rows on here. I sometimes like to just do, let's just do row 0. And we see that row 0 is finishers. Finishers 191. And just out of curiosity, if that's 0, what's row 1? Mel. Okay, so we're starting to see titles going across here. So if we come up here and we do rows, we did what, up to 10? Let's just take a look and see what 10 does again. And just take a look at that information that comes across. Place, bib, name, gender, age, city, state, chip paste, gender, and so on. So it comes all the way down here. We kind of have an ending right here, and then we have 1, and then we actually, it looks like we start to have information. So we have our 1, our 1191, Max Randolph, that must be the name, Mel 29, and so on. You can start seeing how the information starts getting displayed going down. So the next thing we want to do with this, and I'll go back up here and just edit the space we're in so it starts to make a little bit more sense. Keep it all together. And so we want to do for each row in all rows, we're looking at, what information are we looking at? Well, we have our TH up here, that's the header, our TD down here, which looks like the individual information. And we really are looking for the actual data. So we're looking for our TD tags in the rows. And we can do that because remember when it stores the row, it also stores the tags underneath that. So all rows have all the different tags in it. And you can see right here as you print each one of those out. And so when we look at each row, we can create another variable and we'll call it row list. And we'll set this equal to, in this case, row, because we've already pulled all the rows out of soup. So now we want to find for each row, and in there we want to find our TD. And if we go ahead and just print, I'm going to do it, if you notice I changed the indent, so I'm just going to print row list. What this does is the last value to go into row list, our last row is going to print now. And of course make sure you have an underscore instead of a period when you're typing. So row.find underscore all TD, and if we print the last row, you can see I have all the data coming across here. We have our 191, our 1216, Zuma, Okchoa, I hope I said that right, female, I believe that's age 40, and so on. And then we can take our row list, and there's a lot of things we can do with the row list. But we'll do let's do object, or let's just do cell in row list. And so we're going to look at each cell, because this is, if you look at this, they have commas separated between the different objects. And then we're going to go ahead and print cell.text. Let's just take a look and see what that looks like. And we can see here for each row we get 191, there's our 191, there's our 1216, 1216, our individual who's in the race, and so forth all the way down for those different settings. And let's go ahead and create a new variable up here. We'll call this all, let's just call it data. We'll keep it simple. So here's our data, and then we have our row. We take our row and we break it up into individual cells. So we'll call this data row, and we'll set this empty to an empty row. And we're going to take our cells, tab this, and we know that each cell generates a text. And so what we want to do is I want to take my data row, let's just replace that. Let's take our data row and let's append our cell.text. So I'm going to add each row is going to be a row of the different text on here. And then once I create each row, I want my data, which is going to be everything, to append each row. And here's our data row. And then if we go ahead and come down here, and let's just print data. Now, if we were working with large data, we'd be very careful about just throwing all our data on the page. But you can see here, we throw the data on the page and we get finishers, 199, male, 78, female, 113, 1, and so on. And if you look at this, this is the headers on the file. We have finishers, male, female. It's just like some general statistics on the first one. And then we have actually an empty data set, and then we have our data that continues, which the actual information we're looking for. for. So we have 1, 1191, Max Randolph, Mail, 29, Washington, D.C., runtime, 1 of 78, and so on here. So we could really quickly get rid of that. A number of different ways to do that. One of them is just to do, we're going to set, if we do data 2 on, we should get rid of everything, but we want to keep Randolph, so make sure Randolph is in there. Oh, we lost Randolph. Let's try 1 on. There we go. There's Max Randolph on there. So we can just simply redo our data on here, and we can do data. Probably want to do it in all rows from 1 on, but I'm just going to do my data equals data 1 on down here. There's reasons to split it this way. In data science, sometimes you don't want to touch the original data in case you need it, in case we do need the first row. So we'll put it down here, and maybe we'll just call this titles. Titles equals data of 0. And so we could do something here where we print, and we'll print up our titles, and we'll print our data. In this case, instead of 1 on, let's go -2. Let's look at the last 2 rows of data. So here we have our titles, and for some reason I just put in finishers of 191. I was expecting a little bit more up there. And we have our last couple people, and they look like the data on these looks just fine on here. Turns out this is just some generic statistics up here. So we'll get rid of titles completely. It doesn't really do us any good. But we know that data comes in here, and we can look at our data and look at the very end of the data too, the -2 to the end. And we can see it pulls the data in pretty good. We don't have anything too funky in here we're looking at. It looks pretty clean. Now you got to be a little careful, because at some point we might have to come back here and clean up the data if we get an error if we're running data analysis. We might find out there's some unusual characters or something is misset in the data itself. And you also notice that everything is a string. So when we're bringing it in, we might have to do some conversions to test it out and convert them to whatever kind of data format we're working with. So at this time, we want to go ahead and bring in our pandas. And let's go ahead and call this df for data frame. We'll set it equal to, and if you remember correctly, we imported pandas as PD, and that's standard. You'll see that in most code examples where they import pandas as PD, and it is capital D, capital F for data frame. And we're just going to bring in our data. That's what we called it on here. And let's take this and we'll print. Now when you're working with data frames, you're usually talking large amounts of data, and so you almost never want to print the whole data frame out. We're going to go ahead and do that anyway, just so we can see what that looks like. And you can see in here, brings in our data frame coming in here. We just have a mess of information. This is our data. Let's go ahead and print df and see what that looks like in the data frame. And this is nice because it organizes it into a very easy to read table. And we have, they set the label 0, 1, 2, 3, 4, 5, 6, and so on. And then we have each row. We have Mel, 78, none, 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 none. Going across, when we get all the way down here, we'll see Max Randall about number 3. And the first thing this does is this flags me that I brought in a bunch of information up here that we really didn't want. It's from 3 on that we want. And we can clean this up in one of 2 ways. We can try to clean it up under the data, or we can clean it up under the data frame, depending on what it is we're trying to do. And so to fix this, I want to go ahead and just change it up here in the actual data pull-in. We don't need that information. So I'll rerun it, reload our data from 4 on. And then when I run this, we see we have Max Randolph is right at the top of the list like he should be, and we have all the data going down. Now with the data frame, remember I said we don't usually print the whole data frame. We'll go ahead and do df.head. And this prints the first 5 rows, and you can see that we have 13 columns. Here's Max Randall all the way to Theo Kinman. And I usually also print df tell. And the reason I like to do these particular 2 setups, and I'm going to change it just to 2 rows, because you can do that, you can print as many rows as you want, is it's good to look at the first part and the end, because those are usually where you have extra data brought in, something's messed up. And you can also see that we have 190 rows in here. And it comes in with our Zulma, Lisha, and they're both on here on the list. So now we have a nice data frame, columns and rows. We can easily look at it, we can see the setup on here, and we can look at the names and everything. Now at some point you might be looking at these individual columns and find different information that needs to be re-edited. If you can, you try to do it with the whole column under pandas. You can up in the upper part of the code where you went from cell to cell or row to row, you can look at individual cells, maybe you find a marker in that cell that's something specific, like remove all colons or semicolons or something in there, or brackets. So there's a lot of options in there, but you'll find that this one actually comes in pretty clean on here all the way down. And the next thing we really want to do is we want to look at the headers. I don't know about you, but it doesn't make any sense to me when I have column 1, I don't know what 1191 791 is, or 1080. Need name, Kaiser runner. I'm guessing that's column 2 is names. Third one, it looks like male or female, probably age, but I don't want to guess. I want this to bring in my column so I know exactly what I'm looking at. So how can we make Beautiful Soup do that for us? Well, let's take our column headers. We're going to set that equal to our soup, find underscore all, and then we're going to look for our headers, our TH files. And since we're in Jupyter Lab, in this case Jupyter Notebook, I can just type out column headers. If it's the last variable I have listed, it will automatically print it. So it's kind of a shorthand. And we can see right here we have place, I'm guessing that's bib, name, gender, age, city, state, chip time, chip pace, and so on. So we have all our headers right there. I shouldn't have to type them all in. And we'll go ahead and do it before. We'll go ahead and do a header list equals our empty array, and then we can do for column in column headers, and we can take our header list and just append. And what do we want? We want the text from the column, so we'll just do column.text. And then if we come down here and we print our header list, let's see what that looks like. If we did it right, we should get a nice list of all the different column headings we want. So we have place, bib, name, and so on. And then pandas, just because pandas is so cool, we can simply do df columns equals our header from our header list. We can simply set df columns set to df headers, and then if I print df.head, we'll take a look at that, and we'll see right here it has nicely placed our values on here. Place, bib, name, gender, age, and so on. So very quickly we've created this nice data frame. We have the data displayed in nice rows and columns and easy to read. And then as a data scientist, the first thing we want to know is the info. What is in these columns and rows and headers? And you see right here they all come up with non-null object. There's a big flag. So if I want to do anything with this, these are all coming through as strings or an object. I usually mean strings in this case, that they're a string variable. And we have, you can quickly read through this, 191 entries, date columns, total 14 columns. There's a total of 14 columns in the data, and it shows you all the different names and what type of column they are. And it's probably good also to look at the shape of the data. df.shape, we'll go ahead and just run that. You can see it's 191 by 14, 14 columns, 191 entries. This is more like we look at a NumPy array, 191 by 14 for the shape. And remember, this is a variable, so if I put it on, if it's a last variable or last value in the set of cells, Jupyter automatically prints it out. So if you're in a different IDE, you'd want to go ahead and use the print statement on here. And then one of the things you'd want to also go through, we'll create a second one, df2 equals df.dropNA. Now the axes is automatically equal to 0. So a lot of times you'll see something like axes equals 0, comma, how equals any. Axes equals 0 is default. That means we're looking at going down the rows. You could look at the column going across. Let's remove the how any because that's just going to confuse you. The axes is whether you're going down the columns or if you're looking at it row by row by row by row. Or you could be looking at it by column by column by column. This would drop any column and it would drop off the NA in any column. And how equals, and we want any. I always confuse all and any because they both start with A. All means that all of them have to be non-value, where any means that any of them can be there to drop it. So this would drop any column with a null value in it. But we want 0, and it'll drop any value with a null value. And then because 0 is always the default, we'll just leave it out. And then it's curious as to what the shape is now. Did we lose anything? Was there any null values in our df2 that we dropped from the df? And we'll go ahead and run that. And we see 191 and 14. So we didn't really drop anything. But it's always good to check. There's other ways you can also do, are there, let's see, any NAs, you can detect NAs in here. Null values, infinite values, that's another one you got to watch out for. We're working with data that we're going to do something with here in a minute, so you got to be a little careful also in the conversions. Are you going to convert something where people typed in weird characters to describe the data a certain way? So now we've got to this point where we have all our different columns, we have our different data, and at this point maybe you're asking, or maybe the shareholder of the company is asking, hey, can we look at the, based on the chip time, here's our chip time, can we plot that versus gender? how does gender versus chip time compare? And so we can do that. We can take that, and the first thing we look at is we say, hey, well, chip time came in as a string, and that's going to be an issue. Now, there's a number of ways you can change this. One of them is we could go all the way back up here where we created the data and find a way to tag it and say, hey, whenever this cell text, maybe instead of appending this, I noticed that anytime there's 2 colons in it, that's probably a time signature, and let's convert all the time signatures to date time field or whatever. A lot of times you don't get that. You don't get that option. And that's always a question in bringing in data. Whether you convert the data coming in at the beginning, or do you wait till you have it, open it up, and then convert it when you go to use it. We're going to go ahead and convert it after we got it into our data frame. So we have our df2 here. We've dropped all of our NAs. We have a shape. In fact, let's do this. Since there's no difference between df and df2, well, we'll just go ahead and use df2. So let's go ahead and take our df2, and we want to take that specific field and convert it into some kind of numerical value we can use. And let's add another column. A lot of times this is something you want to do is where you want to go ahead and keep all the original columns and just add a new column in there. And this new column is going to be based on if we remember correctly, we had chip time. That's what we're going to look at. Okay, we want chip time versus gender. If we go into our pandas, we find out we have pandas to delta, and this is actually time delta. And then we just want to take our df2, and we're going to use the chip time column. So this is going to say, hey, let's convert everything in df2 chip time into a time delta format. That's the data type we're going to put it as. And we can go ahead and just run this. And if we go in here and we do info, df2, and we'll keep we're going to look at this particular column, but we want to keep it as a data frame. So this is a list of all the columns we want to look at. We'll just do .info on here and run that. And we do an info on that. You can see it's now a time delta 64 nanoseconds. Well, we really don't want nanoseconds. We actually probably want to do it in minutes. So let's take a look at that. And let's take this whole thing, df2. Let's just set the df2. We have our df2. This is a column we're working with here. And we can use the as type property in Pandas. And so we can set this equal to df2. We'll take our same column in here, and we'll set it as type time delta second. So it's still a delta time here. So if I run this, you'll see that it still comes up as, where is it? Oh, it turns it into a float. So we're now at a float 64. So it's a number of seconds in that delta time. And then finally, we want to go ahead and turn that from seconds to, say, minutes. And there's 60 seconds in minutes. And so now we divide by 60. We still have a float. We have our info that shows us it's a float. And then we can go ahead and just do a print df2. And let's just keep it small. We don't want to look at all our data. We just want to do the head of it. And we run this, and you can see right here where we go to, it'll be the last one. Here's our chip time in minutes. And a lot of times, just to make life easy for viewing, since we're only looking at this particular element, we can do chip time in minutes. And now we just see that, oops, we take off. We'll go ahead and take off our info. Done with that. And we'll run this. And you can see we have our minutes. 16.8 minutes, 17.51 minutes, and so on. It's a float number. Now keep in mind, this is 0.8. That's not 16 minutes and 80 seconds. That can always throw you if you're going through so many numbers you forget. So important to remember that. And we're also going to look at, the other one we're looking at is what? Gender. We want to look at gender to chip time in minutes. And so we can see here under the head we get male, 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 and a number of different setups. And let's switch this to tail real quick and just look at the end of it. And here we have female, female, male, female, female. So we have two different genders, and we have our chip time in minutes. And if you remember, we brought in our PLT. If you haven't used the plot library, the Matplot library, you have a drawing place you're putting stuff on. So we have our PLT. We're going to do a bar graph, and we just want to simply use our df2 gender and df2 chip time in minutes. So that's going to plot the two bars. And to make it pretty, we'll go ahead and give it the X label gender, the Y label chip time minutes. And that simply is, remember, it always plots X and it plots Y. We have our gender, our chip time. Give it a nice title, comparison of average minutes run by male and female. And if we go ahead and run this with the correct titles in here and everything matches, you'll get a nice graph. We can see here the comparison of average minutes run by male and female. Here's our chip time in minutes. The men seem to be slackers in this particular case. And it's actually, there's a number of studies that show that women tend to have, as far as doing cross-country, there's a lot of women who have a longer endurance than men. So it's not too surprising. But we can see here the average chip time around 70, and for women over 100 minutes. And then another really cool thing we can do is we can describe the data. So df2.describe, this again is a pandas function, just like info is. And we're going to include NP number, the NumPy number. And if we run that, you'll see here it comes up and it says chip time in minutes, count, it gives you the average or the mean, standard deviation, the minimum, the maximum, all the different descriptive information you're going to want from your data set on there. And just because there's all kinds of fun ways, let's do a box plot to display your information. We can do a box plot where the column equals chip time in minutes. And let's go ahead and run that. Keep mistyping my chip time in minutes. You can see it puts out a nice box plot showing you the information. We have our different values and floaters. And this is always interesting because this is a nice way of seeing where we have these floaters, one up here and there's two up above, and of course your nice spread on the box plot. And we can also modify this a little bit, and we can add in by equals gender, and then we'll just give it a blank title. I don't know why we're giving it a blank title. We'll just add a Y plot, Y label on there for runtime. And if we run this, you can see here box plot grouped by gender, chip time in minutes, and now we have our female and male, two different areas, and you can see how they vary. You have your two different your outlier up here, and you can also see how there's such an overlap between the two different values. So if I was looking at this, I'd be like, wow, I really could not draw a conclusive thing on this saying that women's runtime was more in general because they overlap too much. That would be one of the conclusions I'd have to come up with on here. And then we get to maybe the partners come in from the company and say, hey, we'd like to know the age versus chip time in minutes. That'd be something worth knowing on the statistics on this. And the first thought is we can simply plot it. And we can do this. We can actually plot the scatter plot, chip time versus df2 of age. There's our XY coordinates. But if you remember from df2 when we did the info, let's go way back up here, we're looking at a data object as far as our chip time on this and our age. Now we converted the chip time, but we also need to convert the age. And if we do it right here, we just plot it, and it'll actually let us plot it. It shouldn't. It should give us an error, but it does let us plot it. You'll see the ages come up a mess over here because they're converting it to weird float numbers and all kinds of things. So what we want to do is we want to take our age, and we'll just call this age underscore I. So we're going to take our age and we're going to create another column for df2 age underscore I. And the I is just going to stand for integer. It's our own choice of values. There is a number of ways to do this, but we're going to do pandas to numeric is the best way in pandas. And the reason we're doing this is that numeric creates a float value. So right off the bat, we want all our stuff converted. It converts it to the least common denominator. So if they're all integers already, you'll get integers. As you can see from here, it's doing some kind of conversion that converts it to a float value. The other thing that numeric does is if there's a null value, or they put in like a blank line or a dash to represent no information, it'll convert it to a null. So it goes from like a string to a null versus just having some kind of made up number that Python somehow created for the graph we have below. And then we want to add our df2 age, because that's what we're converting to numeric, and then we want to coerce it. And there's a couple different options on this, like you can have it where it just doesn't process it in pandas, but coerce means that if it gets a weird value, that is a null value now. And since we're dealing with errors, this is what happens when you get an error converting it. We want to coerce it. There we go, and put the end bracket on there. And then finally we want to go ahead and round this off. So I'll put brackets around all the way around it, and this rounds off everything in this series. So what we've done here is I've taken df2 age, which is a D-type object, which in this case is mostly strings with a couple of blank ones in there, and we're going to convert it to a numeric, which will automatically go to float. And then we're going to take wherever there's an error, wherever it says, hey, this doesn't convert, and usually that's a blank string. Like I said, I've worked with so many databases where someone puts down none, someone types in space, some types in a dash to mean none, and you get this really weird conversion coming up. This covers all of that in pandas, so it's really a nice way of just coercing it and saying, hey, if we don't have a number in there, let's make it a null value, and then we're going to round it off. And then finally, let's go ahead and take our df2. Here's our df2, and let's drop those null values. Drop NA, and we want how equals any. So that means if there's any null values in the data set, now this might get you in trouble because you might have null values in a different column, and so you might lose data that way. At this point, we could also do like certain parts of like drop just certain columns with null values. There's all kinds of other options in here. But we're just going to do how we're going to just drop any, and we want to do it inline equals true. So that means it's going to reassign it to df2. So df2 now has rounded out, so it's rounded to the integer. We didn't do any places. The age, and it's going to be age I, and then we've dropped all our null values. That way we're not going to get any errors when we try to plot a null value. And it also makes sure that data, by deleting out the rows, because that's what this does, it automatically does axis 0, which is your rows, axis 1 is your columns. By doing this, it automatically removes all the rows with null values. So it just cleans out the rows. And then when we go ahead and plot this, we see we have a nice clean data, and we have age all the way up to 70. So we have our chip time set, and then our age going across. And it makes a nice plot that you can easily show for display and for and you can easily show that to your shareholders or whatever group you're working on. It makes a really nice and quick, easy display.
Python programming language is one of the hottest language right now. Major companies like Netflix, IBM, and YouTube uses Python in their tech stack, and the job of the Python developer is one of the most sought after in the market. So, in this session, we'll discuss 12 tips that will help you land a job as a Python developer. So let's get started.
So let's begin. Tip number 1, build your own GitHub repository. So go on GitHub, create a repository and add all your files, all your Python codes on there. So it doesn't matter if it's a big project or some small piece of code where you just took some input and made some manipulations, displayed it. Every work counts. Learn a bit of GitHub version control. So not only do you upload your file once, but you can make modifications to them, rework on them, make it better, upload it again, showing your progress. Now this GitHub repository basically becomes your resume as a Python developer. The recruiters can look directly on here instead of you sending them zip files or even Jupyter notebooks. Everything is now available online and they can access it from anywhere through any machine. So this really shows that you're not just writing code for yourself, but you want to share this with other people. And that's very important. Tip number 2, make sure that your code is readable. So when you're putting your code out in GitHub, as I mentioned previously, you're writing this code not just for yourself. So if people want to learn from your code, they want to view your code, it's necessary that they understand this code. And of course, there are a few guidelines to follow which makes your code more readable. The most important one being you follow the PEP 8 style guideline in case of Python. So the PEP 8 style guideline is basically some conventions that you use, and that mainly talks about indentation. So in case of PEP 8, you have a 4-space indentation, tabs and spaces, there's maximum line length, which in case of PEP 8 is 79 characters per line. The line breaks that you need to put blank lines, for example, every major class or every major function needs to be separated by 2 lines, 2 blank lines. The source file encoding string quotes, white spaces in expression, trailing commas, naming conventions, and so on. So again, very basic thing, if you're having a variable, make sure the variable name shows what the variable stores, what it is used for, and it's not just some vague name such as var1, var2, and so on. Tip number 3, create a good documentation. Again, this helps with the readability and the understandability of the code. So one of the main things with creating a good documentation is having a README file in your GitHub repository. The README file should contain details regarding your project, what your project does, the various libraries used in your project, and so on. So this is a great help to anyone who is trying to learn from your code or implement them in a different way. Now here we have a screenshot of the README file created by Raymond Hettinger. It's present in his GitHub repository. Now, who is Raymond Hettinger? Well, that brings us to our 4th point. Raymond Hettinger, like another guy, Kenneth Reed, these are some of the very popular personalities on GitHub. They have a very unique style and a very neat and organized style of coding. And one of the great ways to develop your own coding skill is to look at other people's code. Now, when you're looking at other people's code, it's important to remember that you look at code which is of your own skill level. So if you're an intermediate coder, make sure you look at someone's GitHub repository who again codes on the intermediate level so that you're able to connect with that code. You could probably write the same code, but he or she writes it in a better manner. Now, these are some of the people who have great GitHub repositories. You can definitely learn a lot from them. Tip number 5, read books on Python coding. So you might know already quite a bit of Python. In fact, if you're looking for a Python developer job, there's a good chance that you are an advanced coder coder, but nothing beats books. Here are some of the very popular and well-renowned books for Python. Fluent Python, Automate the Boring Stuffs with Python, and so on. Now, Fluent Python is a great book to start with. What it does is it gets your Python concepts really strong. So now you'll have not only great skills, but also the perfect way to portray these skills. Tip number 6, grow your Python skill set. Of course, you can never stop learning, keep learning. And some of the very important things when you go for a Python developer job is to make sure that you know how to work with some of these Python libraries. In fact, make sure that while you can cover most of these libraries, there are certain ones that you have completely mastered. Some of the very popular libraries with Python are NumPy, SciPy, Matplotlib, TensorFlow, and so on. So learn these, master them, create projects around them, and finally put these all up on GitHub for everyone to view. Tip number 7, it's never enough to just know a language. You must know how to apply it. And with Python, some of its most important and popular applications are in the field of AI, machine learning, and data science. So master AI and machine learning with Python. Learn the various algorithms that these fields use and implement projects on them. As you can see here, we have 2 of the algorithms with machine learning. That's linear regression, k-means clustering. Neural networks is an algorithm used with deep learning. So make sure you have some of these applications up there in your repository. This displays your skill not only in Python, but also in other fields. And both of these going hand in hand just increases your value. Tip number 8, take freelancing projects to start off with. So far, I mentioned how you write your own code, you create your own projects. Now that's not enough. Take up projects by companies. Now these may be non-paid, they may be really low paid. Does not matter as long as you have something to show off. So you have a project under your belt that really pays off. Now some of the websites you can go to for freelancing works are Freelancer, Upwork, Twago, Truelancer.com, and so on. So this really shows to the recruiter that this person did not just learn Python, but he or she is always looking at how to implement them, how to use them. Tip number 9, make open source contributions. So you have your own GitHub repository, that's great, but now look into others' repositories. See if there's some value that you can add, and if you can, definitely go for it. This shows not only your skill, but also that you're a team player, you want to add value to work that is already existing. And that is a skill that's again really valued in organizations. So some of the popular ones include pipenv, which is the Python development workflow for humans. There's also Chatistics, where you can convert your Messenger and Hangout chat logs into data frames. Then you can solve your traveling salesman problems using self-organizing maps. And there's also a Python to BPF converter. So these are great places to make your contributions. In fact, we have the links for some of these in the description below, so please check them out. Tip number 10, start a blog and talk about what you have learned. So having your own personal blog will add a lot of credibility to your profile. In your blog, you can definitely mention where you started off from. That is, at a beginner level, what all did you know, how you took on your journey to where you are now, what materials you used to collect information, and what projects you took on, how you went about this, mention any papers you wrote, and so on. All this again becomes another profile for you. The recruiters can have a quick look at your personal blog and have a good idea of what kind of a learner you are, what kind of a coder you are, and if you have done everything right, this could create a great impression on the recruiters. And if you have done everything right, this will create a great mark on the recruiters. So here's a screenshot on NetBachelor's blog on Python. It'll give you a good idea as to how to create a blog and how to go about it, so please check that out. So here's a list of all his blog posts. He has 227 blogs just for Python, and he writes on various topics. For example, here we have a screenshot of, is Python interpreted or compiled? In fact, you can even include some of your personal views on Python, on the learning process or the learning curve of Python, and so on. Tip number 11, follow a daily schedule for practice. So just because you think you have mastered the language, do not put it aside and let it collect dust. Take out some time every day, write code whether small or big. Make sure that every aspect of Python is at your fingertips. And finally, tip number 12, keep your resume and profile updated on job portals such as LinkedIn, Indeed, Glassdoor, and Career Builder. Look out for Python developer job roles on these sites and Google Jobs, Simply Hire, Dice, and more. A recently updated resume always captures the eye of the recruiter. So these these are some of the tips you can follow to bag that Python developer's job. If you're new to Python and require some help in gaining the skills to attain that job of a Python developer, you have come to the right place. Just go to our website, simplilearn.com, and in here we have just the course for you. In fact, we have a number of courses for Python, but you can start off here with Python training course. This course covers everything A to Z for Python, and it's pretty much all you require to get that job. So before you take up the course, you can definitely go through everything that it covers, the objectives, who should take up this course, the prerequisites, what projects are covered under the course, and also the subheadings of the various topics covered.
Today, we'll be discussing the jobs, skills, and resume that is related with Python. So, let's move forward.
So here is the agenda for the session. First, we will go through a quick intro to Python. Then, we will understand who exactly a Python developer is. After that, we will go through the skill set of a Python developer, the job roles that are suitable for Python developers, the current salary trends of a Python developer in the tech industry, and in the end, we will have a look at the resume of a Python developer to get insights into real-world credibility and employability of a Python developer. So without further ado, let's get started. Introduction to Python. So let's quickly go through this very concise Python intro. Python is an interpreted, high-level, interactive, object-oriented scripting language. Python is very versatile in nature and therefore its applications are spread to various fields in the industries, more popularly in web development, machine learning and AI, and game development. So who is a Python developer? Let's answer this. So here are some of the technologies used by a Python developer. Pandas, Anaconda, TensorFlow, Python IDEs, Django Web Framework, and PyCharm. A Python developer is one who develops backend components of a web application using Python when working as a web developer. Now, the web frameworks like Django and Flask are used for this purpose. A Python developer is also the one who writes effective, testable, and scalable Python code. He also performs data analysis when working in the field of data science. So basically, a Python developer develops, deploys, debugs, and maintains a project. So let's go through the skill set of a Python developer. Now, the core Python skills that a Python developer possesses are data structures like arrays, list, stack, queues, trees, and graphs. There's OOP concepts like inheritance, classes and objects, and abstraction. There's packages and functions, that is importing external packages into a Python code. Database and its connection, that is connecting a Python backend to a database like MySQL. When it comes to data science skills, there's NumPy, that is a library for performing mathematical calculations. There's Pandas, that is the library for storing and manipulating data efficiently. There's SciPy, and then there's Matplotlib, which is a library for plotting charts and graphs for a given data. And finally, there are machine learning algorithms, which consist of models like supervised learning, unsupervised, etc. Now coming to web developer skills, there are frameworks like Django and Flask for backend development of web applications. And then there's web scraping, which includes taking data from websites and converting that data into usable format. There's API handling, which is basically handling API requests for a web application to perform server-side operations. And finally, there is backend connection, which basically involves the backend part of a web application and is usually handled by Python frameworks. Now moving on, let's look at the Python developer job roles. First up is Python web developer. Now a Python web developer usually writes server-side code, works on the web frameworks like Django and Flask, collaborates with the data team to gather end users' requirements, develops the server-side platform, deploys applications, performs tuning, usability, improvement, and automation. Moving on, next job role is data analyst. Now a data analyst generally works on Python libraries including Matplotlib, NumPy, Pandas, etc., carry out data analysis, collect data using the scripting language, explore data sets, gather requirements, tune in applications, analyze problems, communicate findings with the team or stakeholders. The next job role is automation test engineer. Now, an automation test engineer usually works on Python test framework tools, including PyTest, PyUnit, perform complex system tests, troubleshoot code issues, create test scripts, design the automation framework, perform A/B testing. Next up is machine learning engineer. Now, a machine learning engineer has the following roles: to perform statistical analysis of data, put machine learning models into production, research and transform data science prototypes, research and implement appropriate ML algorithms and tools, perform ML tests, and keep updated with the ML trends. The last job role is software engineer. Now, a software engineer is expected to write server-side code, collaborate with the design team to gather end users' requirements, develop the server-side platform, deploy applications, perform tuning, usability improvement, and automation. Moving on to the next topic, let's look at the Python developer salary trends. Now, software engineers with Python skills are offered better salaries across the globe. The average salary of a Python developer in India is around 7,55,000 rupees per annum. The average salary of a Python developer in the US is about $79,000 per annum. Moving on to our last segment, Python developer resume. So let's go ahead and understand what a Python developer resume should portray. Just keep a few things in mind when you're preparing your resume. Your resume should be clear, updated, and concise. You should prioritize the skills according to the job role you're applying for. And do not write anything extra. That's a big no. The recruiters are smart enough to know that. So do not lie and do not write extra. Firstly, let's look at the fresher resume. So if you're a fresher, these are some of the points that you need to know. First, you have the resume header. Now, the summary is supposed to be clear and concise. Just say what exactly you want and some of your strengths. Next is the profile links and your portfolio. So you can mention your LinkedIn profile link and also your GitHub repository link if you have. Next up is the projects. Now, clearly depict the goal of your project. So just in case you worked on, say 5 projects, make sure you keep it concise and crisp. Next up is your education. Do not lie here. Make sure you give relevant education with grades. Next, you have the certifications. If you have any certifications or achievements, go ahead and write them down. Next, you have the technical skills. Now again, prioritize according to the job role. And lastly, you have your non-technical skills. This could be your communication, analytical skills, problem-solving skills, etc. Moving on to an experienced developer. So again, mention the resume header. Then you have the summary, again very crisp and clear. Go ahead and mention your portfolios and your links. Coming to experience, now here you'll have to clearly depict your work. You'll have to make sure that you write down all your responsibilities in that company. Do not go overboard and write extra. Keep it very concise. Again, relevant education and your grades. You have technical skills. The same goes for this as well. Prioritize according to the job role. And finally, you have your non-technical skills. So there you go. By now, you must be aware of all the skills and job responsibilities of a Python developer, and I'm sure you're ready to build your resume for the next interview. We also have a Python YouTube playlist that covers everything from the basics to advanced Python concepts. Don't forget to check that out if you're interested in Python development. The link is added in the description box below.
We will be discussing the top 10 reasons to learn Python in 2022. So, let's begin.
The first reason we have is Python is versatile. Python is a totally versatile language as it is being used widely in artificial intelligence, data science, machine learning, web development, embedded systems, graphic design applications, data mining, gaming, and others. Python is used as an easier and more effectively written alternative to languages that perform similar functionalities like R and Java. Now, talking about the second reason why you should learn Python in 2022, we have Python is the fastest growing programming language. Python programming has become one of the fastest growing programming languages in the world and is the primary language for many applications. Its popularity has grown both in India as well as in the US. In January 2021, Python was in the 3rd position in the TOB index. In January 2022, which is this year, Python has become number 1 in the TOB index of popular programming languages. The ratings are based on the number of skilled engineers worldwide, courses, and third-party vendors. Popular search engines such as Google, Bing, Yahoo, Wikipedia, Amazon, YouTube, and Baidu are used to calculate the ratings. Coming to our third reason, that is, Python is beginner friendly. The main reason why Python is an excellent choice for beginners is its simplicity. Python supports English syntax and is designed to be concise and easy to read, all of which make it more accessible to first-time coders. It is an interpreted programming language. This means that you can run each line of code once you have finished writing it, allowing you to immediately check it and make adjustments if needed. The fourth reason we have is Python libraries and frameworks. Python provides numerous libraries and frameworks that cater to every need of the user and its clients. It has NumPy and Pandas for numerical computation and data manipulation, SciPy for scientific computation, Matplotlib and Seaborn for data visualization, scikit-learn for machine learning, statsmodel for statistical analysis, and much more. Python also supports frameworks such as Flask and Django for web applications. You can also do cross-platform and cross-browser testing with frameworks like PyTest and Robot. Now moving ahead, the fifth reason we have is Python for data visualization. Python is a great programming language for data analysis and data visualization, so it supports libraries such as Matplotlib, Seaborn, Bokeh, and Plotly for creating interesting visualizations. You can make sense of complex datasets and visualize your findings through various representation options like bar graph, pie charts, graphical plots, geographical maps, and much more. Now moving ahead, the sixth reason we have is extensive online documentation. Python has been adapted to the latest advancements with developers continuously releasing new and improved versions. Python language is very organized and its libraries have coexisting documentation, letting you jumpstart straight into programming. You will also find example codes where you can see the functions implemented, so reading the documentation is a good way to improve your knowledge about Python. Moving on to the seventh reason why you should learn Python in 2022, we have Python is great for scripting. Python is also used to write scripts to do automated tasks such as backups and cleanup in servers. In Python, you don't have to compile the code in order to interpret it. You can directly write code in the script and execute it. The machine reads, interprets, and runs the required tests and also performs error checking. Now coming to the eighth reason, we have Python for cybersecurity. Python has been dominating the cybersecurity industry and has been around for a long time now. It can help to automate tasks across the cyber attack lifecycle for both cyber attackers and defenders. You can develop custom Python scripts to automate cybersecurity tasks with libraries such as Nmap, Yara, Skippy, and Twisted. Python is used heavily in malware analysis, host discovery, sending and decoding of packets, accessing servers, and network scanning. Now moving on to our ninth reason, we have Python community support. You always need a community to learn new technology, and friends are your best asset when it comes to learning a programming language. The Python programming language has a global community with millions of software developers who interact online and offline in thousands of virtual and physical locations. In case of any coding related issues, you can always seek help from the Python community. As shown on the screen, Python has a robust and supportive online community with over 1.5 million GitHub repository. Communities such as Stack Overflow also bring several Python experts together to help newbies. Now moving on to the 10th reason in our list, we have Python jobs in high demand. As Python is getting more popular, along with an increase in an active community and its functions, the demand for Python professionals is also increasing. Python jobs are increasingly growing in every business sector and provide high salaries. Python developers is one of the highest paid jobs in the United States. The average salary of a Python developer in the US is over $96,000. So those were our top 10 reasons to learn Python in 2022. Python is the most popular programming language in industries when it comes to data science, web development, and machine learning. The questions and answers covered in this video will give you an understanding of solving basic, intermediate, and advanced level Python problems, as well as give you an exposure to Python data science questions. So let's begin.
Number 1, what is the difference between shallow copy and deep copy? And you can see with shallow copy we have object 1, which has child 1, child 2, child 3, and so on, and object 2, which has child 1, child 2, child 3. A deep copy creates a different object and populates it with the child objects of the original object. Therefore, changes in the original object is not reflected in the copy. Copy.deepCopy creates a deep copy. Shallow copy creates a different object and populates it with the references of the child objects within the original object. Therefore, changes in the original object is reflected in the copy. Copy.copy creates a shallow copy. And you can look at this. If we make a change to child 1, it's only a pointer. So if you make it in object 1 and a change to child 1 in object 1, it will also make that change in object 2. Number 2, how is multi-threading achieved in Python? Oh, this is a good one. With multiprocessing and multi-threading, this question is actually asking you, do you know the difference between multiprocessing and multi-threading and how multi-threading works? Multi-threading usually implies that multiple threads are executed concurrently. The Python global interpreter lock doesn't allow more than one thread to hold the Python interpreter at that particular point of time. So, multi-threading in Python is achieved through context switching. It's very different than multiprocessing, which actually opens up multiple processes across multiple threads. So, multi-threading. Discuss the Django architecture. So the Django architecture, and the first thing to know is that the Django is a web service, way to build your web pages basically. And so when you look at the architecture, you can see here we have a nice model drawn out where the user initiates the Django, which initiates the URL, which initiates the view, what they're going to view, and you have your model and your template. So the model of data, whatever data model you're pulling, goes into the template and then goes back up the pipeline to the user. And the important thing to note is there's a template, the front end of the web page. This is what they're going to see. There's a model, the back end where the data is stored. So you can keep the template and the looks and everything looks the same, but you can swap out the underlying information that goes into that template. Then you have your view, which interacts with the model and template and maps it to the URL, and then the Django serves the page to the user. So your Django grabs it and says, okay, thank you for the URL, and here you go, user. What advantage does NumPy array have over nested list? So NumPy is a module you import. Almost always see NumPy, import NumPy as NP. NumPy is written in C, such that all its complexities are backed into a simple to use module. Lists, on the other hand, are dynamically typed. Therefore, Python must check the data type of each element every time it uses it. This makes NumPy arrays much faster than lists. I would also add in that NumPy has a lot of additional functionality that you don't have in lists. So there's a lot of things you can automate in the NumPy. Quick flip over to our Jupyter notebook. Any IDE will work. If you're going to do a set of interview questions, taking a quick look at code is always important. We have our import NumPy as NP. We'll go ahead and import time. Here's our list sub for I in range of 100. And what we're doing is we're going to time it. So we're going to create a list, then we're going to create a NumPy zeros array. And you can see here, look how quick you can create this NumPy zeros array. Here we are appending 1 0 at a time for a regular Python list, and here we are with NumPy. They're all zeros, and they're all of type integer. I believe it's either float or integer on this. I'd have to actually do a type on it. And then, so if we take in and we create a TL1 time equals time, and then we do for I in range of 100, for j in range of 100, L of I, j equals L of ij plus 5. So we're just doing a simple calculation on our array and subarrays. This is an array of arrays. And we'll do the same thing with TL2. TL2 time.time, TL1 equals, so here we have our final time on that. And then we'll do this with an array op, and this is what I really love, a equals a plus 10, and then you can just print it right out. So you can see right here with a NumPy array, we're doing the same thing. If I run this, our time is significantly different. Here we have 0.09 and 0.003. So you can see that the time drops significantly when you're running this on a NumPy array versus a list array. Also important to note, these times aren't going to be, they'll change each time I run it depending on what I have running in the background. So there we go. Number 5, what is pickling and unpickling? Amazes me how many times I pickle and unpickle something. Converting a Python object hierarchy to a byte stream is called pickling. Pickling is also referred to as serialization. Unpickling, converting a byte stream to a Python object hierarchy, is also called unpickling. Unpickling is also referred to as deserialization. So if you just created a neural network model, you can now save that model to your hard drive, pickle it, and then you can unpickle it to bring it back into another software program or to use at a later time. How is memory managed in Python? Number 6. Python has a private heap space where it stores all the objects. The Python memory manager manages various aspects of this heap like sharing, caching, segmentation, and allocation. The user has no control over the heap. Only the Python interpreter has the access. You have a nice little diagram here. Here's your program. There's your interpreter. We have our heap, memory management on the garbage collector going off of there. Number 7. Are arguments in Python passed by value or by reference? Arguments are passed in Python by reference. This means that any change made within a function is reflected on the original object. So you can see here def function of L of 0 equals 3, L equals 1, 2, 3, 4, function L, print L, and you're going to get 3, 2, 3, 4 because we passed L in there, so it's a pointer. Here we have def function L equals 3, 2, 3, 4, L equals 1, 2, 3, 4, function of L, print L. Because in this function I have assigned, instead of operating on a piece of L, the list, I've assigned a whole new value to that list, or L. It then at that point will create a new object. So if I make changes to the object, it's going to change it in the outside the definition. If I use a variable and I assign it a completely new value, like L equals 3, 2, 3, 4, that will not show up when you're outside the function. Number 8. How would you generate random numbers in Python? To generate random numbers in Python, you must first import the random module. The random function generates a random float value between 0 and 1. The random range function generates a random number within a given range. And you can see here 1 is the lower end, 10 is the upper end, and step 2. So it would be 1, 3, 5, and so on as far as the options in the random generation. Number 9. What does the double forward slash operator do? In Python, the forward slash operator performs division and returns the quotient in float. For example, 5 over 2 returns 2.5. To do a double forward slash operator, on the other hand, returns the quotient in integer. For example, 5 double slash returns 2. 5 divided by 2 and you drop the 0.5. Number 10. What does the is operator do? The is operator compares the ID of the two objects. And you can see in here where list1 equals brackets around 1, 2, 3, list1 equals list2 equals true. And you have the double equals in Python, of course. And you can do list1 is list2, where list2 equals 1, 2, 3 is false. List2 is not the brackets 1, 2, 3. It equals it, but it's not the brackets. And if we do list3 equals list1, then list1 is list3 equals true. Number 11. What is the purpose of pass statement? The pass statement is used when there's a syntactic but not an operational requirement. For example, the program below prints a string ignoring the spaces. And so here we have variable equals simplilearn. We've added 2 spaces in it. For I in variable, so it goes through each I. If I equals space, do nothing. Else, print I, and then we'll have the end equals bracket bracket, and they'll print out simplilearn. Now, of course, you would probably write this if I does not equal blank space, print. But this would be another way you could do that if you need a placeholder for that first logical set or that first area. And you can also do a function like this. You could do function, whatever your def function name, brackets, colon, pass. So it goes into the function and does nothing, but it's a placeholder. Number 12. how will you check all the characters in a string are alphanumeric? Python has an inbuilt method, isAllNumber, which returns true if all characters in the string are alphanumeric. And so you can see here, ABCD, 1, 2, 3, isAllNumber, output equals true. And the second line, ABCD, the @ symbol, 1, 2, 3, the pound symbol, isAllNum, output equals false. So really you just want to know about isAllNum, all numerical, alphanumerical. Number 12. How will you check if all characters in a string are alphanumeric? So here we go. If you know isAllNumber, which returns that the characters in the string are alphanumeric, one can also use regex instead. And so we have Boolean rematch. What's important about this is to note your capital A dash to capital Z, A lowercase to dash to Z, 0 to 9 means that that array includes all of those, the way they have it written out, plus a $, and then we have what we're comparing it to, the string we're comparing to, the ABCD 1, 2, 3. And so we can do an re.match, and if it matches, if all these things, if all the different entities in that array matches the first one, we'll get an output true, and if not, an output false. Number 13, how will you merge elements in a sequence? Sequence. There are 3 types of sequences in Python. There's lists, tuples, and strings. Python, of course, makes this easy. If we have a list 1 and list 2, and list 1 is square brackets 1, 2, 3, list 2 is 4, 5, and 6, we can simply do list 1 plus list 2. And our output is 1, 2, 3, 4, 5, 6. If we have tuples, your tuple is the curved brackets designates it, and again, just add them together. Same thing with strings. We have simplilearn, S1 plus S2 equals simplilearn. Number 14. How will you remove all leading whitespace in a string? Python provides the inbuilt function lstrip to remove all leading access from a string. And you can see here, space python dot lstrip, leading strip, Python. And you can also do strip, which relieves leading and ending. And of course, there's also the ending set. Number 15. How will you replace all occurrences of a substring with a new string? The replace function can be used with strings for replacing a substring with a given string. Syntax: string.replace old, new, count. Replace returns a new string without modifying the original string. Hey John, how are you, John? ? Replace John with capital JOHN 1. And then you can see right here, hey John, how are you? And since we designated with the 1, just says we're only going to replace one of these. 16. What is the difference between del and remove brackets on lists? Del for delete. Del removes all elements of a list within a given range. Syntax: del list start to end. Remove. Remove brackets removes the first occurrence of a particular character. Syntax: list remove element. And we see a nice example over here. If we delete the list 1 to 3, it will delete the first, in this case B 1, 2. It doesn't do 3, remember that. 1, 2, so it will delete B and C and you end up with a D. Where if we do remove B from the list and we have an ABBD, it's only going to remove the first B. Number 17. How to display the contents of text file in reverse order. Open the file using the open function. Store the contents of the file into a list. Reverse the contents of the list. Run a for loop to iterate through the list. Number 18. Differential between append and extend. Append adds an element to the end of the list. You can see right here we have a list 1, 2, 3, 4, and we append 4, and we end up with an output 1, 2, 3, 4. And extend adds an element from an iterable to the end of the list. And we have here list equals 1, 2, 3, list.extend 4, 5, 6. Output is 1, 2, 3, 4, 5, 6. So if you want to append an array to the end of another array, you want to use the extend. Number 19. What's the output of the below code? Justify your answer. This is a great interview question because these are the kind of things that come up when you're proofing code. Def add to list, value, and list. So we have value in and a list in, or list equals an empty, in this case, an empty list. List.append value, return list. List 1 equals add to list 1. List 2 equals add to list 1, 2, 3, empty bracket. List 3 equals add to list A. And then we want to print them. List 1 equals, and you can see the formatting. We have our placeholder, list 1, list 2, and list 3. So when it prints list 1, we get 1, comma A. And what you want to notice here is that list 1 and list 3 are equal. Why are they equal? Well, when we passed the information to the add to list, we passed value without passing the list equals brackets, without passing a second value. What this means is that list, as we have it, if you don't have a list, it'll start off with empty list, which we append the 1 to. The second one, list 2, we appended a value to an empty list. So it's only going to be 1, 2, 3. It doesn't matter what the list was before, we've already assigned an empty list. And then list 3, here's the tricky one. We're adding a to the list, but because we didn't designate the list is a shared value. In other words, it doesn't reset it. And we end up with list 1 equals list 3, 1, a. Default list is created only once during the function and not during its call. Number 20. What is the difference between a list and a tuple? Lists are mutable while tuples are immutable. And you can see an example down here where I have list equals 1, 2, 3. Square brackets denote it's a list. List of 2 equals 4, and I print it out and I now have 1, 2, 4. If I do the same thing with the tuple, I get an error, because you can't change the tuple 1, 2, 3 into 1, 2, 4. You have to completely reassign tuple to a new value. What is docstring in Python? Docstrings are used in providing documentation to various Python modules, classes, functions, and methods. And so you can see here we have def for a function, add AB, and this is a docstring. We have the triple brackets on there. You can add carriage return in that so that you can go multiple lines. And it says this function adds 2 numbers. And then sum AB returns sum. And so we have down here 2 different ways of accessing this function. Output, accessing docstring method 1, this function adds 2 numbers. Accessing docstring method 2, help on function add in model main. This function adds 2 numbers. And so you can see the code down here has 2 very different end values. The second one is basically a help menu. There's our help menu. Number 22, how do you use print without the new line? The solution to this depends on the Python version you are using. In Python version 2, you can do print hi and then you add a comma afterwards. Print how are you? And you have hi, how are you? In version 3, print hi, comma, end equals, and it'll add a space on the end there. You can put different characters in there, but generally you just want to put a space on the end. Print how are you, and now we get hi, how are you? Number 23, how do you use the split function in Python? The split function splits a string into a number of strings based on a specific delimiter. So we have string, split, delimiter, comma, max, the maximum number of splits. The character based on which the string is to split by default is space. So here we have an example. We have a variable red, blue, green, orange, and we want to split it by commas, and we only want to do the first 2. So if we print the list now, you'll find it has red, blue. It only split it the first 2 times, and then it gets to the third one and just groups them all together, green and orange. If you leave the 2 off, it'll split the whole thing. Number 24, is Python object-oriented or functional programming? Python follows object-oriented paradigm, and you should really know in depth what they mean by object-oriented paradigm if you're doing any interview for scripting languages. Python allows the creation of objects and its manipulation through specific methods. It supports most of the features of OOPS, which has inheritance on a polymorphism. So you have an object and you can inherit all the traits of that object and then add new traits in or alter some of those traits. That's what object-oriented means. Python follows functional programming paradigm. Functions may be used as first-class object. Python supports lambda functions, which are characteristic of functional paradigm. So you can set a variable to a function as opposed to setting it to an object. Number 25. Write a function prototype that takes variable number of arguments. Here we have def function name list. So we could have, in this case, whatever the list is, def function. The asterisk denotes, so we're going to take multiple arguments of a variable, and then we can do for I in var, print I. So if you send function of 1, you'll end up with a function 1, 2, 5, 6. It'll actually print those out one at a time. The first one just prints out a 1 because it only sent one variable. The second one will print 1, another line 25, another line 6. Number 26. What is asterisk args and asterisk quargs? Args used in function prototype to accept varying number of arguments. It's an iterable object, def function args. And you can imagine it's just a basic list. So if I add the numbers a comma b or a comma b comma c, it doesn't really matter. It will have that number of objects in it, whatever I send to it. And there's other uses for it, but that's very basic. Quargs I can actually tell it what I want to send. So using a function prototype and to accept varying number of keyworded arguments. It's in both our iterable objects, so you can go through them one at a time, and the def function chords, you can now set like color equals red, units equal 2. So you'll see that, especially in machine learning, there's a lot of like they'll have inline equals true, that kind of thing. Number 27. In Python, functions are first-class objects. What do you understand from this? This means I could return a function. It could be one from another function. I could create a function and treat it just like an object. I can assign it to a variable. I can pass them as arguments to other functions. Number 28. What is the output of print name __ name? Justify your answer. The double underscore name double underscore is a special variable that holds the name of the current module. Program execution starts from main or a code with 0 indentation. Thus, double underscore name double underscore name has a value double underscore main double underscore in the above case. If the file is imported from another module, then double underscore name underscore double underscore holds the name of this module. Number 29. What is a NumPy array? And we briefly touched NumPy array compared to a list earlier in processing speed. Now let's go ahead and look at some of the more specifics. A NumPy array is a grid of values, all of the same type. So if they're either all float, all integer, all string, and is indexed by a tuple of non-negative integers. The number of dimensions is the rank of the array. And the shape of an array is a tuple of integers giving the size of the array along each dimension. Number 30. What is the difference between matrices and arrays? A matrix comes from linear algebra and is a two-dimensional representation of data. It comes with a powerful set of mathematical operations that allow you to manipulate the data in interesting ways. Now, an array is a sequence of objects of similar data type. An array within another array forms a matrix. Like we said here, two-dimensional, so if you have an array of 3 by 4, that would be a matrix. Number 31, how to get indexes of n maximum values in a NumPy array. Of course, the first thing to do is to import your NumPy as NP. You don't necessarily have to use NP, but that is the most standard use of NumPy. We create our array equals an np.array of 1, 2, 3, 4, 5. And then if we want to get our indexes of n maximum values in a NumPy array, we can do, one way to do it is to take our array, sort it, then do -n colon. That means we're going to do, once you've sorted it, you can do -n. N would equal then the number of indices, so it's not the actual letter n, colon. And really this is about understanding this notation, that we can sort it, so it goes from lowest to biggest, and then we can get the top values for n indexes. And then we have our final set of brackets with the -1 on there. Number 32. How would you obtain the resulting set from the train set and the test set from below? And let's go ahead and look at the two different variables. We have train set equals an array of 1, 2, 3. Test set equals a NumPy array of arrays. We have 0, 1, 2, 1, 2, 3. What's important here is that, one, it's a NumPy, so that leaves A out, and then we're stuck with 3 other options, and I'm going to say that D is out, none of these. And let's look at np.concatenate versus np.vstack. Concatenate would put one set after the other, so you would end up with, probably give you an error, because one set is 1, 2, 3, and then we're going to concatenate array 0, 1, 2 and array 1, 2, 3, the array of arrays, onto the end of that. What we really want to do is stack, and by the way, you can actually switch, there's variables you can put into concatenate, obviously, that can change this, so you could use the concatenate with a lot of fudging around. But really what we're looking for is VStack. V stands for vertical versus the HStack, which is horizontal, and if we do a VStack, we can simply do train set, comma, test set, and stack them together. And so we have C, resulting set equals np.vstack, train stack, test set. Both option A and B would do horizontal stacking, but we would like to have the vertical stacking. Option C does this. Again, you could add the axes in and use the concatenate to stack it the correct way. Number 33. How would you import a decision tree classifier in sklearn? We have sklearn.decisiontree import decision tree classifier. From sklearn ensemble import decision tree classifier. And we look at these and they're all import decision tree classifier. That actually have last part happens to be correct, and it's really just a vocabulary knowing where is the decision tree classifier stored, what module is that a part of, and it is of course part of the sklearn.tree. Number C. Number 34. You have uploaded the dataset in CSV format on Google Spreadsheet and shared it publicly. How can you access this in Python? What's important here is to know that we can read stuff with pandas. So we don't show it here, but you can. There's actually a number of ways to do this. What's important here is to know a couple things. One, we have our link generated from the Google Docs and spreadsheets, and then we can do a string.io request get link.content. So there's our source. And then finally, we know that pandas can read a CSV. There's obviously many ways to read a CSV, but data equals pd.read_CSV source. Number 35. What is the difference between the two data series given below? Below we have df name and df location, colon, comma, brackets around, asterisks around name, comma, where. And then we have df equals pd data frame, AABBXXUU, comma, 21, 16, 50, 33. Columns equal name and age. So let's take a look and see what they're looking at. We have, just glancing at the questions, they want to know, is it the original data frame or is it the copy of the data frame? And you can see here that 1 is view of the original data frame and 2 is a copy of the original data frame. 2 is a view of the original data frame and 1 is a copy of the original data frame. Both are copies, both are views. And if you're working with pandas, you know that unless you specifically on certain things tell it to do it inline, and a lot of functions don't allow you, that you're always taking a slice and it is always a copy. So C, both are copies of the original data frame. Number 36, you get the following error while trying to read a file, temp.csv using pandas. Which of the following could correct it? So here's our error. Trace back most recent call last, file input, line 1 in module, Unicode encode error. ASCII codecs can't encode character. Ooh, I hate it when that one comes up. And we have 4 different entries. We'll go ahead and just pretend that D doesn't exist unless we really can't fit it into one of the other answers. And the first one is PD read CSV has our file compression equals gzip. Well, gzip is just an unzipping and you actually get a zip error on there. The second one is dialect equals string. Again, not an encoding or coding setup. And then we have encoding equals UTF-8. Well, that would be the encoding error, switching it from the character code. There's UTF-8, there is Unicode. That's the most common two that it goes between. So really this is about understanding the difference between a UTF-8 coding and a Unicode and the error that comes up quite regularly with that. Number C, encoding should be UTF-8. Number 37, how to set a line width in a plot given below. So looking at this, we have import Matplotlib, PyPlot as PLT, and you should know your way around this, how to do a plot in there. PLT.plot 1, 2, 3, 4, plot equals show. And so this is a little bit of a vocabulary test. The vocabulary is at width equals 3, line width equals 3, LW equals 3, or something else. And the vocabulary word that we're looking for is LW equals 3, which stands for line width in PyPlot library, PyPlot. Number 38. How would you reset the index of a data frame to a given list? So this is a vocabulary challenge in understanding what reindexing is. Reindexing, as we have the different values here, we have the first one, which is reset the index. Well, we're not really resetting the index. Reindex number B means we are double checking our indexes to the column and to the main index, and so the values match correctly. Where reindex like now brings in a new index outside of our data frame to a given list. So this is coming from external, and thus the vocabulary word like is our key word, that it's external, and we have a data frame to a given list. Number 39. How can you copy objects in Python? The functions used to copy objects in Python, we have copy for shallow copying and copy deep copying for deep copy. Number 40. What is the difference between range and xrange functions in Python? Well, this is a good one. We have matrices and arrays. With a matrix, the range returns a Python list object. Xrange returns an xrange object. And with arrays, an xRange returns an xRange object. xRange creates values as you need them through yielding. The key here is that xRange returns the values as you need them. So it actually processes it post, like if you have for x or for a variable in xRange, it is processing them as you need them, 0 to 9. It doesn't create an array 0 to 9, it just hands you 0, then 1, 2, 3, 4, 1 at a time. Number 41, how can you check whether a Pandas data frame is empty or not? The attribute df.empty is used to check whether a Pandas data frame is empty or not. And so you can simply create we have down here import our pandas as PD. We create our pandas data frame equal to an empty array, and is df.empty comes out as true. One of the catches you got to remember with these vocabularies is with empty along with some other pandas setup, whether you need the brackets or not at the end. Number 42. Write the code to sort an array in NumPy by the n-1th column. This can be achieved using argsort function. Let's take an array x, then to sort the n-1th column, the code will be x to colon n-2.args_sort. So let's see what that code looks like. We import NumPy as np. We'll create our array, our NumPy array, which is 1, 2, 3, 0, 5, 2, 2, 3, 4. So we have 3 different entities with 3 different columns in there. And we go x of x, and so we take x of all the rows, first entity, or in this case it's actually the second one because it's 0, 1, 2, .argsort. So that would be the second entity, or -2 would also be the same. You could also do, instead of 1, you could also do -2 there instead of the 1. Argsort, and then we get an output of the array 1, 2, 3, 0, 5, 2, 2, 3, 4. Number 43, how to create a series from a list, NumPy array, and dictionary. So we'll go ahead and import our NumPy, our pandas, and have my list. And you can see here we have my list equals list of A, B, C, D, E, F, G all the way through. So my list now makes a list of that. For array, we have np.arange to 26. My dictionary will create a dictionary with zip my list, my arguments. So I'll just use the NumPy array we just created with my array to go into the dictionary. And the solution is simple with the pd.series, my list, pd.series, my array, pd.series, my dictionary. So it's all about knowing the dot, capital S-E-R-I-E-S. Don't forget that capitalization. Number 44. How to get the items not common to both Series A and Series B. And you can see here we have, instead of Series A and B, we have Series 1 and 2, and we have 1, 2, 3, 4, 5, 4, 5, 6, 7, 8. The solution is we take a panda series, we have a series U equals a panda series, NP union 1 dimension, Series 1, Series 2. So we can now make a union of them. We now have Series 1 panda series with an intersection, and then we can remove one from the other. Series U is Series U dot is in Series 1. So if the union is not in the intersection, then you know it's a unique value. A little bit of logic going on there and playing with 3 different terms to get the answer we want. 45. How to keep only the top 2 most frequent values as it is and replace everything else as other in a series. So again, we're working with pandas, because if you're talking series and data frames, that means we're working with pandas. So we're going to import pandas as PD. We'll go ahead and create our pandas series. We're going to do that by creating a NumPy random state 100, so 100 in the NumPy one. And then we have our pandas series. You can see here we're random integer, NumPy random integer 1, 5 by 12. And so the solution for this is we go ahead and we've created a PD dot, remember the capital S series solution. We're going to print the top 2 frequencies, and that is our series dot value counts. And then we take series values count dot index of up to 2. So we're going to take everything up to 2. And then we'll do the series is in. So if it's not in the first 2, then it's going to equal other. And this would be something you'd want to write down on paper. If it looks confusing, take a moment, pause the video, write this down, and see if you can figure out how the logic came together and try to throw yourself a couple other little logic puzzles like this. Number 46. How to find the positions of numbers that are multiples of 3 from a series. And in here we're actually going to use a NumPy to solve it. The first part, series, lets you know it's going to be a panda series. And if we come down here, we have np.argwhere, so this is a vocabulary question, series with, remember the percentile 3 is the remainder, so if the remainder equals 0, then we're going to generate that string where the object divided by 3 equals 0 has no remainder, so then we know it's a multiple of 3. Number 47, how to compute the Euclidean distance between two series. And this one's really cool because we have our Pandas series, P and Q. And what I like about this one is they give us two solutions you can go with. And really you should kind of know both. The first one would be, yes, you know what the Euclidean distance is. And that is we can take the first series minus the second series squared. And then sum them up, and then we do the square root, which is the same as taking the power to 0.5. Doing the power to 0.5 is easier than doing the square root. So a lot of times you'll see that as a switch, but you could have also done the square root and used the math in there. So there's solution 1, you should know your Euclidean distance. And then solution 2 is the NumPy solution. So we have np.linalg.norm. That's how we're going to compute our Euclidean distance. P minus Q. Very elegant and very straightforward and easy to compute. Number 48, how to reverse the rows of data frame. So here we have our data frame. We're going to create a NumPy array by 25, reshape it 5 minus 1. And this creates a 25 by 25 data frame. And so our solution is to do the df iLocation. And this is just understanding how steps work. The steps, you have your colon, minus 1. So we're taking all the rows, all the columns, minus 1. So we're stepping minus 1 going the reverse direction. And then we're just going to use across all the different columns on there. Let me say that again. The first colon is going to be your row, starting row, stopping row, step minus 1. That's all this is about, is that step minus 1, comma, and then all the columns. 49. If you split your data into train test splits, is it possible to overfit your model? And the answer is yes, it's definitely possible. One common beginner mistake is retuning a model or training new models with different parameters after seeing its performance on the test set. My favorite example of this is you have your script put together and you keep hitting the rerun button until you get the answer you want, not taking the answer it first gave you, or running it over an array and recording all the answers to see how they vary. Number 50, which Python library is built on top of Matplotlib and Pandas to ease data plotting? The answer to this is Seaborn. Seaborn is a data visualization library in Python that provides a high-level interface for drawing statistical information, informative graphs. We've covered 50 different questions that might come up on an interview. Hopefully you've taken the time to note the vocabulary where you're sticking and not having problems. You might have to go back and relook up VStack versus HStack versus concatenate, and also review the axes on those. Little things like that. Also, we address some logics. How do you formulate those different polls from a Pandas data frame so that you're looking at the right data with the -1 step, or in the NP array how we did brackets and really fiddled with it.
We will be discussing the top 10 most popular Python automation ideas. Now, without further ado, let's get started with the agenda for today's session. First, we will go through how and where Python fits in machine learning prediction models and algorithms. Then, we will look into web scraping, another popular application for Python automation. Python is also used for tracking stock market and cryptocurrency prices. After that, we will discuss chatbots, another increasingly popular customer care experience. Later, we will discuss file management automation, which is also common in workplaces. Again, mostly powered by Python. Data mining also employs Python for structuring data. Another good automation idea is to automate sending reminder emails and text messages. Excel spreadsheets can also be read and modified using just Python. Python also used to automate flipping up of online forms. In the end, we will go through the concept of the Internet of Things and how Python is used in that field. So I hope I made myself clear with the agenda. So without further ado, let's get started.
First up, machine learning. Machine learning is huge. Its uses spread across almost every technological field. Python is commonly used for implementing machine learning models and algorithms. Here are some most popular Python libraries that are used for solving machine learning problems. First, NumPy. NumPy adds support for large, multi-dimensional arrays and matrices along with a large collection of mathematical functions to operate on these arrays. Next we have Pandas. Pandas offer data structures and operations for manipulating numerical tables and time series. After that, we have scikit-learn. Scikit-learn is a machine learning library for Python programming language. It features various classifications, regressions, and clustering algorithms, including support vector machines and other algorithms. Followed by that, we have TensorFlow. TensorFlow is also a library for machine learning. It can be used across a range of tasks but has a particular focus on training and interference of deep neural networks. Some of the applications where Python automation is extensively employed are industries. Industries have been using machines for a long time now, but with the introduction of smart machines, Python has come to use in the industrial machines. Followed by industries, we have hospitals. Hospitals use advanced medical equipment for monitoring various body conditions. The newer machines can suggest actions based on specific conditions, and for that, Python programming is required. Next, we have drones. Drones have become popular recently, and they are mostly powered by AI, which in turn is powered by Python. Now, we will move into web scraping. Web scraping is a technique used to extract large amounts of data from websites, and Python is the go-to language for web scraping. Beautiful Soup is a Python library that is popularly used for parsing HTML and XML documents. It creates parse trees that are helpful for extracting the data very easily. It will help for Selenium and Pandas libraries to be installed alongside Beautiful Soup so that the data can be structured properly and becomes ready for further use. The extracted data from website is usually stored in a local file in the computer or in a database in the form of tables. Moving ahead, we have the share market or cryptocurrency tracker. Python is used for tracking stock market and cryptocurrency prices. Let's look into it. The prices of the share market and cryptocurrencies go up and down every instant. So, Python is used to track and predict the market for profitable investment. Even though the markets are highly unstable, Python automation can provide a trend for a better purchase or sell. Long short-term memory is an artificial recurrent neural network architecture popularly used for applications like stock market predictions. LSTM models are powerful, especially for retaining long-term memory, and therefore can provide trends using large amounts of data. A well-informed investment can go a long way, and that's when automated stock price trackers come in, which of course is powered by Python. Followed by share market and cryptocurrency trackers, we have the chatbots. Chatbots are in high demand, and that's why it is an amazing area for implementing Python automation techniques. So let's dive into it. Chatbots are becoming increasingly common, especially in business and e-commerce fields, aiming to provide superior customer service experience to buyers. Chatbots are usually developed using natural processing language libraries like NLTK, Spacy, etc. These libraries can take in hundreds of thousands of sentences and then create a new sentence as a response to a question. Chatbots are automated customer assistance service powered by Python. They used to be only text-based, but now more and more chatbots offer voice support with the advancements of NLTK. And these libraries are completely based on Python. So followed by chatbots, we have file management. Python also offers automated file management features. So let's have a look at it. Python is used for automated file management, creating, deleting, renaming, and other file operations. A handful of Python scripts can perform full-blown file management operations automatically or at a scheduled time. Python scripts are used to perform file management operations either on the same file system or remotely. They are especially useful when files have to be modified over the network using some API technologies. So followed by file management, we have data mining. Data mining is a process of turning raw data into useful information using methods involving data science and statistics. Python libraries like NumPy and Pandas are useful for making sense of raw extracted data from any source, including local file or a website on the internet. Machine learning models like regression and classification are further applied to the structured data and bring out some results. Big companies often use data mining to turn raw data into meaningful information and gain insights. So followed by data mining, we have send reminder emails and text messages. Python is often used in workplaces to automate and schedule sending or receiving of emails and text messages. Python packages like email, SMTPlib are used for sending emails using just Python. You can turn a time-consuming task into an automated or a scheduled task. Emails and text are usually automated or scheduled among other tasks within a team to focus on other development tasks. This increases productivity and encourages better time management in a team. So, followed by sending automated emails and text messages, we will advance into update Excel sheets automatically. So Python provides a module that allows your Python programs to read and modify Excel sheets. Not just Excel sheets, but other formats like OpenOffice sheets or LibreOffice sheets, or basically any spreadsheet. Excel is a popular spreadsheet application by Microsoft, but there are a lot of alternatives in case you don't want to pay for it. OpenPyXL is a module based on Python that you can install for working with Excel spreadsheets and automating tasks using Python. Excel sheets can be daunting, especially when there is a lot of data in spreadsheets. Python helps automate filtering of data-based and specified factors depending on the data type. Python provides CRUD, that is create, update and delete, along with other features on Excel spreadsheets. So followed by Excel spreadsheets, we have fill online forms. Python also offers automated form fill features. So let's have a look at it. Python is used to fill up online forms automatically. Any suitable Python script can be used to extract data from a file and fill in equivalent online form. You can automate filling up of online forms like Google Forms or other sign up and login forms. Using vanilla Python scripts, forms can be submitted without any user interface. You just need to provide data equivalent to what is required to fill up a particular form on the internet. For example, if a particular Google form has fields for name, age, and gender, Python script should be written exactly in the order to fill up those fields. Followed by fill online forms, we have Internet of Things. So, lastly, let's discuss where Python fits in the Internet of Things. Internet of Things is basically the network of physical things that are embedded with some software, sensors, and other technologies that help them get connected to other devices on a network. Python provides various modules for developing services and applications for many IoT devices like Arduino, Raspberry Pi, etc. Packages like MRAA, Circus, MySQL database, and others are popularly used for IoT applications. Python is used as a primary language for IoT because of its compact syntax and fast runtime speed. IoT applications spread across various fields like smart appliances, wearables, etc. The ultimate concept of being an interconnected world more than ever.
And with that, we have come to the end of this tutorial. If you guys feel that we have missed out on some important topics that we were supposed to cover in this tutorial, then please feel free to drop them down in the comment section below, and we'll have your questions answered. If you guys like this video, then do give it a thumbs up. Please comment your doubts below, share it with your friends, and don't forget to subscribe Simplicode. Thank you.